students working in different departments of IISc, right? And this tutorial is aimed to be introductory in nature, so that students who have some unfamiliarity with this topic, they will be able to bridge that gap. And then from tomorrow onwards, we have invited several experts, both from India and abroad, right, to give talks on some of their recent work. So with that background in place, let's begin the first session. So this is aimed to be an interactive session at any point in time. If you feel that there is something that you want more clarification, feel free to stop me. Please be aware that this session is being recorded and it is being live streamed on YouTube. So if you have a question, please raise your hand. I hope one of the volunteers will have a microphone. They will come out to you. Try to say your question on the microphone. This way the question will also be heard on YouTube, and then I will try to provide my response. Okay, so we are studying reinforcement learning. So the first question that naturally would arise is, why study reinforcement learning? Now if you go to any top tier machine learning conference, for instance, I had an opportunity to be at NeurIPS this year, and whatever is written in this tweet was apparent. Basically everybody is doing RL, and anybody who is not doing RL is doing something related to RL. And then there are a bunch of other important but things that happen in these conferences. So now if you try to do reinforcement learning on your own and try to come up with a one-line summary of what is the current state of the art, maybe this comment that I found in some blog, which I will later show, right, summarizes it very nicely. It says that the unspoken truth about deep reinforcement learning is that it holds significant potential, but in its present form remains fundamentally disappointing. By that I mean, one would expect this RL to do much more, and somehow we are not able to extract the full juice out of it, right? So what do I mean by significant potential? Here are a bunch of applications where reinforcement learning has made a mark, and in these different examples, what I have tried to do is, I have tried to collect pictures from applications related to the projects that are pursued at IISc, right? Like for example, here there is, the first picture over here talks about or discusses robo-walking. This is done in Professor Shishish Kolataya's lab, and some of his students will actually be part of the hands-on tutorial later on today. This is RL in the histopathology context. This is done at the Center for Neuroscience here. Then we have RL in the context of LLMs, right? Both people in ECE, CSA, CDS, these are different departments at IISc. They work on these topics. Then there is reinforcement learning in the context of game playing. There is reinforcement learning in the context of stock market prediction, so on and so forth. So you can see that reinforcement learning has already made a non-trivial mark in a wide variety of applications, right? But if you try to do it on your own, right, I'm sure you would end up with a scenario like this. And this is the blog that I was talking about, and here you can see there is a comment, and this is the comment that I showed you a few slides back. So this blog says, beyond hype, the brutal truth about reinforcement learning, and it sort of succinctly summarizes by saying that watching an AI learn to walk is like watching a toddler on a unicycle blindfolded for 1,000,000 years, right? And if you try to go over this blog, it raises a bunch of issues why it claims that this is the reason. And instead of trying to write down the different aspects, what I did was I tried to create a word cloud, right? And if you have created this word cloud on your own, you would notice that the size of the font corresponds to the frequency with which a word appears. For example, there is sample inefficiency. It comes in big font, which means that the word sample efficiency appears repeatedly throughout the blog, emphasizing that sample efficiency is a major concern in reinforcement learning. Similarly, you have high variance, training instability, poor generalization, blah, 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 right? And then you can see somewhere there in short font, it says lack of theory, right? So it is no surprise that this blog is written by a practitioner who believe that theory can't, help resolve the challenges that are there. Okay, but I'm a theoretician, so I would like to focus on this lack of theory. So in this 4 sessions, that I'll be covering, and then you will have 2 more sessions of hands-on tutorial. I'll try to go over the basics of sequential decision making, Markov decision processes, some concept called as dynamic programming and reinforcement learning. And then I will talk about function approximation and deep reinforcement learning. In some sense, this is how reinforcement learning is used in practice. I'll try to make sense of some of the issues that have been raised in this blog. Why do these issues appear, and so on and so forth. And in the last talk, which will happen after lunch, post-lunch, right? In this talk, I will talk about some of the recent advancements that we have made in our lab with regards to addressing some of the issues that have been raised. Okay? All right. So let's begin with lecture 1, which will talk about some fundamentals of sequential decision making and Markov decision processes. Okay, so the first question is, what is sequential decision making? And the next thing is, how is it related to reinforcement learning? Okay, so let's begin with a simple warm-up exercise. Maybe some of you are just woken up, right? So let's try to do this exercise. So the question is that we have been given 5 digits, and we want to rearrange the digits so that we get the largest number imaginable, right? Easy question, right? No problem. You just sort them from, in descending order from the largest number to the smallest number. Well done. All right. So now let's take this problem a notch up. And you can see that here I have highlighted the word sequential decision making. So here also you had to make a decision, but the decision didn't seem that hard. But now let's see if the same problem, if it is transformed a bit, would you still claim that the decision making is not challenging? Okay. So the setup here is as follows. We have 5 blank spaces, and the digits are not revealed to you. Okay. Instead, the digits are going to be revealed one by one, right? And then what you need to do is, whatever digit you see, right, you come up with a strategy and place that digit somewhere. For example, let's say I reveal the digit 2. You decide I have to place it somewhere. Let's say you have a strategy, and according to that strategy, you said I will place it at the 2nd position. Now the catch is that once you place the digit, you cannot move that digit. Is this okay? Now you get another digit. Let's say this time it was 5. Now from among the remaining 4 blank spaces, you have to decide where you would like to place 5. Right? So again, let's say you have some strategy and you decide that maybe I need to place 5 over here, and so on and so forth. Right? So now the question is, how would you develop this strategy so as to place the digits in some order so that at the end you end up with the largest possible number? Right? Now the challenge is, you don't know how the numbers will come in the future. You have to decide now, right? And accordingly, you may either win or lose. Is this okay? So let's try to, go over this this problem. If you have a paper and pen, maybe you want to try it out, right? So I'm going to spin this random wheel, right? And it's going to throw a digit. You can decide which place you want to place this digit, right? And after 5 digits, we will see how many of you have managed to get the largest number, right? And while you are doing this, I don't just want you to, guess. I also want you to think, how would you go about coming up with, quote unquote, an optimal strategy? I'm saying quote unquote because at this point, we don't know what is an optimal strategy. How would we go about defining? And in some sense, this course will tell you how to define these concepts. Okay, but nevertheless, I ask you to, come up with a guess for what would an optimal strategy mean, right? And accordingly, think of a strategy that you believe, fits that criteria. Okay, so I'm going to spin this wheel. You may perhaps put 5 dashes on your sheet of page, right? And let's spin this wheel, right? And the first digit came out to be 9. I think this game is going to be easy now. Okay, but let's see what happens. So I'm going to spin it again. This time it came a 5. So please go ahead and place it. So let's spin the wheel again. This time I got a 0. So place it somewhere. I got a 0 again. Place it somewhere. I got a 1. Okay. So maybe this was easy. Maybe you guys came up with 95100 or maybe something like that. Let's try one more time. Okay, this time I got a 5. Okay, now it's interesting. Now you have to think where would you place the 5, right? It's not obvious. So so now please start a new 5-digit number, okay? Please don't go back to the previous number. So let's say you got a 5, and now you got a 0. You got a 4. You got a 5 again. You got a 5 again. Okay? All right. So I'm sure some of you must have got good numbers. I think the digits were not that interesting, but I can presume that, imagine the last digit was 9. Okay, then that is going to, change the story dramatically. Someone who had left the first digit open, maybe they would have an opportunity to place 9 over there, and otherwise, you would end up placing it in the remaining digit and so on and so forth. All right. So now I want one of you to volunteer and tell me, how do you think you would come up with a strategy to play this game, right? And before I, before you go ahead thinking about that, I would like to give the relation of sequential decision making to reinforcement learning, and I will also talk about some application of what you have just seen, okay? So what is a one-line summary of reinforcement learning, and how is it connected to sequential decision making? That is summarized over here. Reinforcement learning is learning to make sequential decisions under uncertainty to maximize, quote unquote, some long-term notion of reward via interaction. Okay, so there are a bunch of words that I have highlighted, all of which are important. There are sequential decisions, there is uncertainty, there is some long-term concept of a reward that we want to maximize, and you also have the opportunity to interact. Okay, so all these things that are put together, that is what makes reinforcement learning challenging, right? So now I asked you, think of a strategy to solve that 5-digit thing, right? So maybe I'll tell you to think about it after I discuss this slide. So I want to say that, on one hand, that 5-digit problem may have looked maybe relatively simple, right? And maybe you would have said, okay, if I put in some enough time, right, maybe enough energy, and thought a bit about it, maybe I could have come up with a reasonable strategy. Now my answer to you, my remark on that is, if you actually manage to come up with good strategies to such problems, you can actually solve very interesting problems in practice. So here is an illustration of one of the projects that I was involved in, right? So in this project, we look at histopathology image classification. So histopathology means study of tissues. In particular, the goal is to identify diseases, okay, by going over these tissues, tissue scans. So you have given a scan, and the goal is to classify, right? At a high level, you want to say whether there is tumor, no tumor, and so on and so forth, right? So now I want you to classify. I'm sure you are aware that there are state-of-the-art deep learning algorithms for classification. So you must be wondering, oh, if someone gave me an image, right, and if they gave me enough training data set, right, I should be able to do a reasonable job at classification. Do you agree? So this is in line with the first problem. That is, I give you all the digits, I want you to rearrange them and find the largest number. Do you agree? So if I give you the image, I ask you to classify, there are state-of-the-art algorithms, now use them to classify. Now suppose I twist the problem a bit. So suppose these images are very large in size, okay? So these scanners that are now available, they actually scan the images in very high detail. This is because they, want to even capture the, most minutest of information. And because they scan it at such high resolution, these image sizes are very big. Typically it is in GBs. These are called as gigapixel images, right? So because these images are very big, right, you may not be able to load these images fully onto your memory. Is this okay? And because of that, you cannot directly run your existing algorithm, right? And you may think, okay, look, the memory and all those things are now growing. Maybe soon we will be able to manage these large sized images as well. I'll just load this whole image onto the main memory and then, run my existing classification algorithm. But the problem with those ideas is that it's going to be very inefficient. It's going to be inefficient because the decision, okay, of whether there is tumor or not will actually depend on only one small portion of the image. You see there is some red dots over here, right? So it will be like some very small portion of the image. So you actually don't have to look at the full image, right? You have to carefully pick and choose some small portion of the image, and if you use that image to make your decision, you are going to make a good decision. So on one hand, the images are very large in size. So currently you will find it very difficult to load the full image onto your main memory, right? And then run your existing classification algorithm. And on the other hand, even if you figure out some way to do it, that method is going to be inefficient because the diagnostically vital information, okay, the information that is vital for making diagnosis, that is going to be present only in small portion of the image. So if you decide to load everything, right, it's like, you know, wanting to look only here, but you have so many things. So that's what is going to make it inefficient. Okay, so what we proposed in this work is that we will start with a low resolution version of the image. Because it is low resolution, it won't be big in size. So you load that. Now if you just use a classifier on the low resolution image, you are not going to do a good job because the low resolution image would have lost information, right? So what we do is we take this low resolution image, and based on this low resolution image, we sequentially decide which parts of the image to zoom into. Zoom into means I will, you know, look at the high resolution version corresponding to that small patch. Is this okay? And now the question is, if I allow you to view, let's say 10% or 20% of the high resolution image, right? How would you decide which 20% to look at, right? So you may say, okay, I'm going to look at this part. I have the low resolution plus this part in high resolution. After that, I will say, given this information, I decide to look at this part of the high resolution. Once I decide to look at this part of the image in high resolution, I say, based on this additional information, I now decide to look at this part of the high resolution. So here you can see a bunch of squares, and you know, the dark colors mean that we looked at these patches at the beginning, and then the light colors mean that we looked at these patches later on, right? And you can see that we don't look at the full image, we only look at parts of the image, right? And this is now similar to the problem of deciding which is the largest number, right, when the digits are revealed sequentially. So now you have to sequentially decide which part of the image I need to look at. Okay, so I hope you are able to see that sequential decision making, okay, is very useful in applications. Now, given this motivation and background, I would like you to think, how would you go about coming up with, you know, a plan or a strategy for deciding how will you go about placing the digits? Is this okay? Would one of you like to maybe take a guess? All right, okay. Okay, so what his suggestion is that, you know, if the number is below 5, you sort of try to put it from the left, and if the number is above 5, you try to put it from the right. But you can see that the strategy is very vague. I mean, it's right in spirit, but it is still very vague, right? A strategy would be, when you see 5, where should you place it? When you see 4, where should you place it, right? That is what a strategy means. I mean, it is right in spirit, but it is very vague. So how do we polish this, you know, idea that looks good in spirit into a clean idea? Is this okay? So now I would sort of, you know, give some hints of how would you go about solving this problem. The first thing is to realize that this problem is hard. So if it is hard, we would not know how to solve it. So the question is, how do we simplify this problem? Okay? So I say it is hard because there are 5 digits to decide. So I will drop 1 digit and I will ask, how do I go about solving the problem if there were only 4 digits? So if 5 digit is hard, maybe 4 digit is relatively simpler. It's still hard, but I can keep doing this until I have only 1 digit to fill. Is that an easy problem? Yes. I have only 1 digit. I don't have to decide. Whatever number comes up, I just place it there. There is nothing much to do. Okay? So the 1 digit problem is very easy to solve. Now let's build upon this to solve a 2 digit problem. So let's say I only have 2 digits now. Now I give you a digit, right? Now maybe I can use this rule and say that if it is above 5, I will place it in the tens place, and if it is below 5, I'll place it in the zeros place, right? And so on and so forth. So of course, it is possible that I get 7 and 9, right? So 7 and 9 would mean that I would end up placing the first digit as 7 and the second digit as 9. But of course, I can cook up 97 as the largest number. But my strategy is, if the first digit is above 5, I'll place it in the tens location. And if the second digit turns out to be 9, I'm forced to place it in the 0th position. Do you agree? So you can see that even with this strategy, I'm not going to win always. Are you with me? Right? So now we have to decide, what does winning mean? What would an optimal strategy mean? Right? So I hope you can see that because of this uncertainty, we would like to bring in some notion of expectation, which means that if I played this game many, many times, right, and I use the same strategy on all of these runs, which strategy would allow me to win more number of times? That's what winning in expectation means. Right? So you can see that there is some notion of optimality that we have defined in some expectation, right? And you can also see that we have come up with a way to take this relatively hard problem, break it down into simpler problems. That is, you start with a single digit, then you come up with a solution for that single digit problem, then you use that solution to the single digit problem to solve a 2-digit problem. Now that you have or know how to solve a 2-digit problem, I hope you can see that you will now be able to extend it to a 3-digit problem. Is this okay? Because as soon as you fill one of the digits in the 3-digit, that reduces to a 2-digit problem. Is this okay? So I hope you can see that this is a very nice recipe to solve such sequential decision-making problems. All right. So now the question is, how does an RL agent, okay, learn? Right? And you must have seen in the introductory slide, I had a lecturer teaching a bunch of robos, right? And that is illustrative of what I want to say here. In some sense, we want to understand how we learn. Okay, somehow we believe that we learn very efficiently, even though we don't have much capability, right? So we are nevertheless able to learn, and we want to somehow understand how we learn and use that to somehow figure out how we could teach agents, autonomous agents, right? That's the idea. So how does an RL agent learn? Well, here is what I have summarized. I have said that how do you go about learning to play a game like chess? What do? You play that game over and over again, right? You start with some basic strategy, you play with that basic strategy, sometimes you win, sometimes you lose. Based on when you lost, when you won, you use some insights to upgrade your strategy, right? And you keep doing that, right? That's how you learn. And the RL agent is supposed to do something similar. In particular, it is supposed to scale this trial and error approach to make autonomous agents learn to control interactive systems. And a 3-word summary of how we learn is given over here. First is that we act, get feedback, right? Maybe I come up with a very stupid strategy and I lose. It's okay. I get some feedback. I realize that maybe my strategy was very naive, right? And use that use that feedback to refine my strategy. And then I go back again, right? So I act, get feedback, refine my strategy, and repeat this process again and again until my strategy gets better and better. At a high level, this is what reinforcement learning is all about. Okay, so a quick description of how reinforcement learning fits within machine learning. So recall that classical machine learning mainly looked at something called as supervised learning, which includes classification and regression. The idea in classification and regression is that you have been given some input-output data set. In classification, the output is some discrete labels or categories. And the goal is to learn the mapping between the inputs and outputs, right? And an application of classification would be classifying emails as spam or not spam. And then you have regression. Again, you have the input-output data. The difference is that the output are now numerical values, right? Like, for example, you could use regression to figure out house prices based on size and location. So you have a data set of multiple houses. You know their locations, you know their size, you know their prices, and based on that, you come up with a mapping between size, location, and price, so that if you have any other property that is not listed in the database, you can wager a guess of what it would be, right? So in similar spirit, we can discuss unsupervised learning. here also you have been given some data, but the key thing over here is that the data doesn't have this input-output labels. Okay, instead, you have been given some unlabeled data, and the goal is, can we somehow figure out some patterns within this unlabeled data, right? So for example, you may think of clustering, and an example of that would be you want to segment customers, okay, for marketing reasons, right? And alternatively, you have been given some data, it is high dimensional, so you want to reduce it, okay, but keep the key information there. For example, you may want to do image compression, right? Using some principal component analysis or something like that. So now one can ask, what is the difference between reinforcement learning and supervised learning and unsupervised learning? In some sense, it is summarized over here, and the key word would be passive learning versus interactive learning, right? So in particular, for supervised learning and unsupervised learning, you have been given some data. In reinforcement learning, at least at a textbook level, we presume that we are not given some data. Instead, you have to interact with the environment. Like you have to play the game of chess, right, multiple times, and you get some experience. And based on that experience, you have to refine your strategy. And the goal here is to basically predict some input-output relation so that you are able to predict correct outputs for unseen inputs. Okay, and then in unsupervised learning, the goal is to discover some structure in data, and here there is the goal of maximizing some long-term cumulative reward. And as I said, the key thing is how we learn in these different settings. In supervised and unsupervised learning, there is a notion of passive learning. By that I mean you have been given this data set, right, and you ask, what is the best that I can do with this data set? In reinforcement learning, in contrast, okay, the learning is active, right? So you take actions, and these actions will influence the data that you will collect in the future, right? And the feedback that you will collect thereafter, right? So if you play a game of chess and you decide never to learn from your strategy, right? You are always going to get only like very what should I say, useless data, right? But if you refine your strategies, then you will start seeing okay, maybe at these places, these strategies make me win, these strategies make me lose, and so on and so forth, right? And the other difference includes at the level of feedback. So here we have some correct output labels, right? And in unsupervised learning, typically we don't have feedback, right? And in reinforcement learning, the feedback is given at the level of scalar rewards. I will sort of elaborate. And an example of this would be, suppose you are playing some game, right? You take some action, and you get some score, right? Or alternatively, let's say you are investing in stock markets, you buy something and you see some changes, right? So that will be like an immediate feedback that you get, right? But of course, in stock markets and other places, you are not just caring about immediate feedback. You want that, over a long run, you sort of gain, right? That's the idea. And at some level, that's perhaps one of the examples that you may want to keep at the back of your mind. And here are some examples: spam detection, image classification, clustering, game playing, robotics, and so on and so forth. All right. Okay, so now let's talk about the second part of this talk, which concerns Markov decision processes. The first question you may want to ask is, why should we study about Markov decision process? So let's go over a detailed summary of reinforcement learning one more time, and then try to connect how, let's try to see how Markov decision processes play a role over here. Okay, so here is a one-slide summary of reinforcement learning. At its core, reinforcement learning involves an agent interacting with an environment. In particular, the agent must sense the environment's state, right? And then take an action to affect that state. So when the agent takes an action, the state of the environment is affected. And in this interaction, the agent will get hold of some reward. Is this okay? And the agent's goal is to maximize a suitable sum of rewards. In particular, we will look at the case of a discounted sum of rewards. I'll elaborate what it means. And I will use this notion called as value function to denote this sum of rewards. Okay? So there is a notion of immediate reward, and then there is a notion of sum of rewards. Is this okay? So we want to distinguish between the two. The goal in reinforcement learning is not to maximize the immediate reward, but to maximize the sum of rewards, right? And the challenge is that the transitions. By that I mean, the environment is in a certain state and the agent must take an action. So when the environment is in this state and you take an action, the environment will move to a next state, right? So this is what do I mean by transition, right? So how do these transitions happen? They are typically unknown. For example, if I ask you, if you invest this much money in stock markets, what will happen next? Do you think you know? Right? So you don't know exactly. I mean, of course, you have some data, you can make some predictions, but you don't know exactly. That's what I mean that the transitions and rewards are uncertain, right? And in parallel, right, the states and actions are very large in number. Okay, so this is what makes reinforcement learning very challenging. And reinforcement learning, as I said before as well, has found a wide range of applications across large language models, robotics, game playing, health, finance, material discovery, so on and so forth. Okay, so now what is a Markov decision process? So as I said, an agent needs to interact with an environment, right? Now this environment, okay, we will model it as a Markov decision process. Now what is a Markov decision process? It's a stochastic process, right? And to define a Markov decision process, I need to specify these 5 things. The first includes the state space, which basically tells the different states that the Markov decision process can be in. Then I have to prescribe the action space. Basically, this lists the set of actions that an agent can take at each of these states. And to keep things simple, we will presume that all the actions are available at every state, just to keep things simple, right? And then, as I said, there is some notion of transition, which is prescribed by this transition probability kernel, which basically specifies what's the probability that the environment transitions from state S to S prime under action A. So the the transition probability is described by P, and this P specifies these probabilities. And then you have a notion of an immediate reward, right? So the immediate reward typically is a function of the state and action. It can also be a function of state, action, and the next state, and so on and so forth. But to keep things simple, we will presume that the immediate reward is only a function of the state and the action that you take, right? And then there is notion of a discount factor. So a discount factor is a scalar, which is a number between 0 and 1. In particular, it is strictly less than 1. It is used to distinguish between the preference for 1 unit of reward that you will obtain at the present time instance compared to the the same unit of reward that you have obtained at the next time instance, right? So just to illustrate, if I tell you I'm going to give you, let's say 1 crore today, right? And then I say I'm going to give you 1 crore 10 years down the line. Would your excitement be the same, right? If your excitement is not going to be the same for the 2 scenarios, that's where the discounting comes, right? So you're not going to be as excited if I tell you I'm going to give you 1 crore 10 years down the line. Is this okay? All right. So here is an example of a Markov decision process. Yes? They can be the same. Okay, so here is an illustration of that example. I mean, illustration of what you just asked. So here is an MDP. So MDP is an acronym for Markov decision process. So whenever I write MDP, you have to interpret it as a Markov decision process. So in this Markov decision process, you can see that there are 3 states: alert, sleepy, crashed, and we have 4 actions. Is this okay? So let's go over, what is the consequence of each action at each state. So let's say we are in this alert state, right? And if I now take the action of study, so what this number, the number in black, tells us is the probability that you stay at the same state, and this number in green or red tells us the immediate reward that you would get. Is this okay? So I've put some numerical value at this point. It will depend on the domain typically, right? So here, let's say, if you are in an alert state and you study, then you remain alert with probability 0.8 and you get a reward of +10. But it is also possible that with some probability, that is 0.2, you will move to a sleepy state, right? You study, but you feel sleepy. And this time, because you are moving to the sleepy state, right, maybe you only get a +2 reward. Is this okay? Right, so this is something that could happen, right? And similarly, we have some other impact of actions as well. Like for example, if you are in the alert position and you decide to take the nap action, maybe you go into a crash state, but you get some nice reward over here, right? And when you are in the sleepy situation and you decide to scroll your phone, right, then with probability 1 you crash, right, and you get perhaps some dopamine effect, you feel happy, but you go into this crash situation. Is this okay? So I hope you are able to interpret this diagram. Each arrow over here implies some action. The numbers in black correspond to the probability that if you take this action, this transition will occur. And you can see that if you take a single state and add up the probabilities for the same action, that is this action and this action, they will always end up with, the value would be 1. So if you take this action, okay, with probability 0.9, you will remain in the alert setting. That is, if you decide to drink coffee, with probability 0.9, you will remain in the alert situation. But it is also possible that with some probability, you move to the sleepy state. Is this okay? So this is an example of an MDP, right? And I would like to ask you, does this ring a bell? Have you seen flowcharts, right? Do you think flowcharts and this description are one and the same, right? Or not? So I will ask this question and leave this question and let you think about this. All right. So I said that the environment is typically modeled as a Markov decision process. Now the question is, what does Markov in this Markov decision process mean, right? The Markov in the Markov decision process implies a Markov property, which means that the environment is memoryless. Is this okay? The first question is, why do we want to work with Markov decision processes? Because it's easy to work with. What is the other reason for working with Markov decision processes? Despite it being easy, when I say easy, you can do a lot of math on it. Despite it being easy, it can model several application scenarios. Okay, so what does the Markov property mean? At a high level, it means that the environment is memoryless, which means that the probability that the next state is S prime given the history only equals the probability that the state at time t plus 1 is S prime given the current state and action. Okay, and this expression equals P of S prime given SA, which comes from the definition of your MDP. So you recall that in the definition of MDP, you had your transition probabilities, right? So this value equals this value. So in other words, the past matters only through the present. So this is like a very loose summary of what memoryless property means. And here is an example of what do I mean. In chess, the current board position, okay, the positions of different pieces, captures all the relevant information from the past, and the next state is completely determined by the current position and the current move, right? So let's say there is a configuration. If I make a move, you don't have to guess, what will happen next. If I tell you this is the move I'm going to make, you know what is going to happen. You don't have to, worry about what were all the past actions that were taken. You don't have to worry about all those things. Similarly, you don't have to worry about what the previous states were. Given this state, you make this move, this is what the next state would be. Okay, so that is what do I mean that by the statement that the past matters only through the present. All right. So now, as I said, in reinforcement learning, we have an environment, we have an agent, and this agent interacts with the environment. So how does an agent interact with the environment? It interacts via what is called as a policy. Okay. So what is a policy? It's basically a sequence of rules, right? mu0, mu1, so on and so forth. And the rule at time t is basically a function from the state space. So S here is the state space, and A is the action space, and delta of A is the set of distributions over the action space. Okay, let me just finish. So mu t is a function from the state space to a set of distributions over the action space, right? So mu0, mu1, mu2, and so on, the indices being different over here imply that you could start with a different strategy. At time instance 1, you could have a different rule. At time instance 2, you could have a different rule. And by a rule, I mean a mapping from state to the set of distributions over the action space. By that, I mean if you see a state, you decide that I'm going to pick my actions as per this rule. Maybe I will pick this action with 0.5 probability, this action with 0.6 probability, and so on and so forth. Is this okay? And of course, you can also say that whenever I see this state, I'm always going to pick this action. That could also be possible within this description. Yes, what was your question?
Yes, I just want to follow up on your memory-less aspect. So theoretically, can you say that that is always possible? Like, can you always say that you can always capture whatever the relevant information is from the past in current state?
Yeah, so that's a very important question, okay? And the answer is, let me give like a technical answer, right? If you describe the state appropriately, right, then you would be able to ensure that there is a memoryless property or the Markov property. By that I mean, somehow if you are able to, imagine all the information, right? So that once I know that, if I act, I will know what the next state is. But how do we get hold of all this information? Is this okay? So typically, the challenge is that we don't get to see the state, we only get to see the state partially. Is this okay? Like for example, let's say, you see the stock market prices, that means you know the price of every stock, right? And let's say I tell you, what strategies different people are adopting, right? Would you be able to guess what will be the performance of the stock market at the next time instance, right? If you would be able to predict, then you have all the information. But typically, you don't have all the information, right? Maybe there is someone planning some strategy somewhere, right? And it is going to affect the market which you are not aware of, right? So this is what is called as partial observability, right? So the answer to your question is, in practice, typically you only have partial observability. That's what makes things challenging. But if you somehow could gather all the information and use that information to define your state, in that setting, one can say that we would indeed have a Markovian setting. Does that answer your question? All right. So now, the key thing to note here is that when I define this policy at time instant, the decision rule at time instance t is only a function of the state. Is this okay? So one of you may perhaps guess, why is this decision rule at time instance t only a function of the state, right? Perhaps it could be a function of the whole history. At time instance t, you have seen S0, S1, S2, S3, all the way up till ST. Why don't I come up with a rule that looks at this history and then decides which action to take? Is this okay? So you can see that those decisions rules will be very sophisticated, very complicated to study and so on and so forth, right? But nevertheless, we may feel that, okay, just because it's hard to study, why we should ignore them? We should, include them. But thankfully, what is known is that if you take any history-dependent policy, its performance, okay, can be matched by a Markov policy. By Markov policy, I mean that a policy which has this structure. That is, it takes an action by looking only at the current state and ignores the history. At time instance t, it only looks at the state at time instance t and then decides what to do, right? So this is what is called as a Markov policy. So if you look at this textbook by Putterman, whose description is given over here, one can see that any history-dependent policy can be matched in performance by a Markov policy. Hence, it suffices to work with Markov policies. All right. Yes.
You mentioned that reward is a function of S and A, right?
Yeah.
Shouldn't it also include S dash or S prime?
So in different scenarios, it could depend on S prime as well.
In the example that you gave,
in the example, it depended on S prime as well.
Okay.
Is this okay?
Yeah. So in general, is reward deterministic or probabilistic?
It could be uncertain also. The distribution could depend on S, A and S prime, but the reward could come from that distribution. All those things can happen. Okay, but in this discussion, we will keep things simple and presume that it's a function of only the state and action. Yes?
Hello.
Yeah.
Maybe my question will not make sense, but still, while we take action via Markov policy, what if we have a history table and we take the another decision with the help of that history table, which is generated by the Markov process? Is it become the like normal history thing?
I'm not sure I fully understood your question, but let me try to make sense of it. So you are saying that maybe there is a history-dependent policy,
okay,
right?
But it is like the history which is generated by Markov policy, not the match performance.
So let me try to summarize. See, so what you are saying is that maybe there is some policy with which somebody else is interacting with the environment. But keep in mind that if somebody else is interacting with the environment, right, that will already affect the state of the environment. It's not like once you are at state ST, somebody acts and you are still able to see ST. So this is not like a multi-agent scenario at this point. There's only single agent. Okay, so either you have your Markov policy or you have some other policy. There is no like somebody else is applying the Markov policy and you are applying a different policy. Whatever policy with which you interact with the environment, that is going to affect the environment. Is this okay? Right? Okay. Okay, maybe we can take some of these questions offline, otherwise I will not be able to finish. Sorry about that. Okay, so now let's see what would happen if the agent interacts with the environment. What would we get? Right? So we would get what is called as an experience trajectory. By that I mean you would see some state, action, reward, state, action, reward, and so on and so forth. So let's see what it implies. So you start at some arbitrary state S0, then you interact with the environment based on your policy. So recall that your policy said use rule mu0 at time instance 0. And you see that the current state is S0, so you use that rule. So you have a distribution, you sample an action from that distribution and you get A0. So once you get this A0, you get a reward which is a function of your state and action, right? And then the environment makes a transition to the next state S1, which is presumed to be sampled from this transition kernel. At S1, again you act, which means that you take an action, and this time you take an action according to mu1, right? And mu1 is a distribution that depends on what the current state is. Then you get to see the next reward and so on and so forth, right? So just because I have written mu0, mu1, mu2 doesn't mean that your mu0, mu1, mu2 have to be different. They could be the same policy, I mean same decision rule at different time instances as well. It's up to you. How do you want to interact with the environment? Okay, so now the next question is, if I have a policy, how good is this policy? Is this okay? We need to first quantify, right? No, not go by feelings. Okay, this looks good, this looks nice. Okay, we don't want to go with these subjective notions. We want to quantify, right? When do we say, or how good is a strategy, right? So towards that, there is a notion called as a value function. So a value function for a policy mu bar is a vector. Okay, it's a vector whose size equals the number of states in your MDP. Is this okay? If your states have, in that MDP example, we had 3 states. So in that setting, the value function will be a vector in R3. And the little sth coordinate of that vector is defined in this fashion, right? So you see that there are 2 notions. The first description is in that of a finite horizon setting, which means that I'm going to interact with the environment for t many time instances, where t is some fixed quantity, right? So that is what do I mean by finite horizon. Alternatively, we could also interact with the environment infinitely, right? Often, in which case we have an infinite horizon setting. So in the finite horizon setting, notice that I look at the sum of rewards that I get plus the reward that I get at the terminal state. At the terminal state, I don't get to act. Okay, I reach that state and that's it. I'm not allowed to act because the interaction has stopped. So you see that I look at a sum of rewards where the action is chosen according to your policy mu bar, right? So what is the expected sum of discounted rewards? Okay, conditioned on the initial state being S. So this S and this S are one and the same, right? So if you define V mu bar of S in this fashion, the vector that you end up with is called as the state value function, right? So this definition is in the finite horizon setting. This definition is in the infinite horizon setting. So one can define these value functions for different policies. And now one can ask, what is an optimal policy, right? And policy mu bar star is said to be optimal if it is better than every other policy. Now the value function is a vector. So what do I mean by one vector being better than another vector? I mean in a coordinate-wise sense. By that I mean V mu star of S should be bigger than V mu bar of S for all mu bar and all S, right? So now one can ask, would such a policy exist whose value function is better than every other policy at every other state? Would such a thing exist? So one can actually use something called as a Banach fixed point theorem and so on and so forth to show existence of such quantities. So one can indeed show that for MDP, a unique V star, okay, which is the value function of the optimal policy, exists. But one would like to highlight that while the value function could be unique, there could be multiple optimal policies. Okay. Now, given this formal description, one can ask, okay, what is reinforcement learning? Well, reinforcement learning is to learn this optimal policy from the sequential interaction data, ST, AT, RT, and so on. Is this okay? So now one can ask, can we come up with a characterization of these optimal policies? Is this okay? So we now have given some description. Now we would like to ask, can we characterize them? So first let's go over the finite horizon setting. Is this okay? So now let's try to recall how did we, discussed one should go about solving that 5-digit problem. What did we say? We start with a single digit, right? Then we go to the 2-digit, then we go to the 3-digit and so on. So in that sense, okay, we will try to characterize the optimal policy. So what we do is, we define Vt star, that is the value function at time instance t, that is the terminal time instance, to be the terminal reward. So if I am at state S, I am only going to get Rt of S. There is nothing I can do about it. Now let's say I am at one instance before that. Okay, so if you put k equals 1 over here, you would have Vt star of t minus 1, right? And now, if you put k equals 1 over here, you would have Vt star of t. So if you start at S, and if you pick an action A, this will be the probability with which you will move to S prime. So since you started at A, and you picked an action A, you would get an immediate reward, and then you will end up at this state S prime, and this, at this point, you will get the terminal reward. So what we are trying to do is, if I am just one step away from t, how do I go about deciding? So if I am at state S prime at time instance t, I know what is going to happen. Now if I am one time instance before, I know that for different states, what is the terminal reward I am going to get. So if I start here, I would like to know which action I should pick so that the immediate reward plus the terminal reward, that is maximized. So one can see that Vt star of t minus 1 will be max of this quantity over here. So you can see that we are solving the problem in reverse. So the last stage is easy. Like if I ask you, today is the exam, what can you do? There is nothing we can do, right? I mean, the exam is there, nothing can be done. Now I ask you, given that nothing can be done today, what would you do one day before the exam? Is this okay? And imagine if you could, backtrack this way, you would be able to figure out 100 days before the exam or, a few months before the exam, how you should go about, planning. Okay? So this is what this tries to tell you. And once you figure out, these optimal values at different time instances, you can figure out the optimal rule as well. Okay? So the optimal rule at time instance t minus k at state S is to pick that action which maximizes this quantity. So this quantity and this quantity are one and the same. So you pick the action that maximizes it. This way you get the rule that is the best at time instance t minus k. So the idea is you start at time instance t and you go one step back at a time and you figure out what is the optimal strategy from at time instance t, at time instance t minus 1, at time instance t minus 2. And this way you figure out what is the optimal strategy for all time instances. Okay? And this is what the optimal strategy is. So now one can use a similar philosophy in the infinite horizon context, right? So in the infinite horizon context, instead of there being a finite sum, we have an infinite sum, right? And again, by using a one-step decomposition like we did previously and using some algebra, one can show that the optimal value function which actually satisfy a rule like this. In the previous case, v star t minus 1 equaled something plus v star at t. Here in contrast, in the infinite horizon setting, we would have v star at both places. Okay, one can actually show that. And one can show that the policy which maximizes this quantity is the optimal policy. And one can see that the policy mu bar star in which the decision rule is mu star at all time instances. Okay, that will be the optimal strategy. So I hope you can see the difference over here. Okay, here the strategies, I mean the rules at different time instances are different, whereas the rules over in the infinite horizon setting are the same. Right? So I hope you are able to appreciate that. If you have a finite horizon setting, let's say I have 10 days or 1 month to the exam, the rule on the first day of how you would go about preparing for that exam and 1 day before the exam cannot be the same. Is this okay? So that's what is illustrated over here. Whereas if you have an infinite horizon setting, right, what you do today, if it is optimal, that same thing you should do tomorrow as well, and so on and so forth. All right. So I now come to the end of this talk. Okay, so what are the takeaways from this talk? So I sort of gave you an intuition of what reinforcement learning is. The summary is that reinforcement learning involves optimal sequential decision making under uncertainty, and I should add the word with interaction. Okay, the interaction part is important. Then we discussed MDPs. MDPs give a structure to this problem, right? And they also help us characterize optimal policies. Okay, and now the question is, how do we compute these optimal policies? We have given a characterization, right? So what mu star satisfies, how does it satisfy here, right? So how do we go about solving this problem? In finite horizon problems, perhaps we can use this rule itself to solve this, right? Because for time instance t, we can figure out what Vt star is, and from there you can go one step back and keep solving what is Vt star minus 1, V star t minus 2, and so on, and accordingly figure out what these mu stars would be. But how would you go about solving it in the infinite horizon setting? Okay, so that will be the goal of the next talk. With this, let me stop. Thank you. So I think we can have time for maybe 1 or 2 questions, and there is a coffee break. So those who wish to have coffee, feel free to go ahead. Okay, but I'm available here for a few questions. Yes? This one? Okay, so let's go over it. So did you understand this notation?
What does the T signify? Like,
so T is the length of the horizon, okay, right? So you have T time instances to interact with the environment. Let's say you have 30 days to prepare for an exam. Is this okay? So T here would be 30. Okay. Is this okay? So now if you are at state S at time instance T, right, what would you get? Like let's say at, on the day of the exam, you are very well prepared, right? There is nothing you can do, right? You are very well prepared, and that's it. You will get good returns, when you give an exam from a well prepared state. But let's say for whatever reason, on the day of the exam, your S, which is the state, is completely unprepared. So on the last day, I hope you agree that we cannot do anything. Is this okay? So whatever is the state, that is what is going to affect my performance. So if I'm completely unprepared, maybe I'm going to, perform very poorly in that exam. So that is what this means. At the terminal time instance, whatever is my state, that is what is going to determine what is the returns I'm going to get. Okay. So now let's say on the day of the exam, I know that if I'm this state, I'm going to get this. If I'm going to be in this state, I'm going to get this. Let's say now we go 1 day before that. Is this okay? So on the last day, I know that if I'm in different states, what is going to happen? I'm 1 day before that. Is this okay? In 1 day, let's say I'm at a particular state. So that is what this means. So if I put k equals 1, V star t minus 1 means what is the best I can get, okay, starting from time instance t minus 1 at status. Okay, so at time instance t minus 1, so I am, don't think like that. So at time instance t minus 1, I am at state S. So I am just looking at, the last but 1 day and the last day. That's all I am looking at. I am saying if I am at state S, okay, let's say I am very well prepared 1 day before the exam, right? Now what should I do, right? So perhaps the best action would be revise, okay, or maybe it would be like relax, one of the two. Right? Because if I am at a very well-prepared situation, maybe going from a very well-prepared situation to completely unknown situation, that is going to have very small probability, right? So I'm just saying, if at time instance t minus 1 I am at state S, what is the best that I can do? So I start at S at time instance t minus 1. Given that at time instance t minus 1 I am at state S, I pick an action A. So this is the reward that I will get. Okay, and then this state and action will lead me to this state S prime. But this will be the state at the last day. And I already know that if I am at S prime scenario, what is the returns I would get? So I take the current reward plus the value that I will get if I am at state S prime. Okay, so this is like a one stage problem. If I know what is going to happen tomorrow, given that I know what is going to happen tomorrow, what can I do today? So this is just solving that problem. Okay, and then it is saying this is the returns or the best returns I will get from time instance t minus 1. So it is best because I am maximizing over all possible actions. So after I solve this, v star t minus 1 will tell me at different states what's the best I can get. So now what I do is I go to v star t minus 2, that is 1 day before the last but 1 day. Then I ask on this day what I should do. So now I know what's the returns that I will get from time instance t minus 1 onwards. Now notice that when I say I know the returns, I just don't mean the immediate reward. I also know that if I take an action, I will go on to some other state, what's the best I can do, by taking all possible actions. That is what I know when I say I know that v star of t minus 1 is known. So given that I know what can happen from time instance t minus 1 onwards, now I don't care about t and all. I only know that from t minus 1 onwards, I know what is going to happen. So now I ask at time t minus 2, what do I do? Is this okay? So this is, to summarize, at any given iteration of this algorithm, I'm solving a one-stage problem. One-stage problem meaning given that I know what is going to happen from tomorrow, what can I do today? That is the kind of problem I'm solving over here. Okay? Yes?
Hello. Yeah, it's just a tiny doubt. In the one of the statements in one of your slides was so that only, the previous one that you showed. Or the one after. The one after.
One before?
Yeah, this one. So the statement that there exists a Markov policy which matches a history-dependent policy, is this a theorem or an empirical result?
This is a theorem.
Okay.
It can be, you can see this reference over here. You can go to Puterman, Markov decision processes. You can go to chapter 5. If I'm not wrong, in section 5.5, there is a result. If I'm not wrong, it is 5.5.3. You can go over there and you can see that they have discussed this. Is this okay? Yeah. Okay. It's a theorem. It's not empirical proof. Okay. All right.
Hello.
Yeah.
Sir, my question is that when you are saying that decision making under uncertainty, I guess that we are assuming that the model of the system is unknown, and we are giving some input to the system, right? We can partially observe the state and we get some output. Based on the output, we try to construct some strategy for the next step, and then we are gathering all the state and output data, and based on that we are creating a model of the system which gives us future strategies.
Okay, maybe I'll try to summarize it, right? So, so here is the Markov decision process, right? So the knowledge of Markov decision process would mean that I know all these 5 things. Okay, I know the state space, the action space, the transition probabilities, right? The rewards and the discount factor. So when you say I'm using data to construct a model, that basically means I'm trying to estimate all these quantities. In particular, I'm trying to estimate the transition probabilities. Is that correct? I presume that's what you mean. So your question is, am I using the data to estimate the underlying model? Estimate the underlying model means estimating MDP. In particular, it means estimating the transition probabilities. Is this okay? So your question is, am I using the data to estimate the transition probabilities? I believe that's your question. And then you are asking, if I know the transition probabilities, can I then solve the problem? Right? And I believe that's what you're asking. In particular, you are saying, am I finding the optimal strategy by first figuring out the model and then using the model to solve the problem? Is that correct?
Yes, sir.
So at this point in time, in this lecture, I have not discussed the scenario, what is called as model-free setting. Okay? Model-free setting means when I don't know the transition probabilities. Is this okay? So in the next class, we will actually look at some instance of model-free algorithms, where I will show you that we can actually get hold of the optimal policy without constructing the model. Is this okay? So I will sort of elaborate on that. Okay, so I request you to hold your question until then. So we don't find the model and then solve the problem. Okay, we actually solve the problem directly by using the data itself. So in other words, instead of figuring out the transition probabilities, we actually use the data to figure out some other quantity, and that quantity is good enough to tell us what the optimal policy would be. Is this okay?
Sir, so at this point, what do you exactly mean by the uncertainty here?
Uncertainty means that if you start at a state S, like for example in this example, if you start at this state, right? If you take this action, there is some probability that you stay here, but there is also some probability that you move to this state. Is this okay? So you take the action, you don't know what the next state is going to be. That is what uncertain means. With some probability, the next state could be that you still remain in the alert situation, or the next state could be that even though you had coffee, with some probability, perhaps the coffee relaxed you, and then you feel sleepy and you actually fall, you go in the sleepy state. So that is what uncertain means. It means that even though I have taken action, I do not know what the next state would be. Is this okay? Certain would have been, I am at this state, I took an action, this is the next state where I will end. That would be I would describe that as certainty.
Okay, so can I say that the exact model of the environment is not known to me, that's why I don't know the outcome of my input?
So again, I will describe this in detail in the next lecture, but here is a short answer. Even if I know the transition probabilities, okay, that is even if I know the model, if I ask you what is the optimal strategy, right? I would ask you, how would you go about solving this question? Okay, now in this finite horizon setting, you can see that I have told you a way to figure out what should your optimal strategy should be. And you can see that in all these calculations, the knowledge of P plays a role.
Yes, yes.
Is this okay? So if you know P, right, you can solve this problem. Is this okay? Now let's go to the infinite horizon setting. The infinite horizon setting involves solving this problem. Okay? Now the challenge here is, you want to know V star, but this V star sits on both sides of the equation.
Yes.
Is this okay? So now I'll ask you, let's say you know the value of P. Let's be in the scenario where you know the value of P, that is you know P, SA, S prime for every SA and S prime. Even then, can you solve this implicit equation?
No.
Is this okay? So that is what, is the challenge. Even when you know P, okay, how do you go about finding the optimal strategy? That is challenging. It is even more challenging when you don't even know P. But we will sort of go take a look at this problem in a sequential fashion. We will begin by asking, suppose we know P, can you find the optimal strategy? Then, can we take those ideas as inspiration to develop algorithms, okay, that will work even when the transition probabilities are unknown? Okay, that will be the idea. Okay, all right, thank you.
So
maybe you can ask me outside. Is that okay? Maybe we can ask outside, and I'll also be available during lunch break. Is that okay? You can ask me outside. Let's stop for the day. Let's stop for the time being.
circulating an attendance sheet for each of the sessions, and it's classified into IISc, non-IISc participants. So if your name is not mentioned on the sheet, you can just write your name and put a signature for each of the sessions that we're attending. So I'm a volunteer. There are 4 volunteers: me, Nivedita, Aditya, and then Girik, who is back there. So if you have any questions, we'll be coming around with microphones during the, as happened in the first session, right? So just raise your hand and we'll give you a mic so it can be heard on YouTube, etc. Yeah. So just some logistics.
All right. So maybe we can begin the next lecture. I'll just see if Sanjay, Nivedita, can you just check if Sanjay or someone from the auditorium is there? I just want to make sure we can go ahead. We can start? Okay. All right. So hello and welcome everyone to lecture 2 on reinforcement learning. Okay, so right after the session ended and also during the coffee break, many of you had multiple questions, right? These are very, very important questions, and we will try to address some of these questions in this lecture and the next, okay? And maybe we can interact one more time during the lunch break if you still have additional questions related to the things that we are going to study in these 2 lectures. Is this okay? All right. So this lecture is titled Dynamic Programming and Reinforcement Learning. At a high level, what I want to now discuss is how to find this mu star. Is this okay? The optimal policy, how to find it. So at some level, we saw how to do it in a finite horizon setting, right? We sort of do it, like you go to the last stage and then you sort of go to the one stage before that and so on and so forth, right? And it sort of looked a bit challenging. How do we figure out how to find the optimal policy in the infinite horizon setting? Is this okay? So we are going to discuss that. Now let's do a quick recap of what we saw in the previous class, right? So the value function of a policy mu bar, okay, is in the infinite horizon setting is the expected value of the infinite sum of discounted rewards starting from state S. Okay, and here the expectation means that the actions are being chosen as per your policy mu bar. In particular, at time instance t, you take an action based on the knowledge of st and your policy mu t. Is this okay? So that will lead to some experience trajectory, and whatever is that experience trajectory, you take this sum of rewards on that trajectory, and this expectation is over all possible trajectories. Okay, and then we define the optimal policy to be one whose value function is the largest. Is this okay? So mu star is the optimal policy if its value function is bigger than V mu bar for every policy mu bar across all states S. Right, and then I sort of said it in passing that the optimal value function actually satisfies an equation like this. So let's go over it in some more detail this time, right? So the sequential decision making problem is hard because you have to figure out what to do across all time instances. Right? Let's say I gave you a position of the chessboard and I ask you what's the best move for this time instance, and let's not care about what will happen after. I hope you agree that that's an easy problem, right? You have a finite number of positions to make changes to, and you figure out, okay, what's the best, right? So that is an easy problem. What is hard is after you make that move, it's going to have some consequences, right? Like for example, maybe you are in a position where you can defeat the queen, right? So at this particular time instance, maybe defeating that queen or capturing that opponent's queen may turn out to be a good move. But maybe it lands you in a position from which there is no escape. Then that is not a good move, right? So the sequential decision making problem is hard because the immediate action can influence future states, right? And you don't want to just be good in an immediate sense, you want to be good in this sum sense. Okay, so you just don't want one reward to be large, you want the sum of rewards to be large. Okay, that is the challenge. Now what this decomposition that I mentioned in the previous lecture does is, it tries to take this sequential decision making problem into a one-stage problem. Is this okay? It takes this sequential decision-making problem into a one-stage problem, right? So here you can see that you are sort of saying, suppose the terminal reward of a one-stage problem was V star, right? What will be the best action to take? So this is like, viewing this sequential decision-making problem into as a one-stage problem. Is this okay? So you have one action. So you start at some state S, you take an action, it will take you to a next state, which is S prime, right? So you only look at the story at S, say, S prime level. So you start at S, take an action, move to S prime, right? So this is the one-stage problem, and you are presuming that somehow the reward at the terminal state is this. Then what is the best action to pick so that this quantity is maximized? Is this okay? So the whole idea over here is to take a sequential decision-making problem and break it down into multiple one-stage problems and solve each of these one-stage problems. Is this okay? So in the finite horizon setting, it was relatively easier because this quantity was not this itself. So if you recall, in the finite horizon setting, here you had V star t minus 1, here you had V star t. So you first figure out what is V star t, then this quantity becomes known under the assumption that your p's and r's are known. So if you know these things, then this quantity becomes known, and once this is known, you can figure out V star t minus 1. Once you figure out V star t minus 1, you again solve a one-stage problem between time instance t minus 2 and t minus 1. And again, this quantity would then be known because it was calculated in the previous iteration. And you use this knowledge to figure out what should V star t minus 2 should be, and so on and so forth. Okay? While the one-stage interpretation applies even in the infinite horizon setting, the challenge is that the unknown quantity sits on both sides of the equation. Is this okay? Are you with me? So the question is, how do we solve this thing, right? And we also observed that in the infinite horizon setting, the optimal policy turns out to be stationary. By stationary, I mean that the rule that you use at time instance 0, the rule that you use at time instance 1, they all turn out to be one and the same. Is this okay? So this is what is called as a stationary policy. In finite horizon settings, in contrast, the optimal policy often will be non-stationary, which means depending on the time instance, you may have to adopt a different decision rule. So because of the optimal policy being stationary, to keep things simple, henceforth what we will do is, we will focus only on the class of stationary policies. Like previously I said that we can ignore history-dependent policies and only focus on Markovian policies. These Markovian policies could still be non-stationary. Now we are going even a step ahead and saying that for infinite horizon problems, it suffices to look at stationary policies. Means at every time instance, I'm going to apply the same rule, use the same rule to decide which action to pick. Henceforth, whenever I write mu, I would imply that it is the stationary policy mu bar, where at every time instance I act according to mu. So I will drop this bar over here and replace mu bar with mu, and in that similar spirit I will write v mu as v mu bar, and so on. So now let's ask this question, how to find mu star. Okay, so several of you asked, in this problem how would I do it, in that problem how would I solve this. Okay, so I'm going to give some assumptions, and as we go along, I will relax these assumptions, and you will see that we will go closer and closer to real world problems. So to begin with, we will presume that the model is known. So when I say the model is known, I mean that the MDP is known. MDP is known means you know the state space, you know the action space, you know the transition probabilities, you know the reward function, you know gamma. You know all these things. Despite that, because this equation is implicit, meaning V star is sitting on both sides, it is still hard to solve at this point. So you will first figure out in this simple scenario how to solve, and additionally I will presume that the state and action spaces are finite, and I will denote the state space by calligraphic S, but its cardinality by the regular S, and similarly A and calligraphic A. Alright. Okay, so before we go ahead finding this optimal policy, I will come up with a slightly different definition of the value function. First, let me tell you why I want to come up with a different definition of a value function. So what we have looked at so far is what is called as the state value function. Okay, state value function means if you give the state, it will tell you if you start from that state and act according to a policy, what is the expected returns you will get. Okay, that is what is called as a state value function. Now if you look at this equation, this is what is called as the Bellman optimality equation, right? You will see these words often now. So this implicit relation that we saw before is what is called as the Bellman optimality equation. And because of this P S prime given SA that sits over here, you can express this summation as an expectation of this quantity. So in other words, V star of S is the max over expectation of a one stage problem. Is this okay? Now notice that the max and expectation appear in a certain order. In particular, the max appears outside the expectation. Now if you have seen law of large numbers and so on and so forth, you know that if you collect multiple data points and average them out, you would be able to get hold of an expectation. Now how would you get hold of max of expectation? Is this okay? So that sort of, is challenging. More formally, since the maximization lies outside the expectation, eventually when we want to work with sample-based optimization techniques, solving this equation is going to be a bit challenging. Okay, that is one reason. The other reason for moving on from state value function is that even if we somehow manage to figure out what V star is, right? From V star, knowing what mu star is, that requires us to solve this equation, and this equation requires the knowledge of P. Okay, so these are like two broad reasons why we want to move away from state value function. And the alternative is what is called as the state action value function, or more succinctly as the Q value function. So what is the definition of the Q value function? So here I have a policy, and recall as per our notation, this is a stationary policy, mu, 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 mu. So this is Q mu bar in our previous notation. Now Q mu actually is a vector that sits in a SA dimensional space. V mu used to sit in a S dimensional space. Q mu now sits in a SA dimensional space, and the little s, little ath coordinate of this is defined in the following way. Now if you go back to the V mu definition, it also had a similar prescription. It was some expectation of some infinite discounted sum. The difference lies in what is the conditioning. So in the state value function description, you only condition on the initial state, which means that the first action, that is the action A0, that was also chosen according to your policy mu. Is this okay? In contrast, in the Q mu setting, right, you first fix the initial state action. Okay, this action, okay, need not be chosen according to mu. You pick an arbitrary action, you pick an arbitrary state, and then you interact with the environment from that point onwards with your policy mu. So A0 is arbitrary, but A1, A2, A3 and so on, they are all chosen according to mu, and this expectation is with respect to that. So you have the same quantity whose expectation we are computing, but the conditioning is different. I'll just finish this point. Right, and one can see that, even though we have this different definition, Q mu and V mu have some very nice relations between them. In particular, your Q mu, okay, equals this expectation, and your V mu is actually the expectation of Q mu with respect to mu, which means that if you chose this action according to your policy mu, and if you take the average of Q mu with respect to mu, then this sum would actually equal V mu S. In other words, your state value function at state S is the average of your Q value function, okay, when the averaging is done according to the policy. Does this make sense? So there are some nice relations between Q mu and V mu. Yes, what is your question?
Sir, can't we think before taking any action?
What does that mean?
So basically you have 2-3 steps.
Yeah.
We'll think, okay, if I take this step.
So again, it's not clear what do you mean 2-3 states. Is this okay? You start with a state, right? You interact and you get the next state. So are you saying that there are multiple initial states? Is that what you have?
So you mentioned our model has multiple states in action. So our algorithm knows what all are the states we have.
Okay.
So assume we are at the ST and we need to go to ST plus 1, but we don't know what is the ST plus 1, but we know all ST plus 1. can't we think before taking any decision?
I mean, see, the problem is that, let's say you know ST plus, I mean, you know all possibilities for the next state, you know all possibilities for the current state, right? Now you have to decide which action to take. How will you decide that? That is the question we are solving. Do you agree? How do we decide that? Exactly, that is the question we are solving. Okay, all right. So now the nice thing about working with Q value functions is that if mu star is an optimal policy in the language of state value function, it will continue to be an optimal policy in the Q value function language as well. By that I mean, if mu star is an optimal policy in the state value function definition, then Q mu star will also satisfy this relation in that Q mu star SA is bigger than Q mu SA for all mu and all SA, right? And as we argued out, that is the reasoning that one used to figure that Bellman optimality equation, that reasoning I sort of hand waved, but if you go through the description of how you end up with the Bellman optimality equation, if you use the same reasoning, this time you will come up with an equation like this. Now notice that here the expectation and max are swapped. Is this okay? In the V situation, the max and expectation appeared in that order, whereas in the Q setting, the expectation comes outside the max, and because this expectation is outside the max, it is more convenient in the sample-based optimization setting. Okay, so that is the reason. So just to summarize, state value functions are sitting in smaller dimensional spaces. However, the ordering of the max and expectation makes it inconvenient to use sample-based optimization there. These Q values sit in a higher dimensional space. However, it enables sample-based optimization techniques to figure what this Q star is, which we will soon see later. Yes? So of course, this S prime is what is the random variable here, so you can actually pull this outside as well. You are right. Okay? So you can, I will not have time to go over that description, but if you go through the arguments of how you arrive at the Bellman optimality equation, if you go through those arguments, you will see that this is what will happen. Okay? And one short answer could be, see here, your Q star will satisfy some relation where you have V star over here, and the V star will have a max. Is this okay? So if you sort of use the V star max connection, you will be able to see that that max will come over here. Yes? I will discuss that later. At this point, I'm just saying that this is convenient for sample-based optimization. When we come over there, we will discuss all those things. Okay? So at this point, I'm just saying that we need to work with Q value functions. And the other nice thing about working with Q value functions is that if you somehow manage to figure out Q star, by looking at a greedy policy with respect to Q star, you will know what the optimal policy is. So what do I mean by a greedy policy? Q star is a vector, right? It sits in a SA dimensional space. You take one state, little s, look at the value of Q star for different actions now. Q star SA for different A's. You pick that action for which Q star SA is the largest, and that is the action you have to use at state S. So that is what do I mean by being greedy with respect to Q star. Okay, so to summarize, Q star is easy to work with in the sample-based setting, and the other advantage of working with Q star is that once you know Q star, just taking a greedy policy with respect to Q star will give you the optimal policy. Notice that you don't need knowledge of P here. Is this okay? That is the main reason that a greedy policy with respect to Q star will give us the optimal policy. All right. So I'm going to define a few operators now. So in particular, if you look at this equation and this equation, so notice that whatever is over here and whatever is over here, I'm going to use them to define some operators. Is this okay? So in particular, I will define what is called as a Bellman operator in the following way. So this Bellman operator takes as input something in the SA dimensional space and spits out another vector which also lives in the SA dimensional space. Is this okay? So you take X, apply T mu on that. This quantity lives in the SA dimensional space, and the SAth coordinate of the output is defined in the following way. Is this okay? The SAth coordinate is defined in the following way, and this expression is precisely what you have in the definition of Q mu. So one can see that if you define your T mu in this fashion, then Q mu will be a fixed point of T mu. By fixed point I mean if you give q mu as input to t mu, the output will be q mu again. So this Bellman operator is defined so that q mu becomes a fixed point of t mu. Okay, are you with me? So in general, if you give x as input to t mu x will not be equal to x. But in the special case of q mu being given as input to t mu, the output will match the input. In that sense, q mu will be a fixed point of t mu. In the same way, we define t, and the difference between this and this operation is that here a prime is chosen according to mu, whereas here a prime is chosen to be the one that maximizes this quantity. Is this okay? So that's the difference between the t and t mu operators. And again, t is an operator which is taking something in the SA dimensional space and splits something in the SA dimensional space. And one can again see that your q star vector will be a fixed point to the t operator. Is this okay? So this is what I have summarized over here. The nice things about this t mu and t is that q mu and q star are fixed points of these operators respectively. Moreover, these operators are what are called as contractions. By contractions, I mean if you give two inputs x and y, then the distance between the outputs is less than gamma times the distance between the inputs, right? And this is in the L infinity notion, right? So what this means is that the distance between the outputs will be less than the distance between the inputs. And since this gamma is strictly less than 1, the distance will actually be strictly smaller. Is this okay? And here we have a similar interpretation, but this time the contraction is defined on the t operator. Okay? And moreover, I mean, there are some other nice properties that these operators satisfy. In particular, they satisfy what is called as the monotonicity property. What it implies is that if x and y are two inputs which satisfy this relation. So let's spend a couple of seconds here. This is a vector, this is a vector. When I write this inequality, I mean it's a coordinate-wise inequality. Is this okay? So x greater than y means that every coordinate of x is bigger than every coordinate of y. And if you apply these operators, one can show that the outputs would also respect this monotonicity. Is this okay? Both t mu and t will respect this monotonicity. All right. So now we are ready to figure out what your optimal policy should be in the model-based setting, right? So we are in the finite state action model-based setting. We know P, hence we know these different operators, right? So the definition of T involves knowledge of P. I hope you can see that. The definition of T involves knowledge of P. So given the knowledge of the model, the first algorithm that we will discuss to figure out mu star is what is called as value iteration. Is this okay? Now recall that to find mu star, it suffices to find q star. Why does it suffice to find q star? Because once you know q star, the policy that is greedy with respect to q star is the optimal policy. So I hope you agree that if I somehow figure out q star, I'm done. Now I know that q star is the fixed point of operator t, which is the Bellman optimality operator, and moreover, t is a contraction. So if you have some knowledge of these concepts, you will be able to cook up this algorithm as the natural algorithm. So what you do over here is, you start with some arbitrary guess q0, and you apply t repeatedly. Is this okay? So you start at q0, apply t once, you will get q1. Once you get q1, right, you again apply t, you get q2. Once you get q2, you again apply t, you get q3, and you keep doing this. Is this okay? Right, and you know, maybe at some point you get bored. By that I mean maybe the iterates are not changing by a big margin. Right, at that point in time you stop, and whatever is the terminal qt, you take the policy that is greedy with respect to that and declare that to be an estimate of the optimal policy. So here is an illustrative example. So this is the MDP with which we started out, but it is very complicated. So what I'll do is I'll simplify that first so that we can discuss it in class. So here there are 3 states. I now label them as S1, S2 and S3, and I have now reduced the number of actions as well. Now I have only 2 actions, study and maybe use phone. Right? So if you are in a sleepy state and take the action of study, with probability 1, you will remain in the sleepy state. Okay? But and you will get a reward of +4. Okay? On the other hand, if you take the action of, maybe scrolling through your phone, right, with probability 1, you will move to an alert setting, right, but you will not get any reward over here. Is this okay? With probability 1, you will move over here. And here, if you decide to study, with probability 1, you will move to a sleepy state, but you will get a higher reward over here, right? So you can see that you get +10 because you are studying in an alert situation. But when you are alert and you used your mobile phone, then you sort of crash out. Okay, so I've sort of cooked up some scenario. So this is the scenario. Now, the question that we want to decide is, when you are in a sleepy situation, okay, should you watch your phone or should you study? That is the kind of question that we want to figure out. Okay, now this is what is the optimal policy that we want to figure out, and the goal is, can we use value iteration to figure out this optimal strategy? Okay, so here is the MDP on the side, and we are going to start with this initialization. So observe that S is 3, 1, 2, 3. The number of actions is 2, study or use your phone, and I'll use L to denote the action concerning study, right? And there are 3 actions, 2 states, so the product SA is 6. So your Q vectors sit in a 6-dimensional space, okay? And for simplicity, I will presume gamma is 0.9. Okay, so I start with some arbitrary initialization. So there are 2 numbers in red, 2 in green, and 2 in black. So these 2 numbers correspond to the value associated with this state for the different action. So for example, this is Q0 of S1L. Okay, this number over here is Q0 of S1P. Similarly, this is Q0 of S2L, Q0 of S2P, and so on. Is this okay? So here, I have not indicated the actions, but the way to interpret is, once you reach this state, whatever action you pick, with probability 1, you will come back to the same state and you will get 0 reward. Is this okay? That's the interpretation you want to take in. So now let's apply value iteration. So you start at Q0, you have to apply T. Okay? So the description of T means that Q1 of SA will equal this quantity over here. Okay, so let's try to compute Q1 of S1L. So you are at S1 and you want to know what is the value of Q1 S1L. So according to this rule, you have to ask, if I take the learn action, okay, where will I end up in? So in this simplified scenario, if you take the learn action with probability 1, you will remain in the sleepy state. But you will get an immediate reward of +4. So you see that here, although there is expectation over all all possibilities for next states, in this simple scenario, the next state is only S1. So that's why I don't have an expectation here. Instead, I have 4, which is the immediate reward, plus gamma, which is 0.9, times max over the different values for the different actions at the state at which I end up in. So if I take L action at this state, I end up here. So that's why I have S1 and S1 here. And I take the max over Q0 S1L and Q0 S1P. Is this okay? Now since these 2 values are 0, the max of 0 is 0. So 0.9 into 0 is 0. So 4 plus this is 4. And that's how I end up with 4 over here. So you can repeat this calculation for different state action pairs and you will end up over here. Okay, now let's pause over here and let's ask, if I had Q1 as my estimate of Q star, what would be my optimal strategy? So how do I decide the optimal strategy? I look at the Q values and look at the greedy policy with respect to that. So here is the Q values for the state S1, and it says that if I study, I will get a return of 4, right? And if I use mobile, I'll get a reward of 0. So this estimate tells that the optimal policy should be at state S1, you should study. So even though you are sleepy, it suggests you should study. Okay, so this is the initial iteration. Now let's do one more round of this iteration, right? So again, I apply the same rule. This time I use Q1 to compute Q2. Is this okay? So now when I do this computation, I end up with this vector. Now here you can see that the ordering has now changed. Is this okay? So after doing this computation one more time, you can see that the ordering has changed. And now if you take the greedy policy with respect to this estimate, I hope you agree that it suggests at state S1, okay, it may actually be better to use your mobile phone so that you go to a alert state, and at the alert state you should study. Okay, at the alert state don't use your phone, right? So this seems reasonable. So you can see that in just 2 iterations I have an estimate, okay, from which if I look at the greedy policy, I have an optimal strategy, right? Now I can, run more iterations of my value iteration, and this will be my Q3, this will be my Q4, I can keep doing it, and one can show that eventually it will settle at this vector, which is the Q star vector, right? So although these values are very far away from this, observe that even though we are far, the ordering is correct. Are you with me? This is very important. Even though these Q estimates are very far away from Q star, the ordering is correct. By that I mean this value is bigger than this value, and in the Q star setting as well, this value is bigger than this value. Okay? So even though I only have a rough estimate of Q star, if I get the ordering right, I have a hope that I can get hold of the optimal policy. Is this okay? So whole of reinforcement learning actually works on this thing. I may require lot of samples to get a very good estimate of Q star, but to know the optimal policy, perhaps I may not need a very good estimate of Q star. What I need is the ordering. I hope this is clear. Okay? So I hope this example is illustrating that fact, and one can see that Q star will actually satisfy this Bellman optimality equation. In other words, Q star will be the fixed point of your T operator. Okay? All right. So this is an illustration of this value iteration. Now let's move on to other dynamic programming approaches. So there is value iteration. Then there are some other ideas such as policy iteration, and keep track of these years over here. This policy iteration actually came in the late 1950s, right? So the idea in policy iteration is that you start with some initial policy, not Q0. You start with some initial policy, mu0. And then you repeatedly do these two things. What do? Whatever is your current policy, you try to find the Q value of that policy. So if your policy is mu0, you try to find Q mu0. So now you may ask, how do I find Q mu0? Well, you have to solve that fixed point equation, and one can show that the fixed point equation associated with the fixed policy is actually solving a linear system of equations. Okay? The fixed point associated with the T operator, okay, that is solving a nonlinear equation, but for a fixed policy, solving or finding the fixed point of T mu is actually solving a linear system of equations. The only challenge is that this system of equations sits in a SA dimensional space. So it's like linear system of equations, but this is sitting in a very large dimensional space. Okay? All right. So what is the idea here? You start with mu0, find Q mu0, and then what you do is you come up with a new policy which is greedy with respect to Q mu0. Mu0, Q mu0, mu1 greedy with respect to Q mu0, and then you compute Q mu1, and then you find a policy mu2 that is greedy with respect to Q mu1, and you keep repeating this process. And one can show that this algorithm will actually terminate in finitely many steps. Although this number of steps could be very large, it will terminate in finitely many steps. And whenever it terminates, whatever is the final policy, you declare that to be the optimal policy. And one can show that that will actually be an optimal policy. And then there is a variant of policy iteration called as conservative policy iteration. And again, notice that this idea actually came 25 years back by Shyam Kakade and John Langford. Right? The difference between policy iteration and conservative policy iteration lies in how you do your update, policy update. So you start with an initial policy. In the policy evaluation step, you figure out how good this strategy is. Figuring out how good this strategy is equivalent to finding Q mu0. Now, from Q mu0, instead of taking your new policy to be fully greedy with respect to Q mu0, what you do is you try to take a convex combination of the greedy policy with respect to Q mu0 and your current policy. Is this okay? You take it to be a combination between the current policy and the fully greedy policy. So in other words, you try to sit between the current policy and the fully greedy policy. So now one may ask, why are you wanting to do that and so on? Well, one can show that by being partially greedy in this sense, one can actually maximize this performance difference. Okay, so let's understand what is this performance difference. So Q mu k is a vector. nu is another vector which is of the same dimension. So nu transpose q mu k is a scalar, right? And nu transpose q mu k plus 1 alpha, this is the q value of this policy, and you look at a scalar where the averaging is done with respect to the same nu. Okay, so the way is, you look at the q value functions, look at the average of that q value function, and the average is taken with respect to some suitably defined weight vector on the state action space. For example, you may prefer some state actions over other state actions, so you give more weights on certain state actions. So in that way, you come up with a initial state action distribution, right? And that you use to look at an average, and this difference between the scalar quantities is what you want to maximize. And one can show that by being between the full greedy and the current policy sometimes helps in maximizing this per step performance gap. Okay, so I'm being very careful. I'm only saying it can perform better on a per step basis, right? Going fully greedy may not give you as much improvement on a per step basis, okay, compared to going partially greedy. Okay, and the idea in this paper is you take this difference. This difference is actually not this is like a nonlinear function. So what you do is you come up with a quadratic approximation to this function, right, which is actually a lower bound to this, and that will be a quadratic in alpha, which is a scalar. You maximize that alpha, that function, and whatever alpha you get, you use that alpha to decide what your next policy could be. Okay, and you keep doing this. All right. So now the question is, what are known about these different methods? So here is a quick summary, right? So here is value iteration, policy iteration, conservative policy iteration. I would like to highlight that all these are different methods in the model-based setting, meaning we know the transition probabilities, hence you know the definitions of the different operators, right? When you know the definitions of these different operators, you can actually run these algorithms, and the properties of these algorithms include the following. The first thing about value iteration is that of monotonicity, which means that if your Q0 is chosen such that it satisfies some initial condition like this, then your Q0, Q1, Q2 will monotonically get better. Okay, and again these are vectors over here, so the inequality here is coordinate wise, and because you are trying to find the fixed point of a contraction and you are using the fixed point iteration, one can show that the distance between Qt and Q star actually decays exponentially fast, okay, depending on the discount factor gamma. Is this okay? So this is something that we can show. Now with regards to policy iteration, we get a different notion of monotonicity. Here observe that the Q0, Q1, Q2, they monotonically get better. In policy iteration, in contrast, your Q mu1 is better than Q mu0. Okay, Q mu1 is how good is your policy mu1. There is no interpretation of Q1, Q2 here. These are all estimates of Q star. Here on the other hand, Q mu1 is an estimate of how good mu1 is. And in policy iteration, one can guarantee that the next policy that you get, okay, will be probably be better than your previous policy. And notice that in value iteration, you don't have any intermediate policies, right? I mean, whatever you do, perhaps you may try to cook up the intermediate greedy policy with respect to this, right? And it is possible that you may get different greedy policies, but they may not have such monotonicity properties. Is this okay? You may start better, you get a different greedy policy. That greedy policy need not be better than the previous greedy policy in the value iteration setting, but in the policy iteration setting, one can guarantee this monotonicity, and one can show that policy iteration actually is a Newton step to find the zero of this fixed point error, right? Which means that when you are very close to Q star, this policy iteration algorithm will give very fast convergence. Is this okay? And then there is this conservative policy iteration. Here again, one has a notion of monotonicity, but this monotonicity in this average Q value sense, right? These are scalars, and the average actually gets better. It's not like Q mu1 is better than Q mu0, Q mu2 is better than Q mu1. It's not that. Instead, the average of Q mu0 with respect to nu, the average of Q mu1 with respect to nu, these scalars actually get better, and one can actually show that the convergence rates in the conservative policy iteration is actually order 1 over k. So compare this inverse polynomial convergence rate with this exponential convergence rate. So keep these things in mind, and we will discuss them later on. All right. So far we were in the model based setting, And now we would like to move to model-free settings. Okay, so here the assumption is slightly relaxed in that we presume the state space, action space, and possibly reward and the discount factor, these things are known, but the transition probabilities are unknown. Instead, the agent can interact with the environment using different strategies to get experience samples. I hope the difference is clear. In the model-based setting, you don't interact with the environment because you know the transition probabilities. Now that you know the transition probabilities, you know your Bellman operators, and you can play around with these Bellman operators to get some estimate of Q star or the optimal policy mu star. Now we are in a different setting where we don't have access to P, hence even if we wanted to do a Bellman operator operation, we won't be able to do because we don't know P. Are you with me? So now we have to collect data by interacting with this environment and use this data to figure out what your Q star or mu star should be. I hope the goal is now clear. Okay? So what we will do is, we'll first start with a simple version of the problem, which is that of policy evaluation. So what does policy evaluation mean? You have been given a policy, you want to know how good that policy is. You want to quantify it. So whenever I say quantify how good a policy is, it basically means you want to compute Q mu. Is this okay? When I say evaluate a policy, it means compute Q mu. Now the challenge is, we don't know P. The transition probabilities are unknown. So the question is, without knowing transition probabilities, can you compute Q mu or not? In other words, can you use the data to compute Q mu? Okay, so towards that, one of the most popular algorithms is what is called as the temporal difference learning, right? And you can find the details in this Sutton and Bartow book, right? And the algorithm goes as follows. So you start with some initial estimate Q0 and some initial state action S0, A0. So notice that I only have one state and one action. Is this okay? Now, as soon as I start at this state and take this action, I would get to see the immediate reward, and the environment will now make a transition to the next state. So I start at S0, A0, I got R S0, A0, and I now get to see S1. Right? And now what I do is, I take action A1, I think there is a typo here, this should be Sn plus 1. So I take action An plus 1 according to the policy whose value I want to estimate. Okay, so mu is some policy that is given to me, right? And I want to know how good it is. So I use that policy to interact with the environment and pick a sample action according to that policy, right? So this action will influence my next state. I hope it is clear to you. Okay, there is a typo here. This should be Sn plus 1 and not Sn. Okay, so now that I have Sn, An, Sn plus 1 and An plus 1, I run this update rule over here, right? So what is this update rule? Qn plus 1 is Qn. Notice that these are all SA dimensional vectors plus some step size times some square bracket, which is a scalar, times a vector. Okay, so let's just understand the notation. This is a vector sitting in an SA dimensional space where all coordinates are 0 except the Sn, An coordinate. Okay, so this is the standard basis sitting at Sn, An. So this is a vector and this is a scalar. So what is this scalar? This is the reward that you observe plus gamma times the value of Qt at the next state action pair minus the value of, sorry, this should be Qn here. So Qn of next state action pair minus Qn of current state action pair. Okay, so you do this, right? And you run this algorithm. Okay, so let's go over this algorithm and let's try to understand why this is referred to as a model-free algorithm. Do you see any P sitting here in the algorithm? No. The role of P is over here. So the interpretation over here is you interact with the environment, get hold of the state. Okay, so it's like, you play the game of chess with a computer engine, right? You start at a state, you make an action, and you get to see the next configuration. Is this okay? So you don't know how the chess engine is playing, but you get to see the next state. So this is a scenario where you don't know P, but you can interact with the environment and figure out what the next state is. Is this okay? So you can see that you are using your samples and running your algorithm. Yes. So right now there is no greedy or anything like that. I mean, this mu is some given policy. So this is policy evaluation, meaning I give you a policy and the question is, what is Q mu? I'm not interested in finding out the optimal policy over here. I only want to know what is Q mu given mu. That is the question. Okay? All right. So now the question is, okay, how does one come up with an update rule like this? Okay, that is the question that I would now like to discuss, so that tomorrow, if you want to design your own RL algorithms, perhaps you can do something like this. Okay? And the short answer is, okay, there is no fixed recipe to come with these algorithms. At some level, it's more art than science. Is this okay? The idea is you have to do lots of trial and error and maybe somehow figure out, okay, maybe something is like this is what needs to be done. I mean, if you have worked with actually machine learning scientists and researchers, you would have experienced this, okay? They will say, oh, do this, do this, do this, okay, maybe it will work, okay, let's try this, and suddenly it will start working. And if you ask them, why are you doing it? You know, do you have some, reason? Do you have some, theoretical understanding, intuition of why you are doing? They will say, look, it works, and things like that. Is this okay? And I have had an opportunity and privilege to, work with such people, and I have always been, surprised. Wow, you could come up with some ideas like this in this fashion. So I'll try to give a glimpse of how you could come up with the TD learning algorithm. So this algorithm is one of the most popular algorithms. Now I'm going to give you a glimpse of how you could have gone about coming up with this algorithm. Okay? So I want to find Q mu. So the first thing I do is I define some objective function. Okay? So at a high level, everybody wants to come up with an objective function, try to do gradient descent with that objective function. Is this okay? So that's the idea. So you cook up some function like this, right? One can see that this is the distance between Q and Q mu, and the distance is measured with respect to some diagonal matrix. There is some technical description. Let's not worry about it. So this is some distance between Q and Q mu. Okay? And you can see that this distance will be minimized when Q equals Q mu. Do you agree with this? This distance is minimized when Q equals Q mu. So let's see if we can do gradient descent with respect to this objective. Is this okay? First, keep in mind that this objective involves Q mu, which is the quantity that we want to estimate. Is this okay? Machine learning people will not think like this. They will say, let's begin here, let's see where it takes us. Okay? So let's take this objective function and let's see if we can do gradient descent. So if you try to write a gradient descent algorithm, you would end up with something like this. So Qn plus 1 is Qn plus some step size times some diagonal matrix times Q mu minus Qn. Okay, so this is the negative of the gradient, and since we want to do gradient descent, you will end up with some update rule like this. So now let's ask, can we do this update rule or not? The problem here is that there is d mu, which actually corresponds to some stationary distribution of some Markov chain induced by some policy mu and so on and so forth. So the thing is, we don't know d mu. Okay, we can estimate d mu, but we don't know d mu. Okay, and the other problematic thing is we have Q mu here. So of course we cannot run this algorithm. Why we cannot run this algorithm? Because Q mu is the quantity which we are interested in estimating. So this algorithm we cannot run. So then if you put on a machine learning engineer's hat, you would say, okay, I don't know Q mu. Can I come up with an estimate of Q mu? Is this okay? So then you ask, okay, what is an estimate of Q mu? Okay, Qn is an estimate of Q mu. Can I substitute Qn instead of Q mu? But if I substitute Qn instead of Q mu, what will happen? This will be 0. So you realize, okay, this is not a good idea. So let's see if I can do something. In particular, let's see if I can come up with some alternative representations for Q mu. So now I know that Q mu is a fixed point of T mu. In particular, Q mu is T mu Q mu, right? And if you expand using the definition of T mu, you will see that Q mu has this expansion. So this is like an immediate reward plus the Q value at the next state. Okay, where this P mu is actually an SA cross SA matrix which has some description like this. Okay, all right. So now what we do is, wherever there was Q mu, I replace it with T mu Q mu, right? And this T mu has this expansion, so I write it this way, right? Now what do I see? I see Q mu again. There is P mu, there is D mu. So again it looks a bit uncomfortable. How do I run this algorithm? I don't know Q mu. But now you would say, look, I know an estimate of Q mu, which is Qn. So let me just plug that thing over here. and I end up with this update rule. Is this okay? Right? So you come up with this update rule. There is d mu, p mu, and there is no q mu here. So this is an update rule that at some level you can start running, and then you realize that this d mu, p mu can be written down as an expectation. So once you can write something as an expectation, you try to get a sample, okay, whose expectation is this quantity. Is this okay? So you start with gradient descent, do some approximations, end up with this algorithm. Now one would be able to show that this update rule cannot be expressed as the gradient descent of any objective function. Let me again elaborate. You start with this objective, you write down the gradient descent, do some manipulations, end up with some update rule like this, and one can show that you cannot come up with any objective function whose gradient descent will have this description. But nevertheless, one can run this algorithm. So if you put a machine learner's hat, you will say, let's run this algorithm and let's see if it works, and you will see that it actually works. And then as a theoretician, you start, can we somehow try to understand why does this algorithm work? Okay, so this is what is called as the TD learning algorithm, right? And now if you asked, why does this algorithm work? Maybe I'll go ahead because I'm running out of time. Maybe at the end of the class, I'll take questions, right? So now if you ask, can you give some intuition of why does this algorithm work? So notice that here there is no d mu, no p mu. I hope you can see that. So we actually take a sample whose expectation looks like this. Is this okay? So that's a sample-based implementation of that algorithm, and this is what is called as the TD learning algorithm. So now let me elaborate what does TD learning, why do we call this TD learning? We call this TD learning because of the quantity that is sitting over here. This is, there is a typo here. This should be Qn of Snan. So this is like an estimate of Q mu. This is another estimate of Q mu. Is this okay? This is an estimate of Q mu. This is another estimate of Q mu. So you are looking at two different estimates of Q mu, comparing them and deciding whether I should update my Qn or not. Okay, so that's what temporal difference means. Temporal means time. So you look at two different estimates of Q mu. One is your current estimate and the other is your estimate based on the new information that becomes available to me. So you look at two different estimates of Q mu and compare them, right? And then use that to decide how to update your Qn. Is this okay? So this is what is called as bootstrapping. You are using Qn itself to update the estimate of Qn. Is this okay? This is what is called as bootstrapping, right? So this is your TD learning algorithm, and one can show that if you use something called as stochastic approximation theory. So let me maybe add a few words here. Recall that I said this algorithm cannot be written as a stochastic gradient descent. It cannot be written because we did some approximations in between, because of which the gradient nature was lost. So you cannot restrict yourself to stochastic gradient descent theory to study the behavior of such algorithms. You will have to go beyond to what is called as stochastic approximation theory, right? And use that theory to understand the behavior of this algorithm. In particular, one can show that if the step sizes decay sufficiently fast, then the iterates of this algorithm asymptotically will track solution trajectories of this deterministic ODE. Okay, so here everything is deterministic. While this ODE is unknown, okay, you know the structure of that ODE, and because you know the structure of that ODE, you can say something about that ODE. Are you with me? It's not that the ODE is known, but I know the structure of that ODE. Okay, and one can show that this ODE, okay, has Q mu as its globally asymptotically stable equilibrium. Meaning if you take any solution trajectory of the ODE, it will actually eventually go to Q mu. And what this stochastic approximation theory tells us is that this iterates, right, will eventually track the solution trajectories of this ODE, and the solution trajectory of this ODE go to Q mu, hence these Qn's also need to go to Q mu. Now keep something in mind. This is a deterministic ordinary differential equation. This is a stochastic algorithm. This is stochastic because these Sn, An, Sn plus 1, An plus 1, these are obtained by sampling or interacting with the environment, which means that each time you run this algorithm, the trajectory, the experience trajectory that you will see will be different. Is this okay? But what this result says is that on almost all these runs, eventually you will get an estimate of Q mu. It is something in spirit of your law of large numbers, right? Each time you do this law of large numbers experiment, the samples that you will get will be different, but eventually if you do this averaging, you will get hold of the mean of the distribution from which these random variables are coming. So each time you repeat the experiment, the samples are going to be different, but eventually the estimate of mu is going to be reasonable. Okay, that's roughly the spirit of this idea over here. So now we can go beyond and ask, can we use a similar recipe to compute Q star directly? Right? So far we focused on the case of finding Q mu, which means given a policy, how good is that policy? That's the question we asked. Now we say, okay, who cares about how good is my policy? I want to know the best policy. So now the question is, can I find the best policy itself? So if you use this similar hand-wavy, style of coming up with an algorithm, you would see that you will eventually end up with an update rule like this. The difference between this update rule and the previous update rule rests on the fact that there is a maximization over here. Previously, this was an plus 1, and an plus 1 was chosen from some behavior policy. Here you don't have an plus 1. Instead, you pick the action which maximizes. I think there is a typo here again. This should be Qn. So you pick an action which maximizes this expression over A prime. So this is the difference between this TD learning algorithm and the TD learning for policy evaluation. But the philosophy is the same, right? And here you notice that the action that you pick, okay, is based on some evolving policy, right? And whatever is your an plus 1 will influence which coordinate of Qn you update at the next interaction. Is this okay? So you notice that because of this Esn an, only one coordinate of Qn is updated at every time instance, right? And which coordinate is updated depends on the state action that you observe. So the action that you observe, okay, is based on a policy with which you interact. Now here in this algorithm, I'm not telling you how to pick this mu n. I'm saying you have some mu n and you pick actions according to that. And now I will tell you how to pick mu n. So some of the popular ways include the following. The first is that of a fixed behavior policy, right? Which means you start with a strategy, right? And you interact with that environment. This strategy could be very far away from the optimal strategy, but this is the strategy with which you interact with the environment. This is what is called as a behavior policy. The behavior policy could be different from your optimal policy, right? So you interact with the behavior policy, fixed behavior policy, but the more popular one is what is called as epsilon greedy, right? So the idea is, if Qn is an estimate of Q star, then the policy that is greedy with respect to Qn, right, that is perhaps an estimate of mu star. Okay, so why don't I already act according to that policy and interact, with the environment using this estimate, right? However, we need to be careful. Sometimes these policies could be very far away from the optimal policy. So if you decide to act greedily according to your Q estimates when they are not reasonable estimates of Q star, there is a chance that the way you are interacting is using a suboptimal policy. So to prevent issues that arise because of this, you often act randomly. Okay, so the way epsilon greedy works is, with probability epsilon, at any time instance you randomly pick an action, and with a large probability 1 minus epsilon, you try to pick an action that is determined by what is greedy with respect to Qn. Does that make sense? That is what epsilon greedy means, right? And this is the idea, and this is how you pick your actions over here, and you run this algorithm in the following fashion, right? So now again one can use stochastic approximation theory for analyzing the convergence of Q learning, and one can show that if your behavior policy ensures that all state actions are visited infinitely often, it's not like your behavior policy is only showing you a bunch of state actions. You should get to see all state actions infinitely often. If you do that, one can show that the Qn iterates actually track the solution trajectories of this ODE, right? Now notice that the difference between this ODE and the previous ODE is that here you have the T operator, whereas in the policy evaluation case, you had the T mu operator. Is this okay? So this is the difference, but nevertheless, one can show that this ODE okay, also has a global Lyapunov function, which implies that the globally asymptotically stable equilibrium point for this ODE is Q star itself, which means any solution trajectory of this ODE will go to Q star, and because your Q learning algorithm that is given over here, okay, tracks the solution trajectories of this, your Qn will actually go to Q star, almost surely. Okay, so here is a model-based way of figuring out what Q star, model-free way of figuring out what Q star is. And since mu star is greedy with respect to Q star, once we find Q star, one can get hold of mu star itself. Okay? Sorry, can you repeat? So this is what is called as the Bellman optimality operator. Okay, this is an operator that I had defined at the beginning of the lecture. Maybe I can, ask you to look at that. Right. So let me quickly summarize what we have done. Right. So we sort of came up with some Q learning algorithm, and the question is Q learning, related to any of these model-based algorithms that we saw? In particular, we saw value iteration, policy iteration, conservative policy iteration. So is Q learning related to any of them? So if you look at this ODE, you see that there is TQT minus QT. So at any point in time, QT is, pushed in the direction that takes it closer to TQT. Are you with me? So this ODE ensures that whatever your QT is, you are pushing it in the direction that takes it closer to TQT. So in other words, at any given point in time, this ODE is trying to close the distance between QT and TQT. And once the distance goes to 0, you have to end up at Q star, because the only fixed point of T is Q star. In other words, the only place where TQ minus Q will be 0 is Q star. So this algorithm is trying to reduce the distance between TQ and Q. And from this interpretation, one can see that Q learning is actually a value-based extension of value iteration. Is this okay? So one can see that in value iteration also, the TQ and Q distance are being reduced because it tries to take you closer and closer to Q star, which means that TQT and QT distance are actually being minimized. So in that sense, one can see that Q learning is a sample-based extension of value iteration. So one can then ask, okay, if we can come up with sample-based extensions of value iteration, can we come up with sample-based extensions of policy iteration? So the answer is yes. There have been several algorithms that have been developed. In particular, they lie within this family called as actor-critic methods. One can then ask, okay, can we extend the conservative policy iteration also to model-free settings? The answer is yes. There is a very popular paper called as Trust Region Policy Optimization by Schulman, right, and others. And that sort of tries to operationalize this conservative policy iteration. So in the setting where the states and actions are finite, right, and we work with these Q vectors. So if you remember these update algorithms, these Q vectors actually sit in a SA dimensional space, right? So this is what is called as tabular learning. Okay, so when you do tabular learning, okay, tabular reinforcement learning, then in those situations, one can actually provide strong convergence and convergence rate guarantees. Is this okay? So let me stop this lecture. Here are the takeaways. Okay, so we discussed Bellman equations, and these Bellman equations characterize optimality. Then we discussed model-based algorithms, and the model-based algorithms basically exploit these properties, right, to figure out the optimal value function and in turn the optimal policy, right? And we discussed dynamic programming, which basically is value iteration, policy iteration, conservative policy iteration, right, where these ideas work when the model is known, right? And knowing this model implies there is some expectation taken with respect to the transition probabilities, right? So when you look at reinforcement learning algorithms, they try to at some level mimic these model-based settings by replacing the expectation with suitable samples. Is this okay? They try to replace the expectations with suitable samples. So that is what I write over here. The reinforcement learning algorithms typically try to take these expectations and replace with samples. We saw one instance of such an algorithm, which is the Q learning algorithm, but there are several algorithms, which try to mimic policy iteration, conservative policy iteration, and so on and so forth, right? And one can show that these TD learning algorithms in the tabular setting converge because these Bellman operators is a contraction. Okay, so now in the next lecture we will ask, okay, if the state and action spaces are very, very large, okay, would we still have such guarantees or not? Okay, so let me stop here. If you have few questions on this this lecture, let me know, and then I will move on to my third lecture. Yes. We know what? So I believe what you are saying is that we know the model for some state actions, but we don't know the model for other state actions. Is that the question? I mean, at the end of the day, we need to know P for all state actions, right? So it's not clear to me how will that be beneficial.
Like for some problem, we know transition probabilities, but other transition probabilities we don't know. Is it possible in real life, and how do we handle that?
I mean, it is possible in real life. Maybe, you know, for certain scenarios, you may be able to figure out if you take this action, maybe this is the next state you will observe and so on. But maybe for more complicated scenarios, you may not be able to figure it out. So for certain, like for example, you know, if in your investments, you invest in, let's say, an FD. Okay, so you have 100 rupees and you decide to put the full 100 rupees in FD. This is an action you are taking, right? You would know after so many years, this is the return you will get. So this is exactly known, right? So these transitions are exactly known, but at the same time, you don't know if you invest in stock markets, what will be the consequence. So there is some uncertainty. So this is an example of a scenario where, you know, the transitions for certain state actions are known, but for other state actions, you don't know. Is this okay? I don't know if this was your question, and does that
like
answer?
How we can handle that scenario?
I mean, I don't know how to handle that scenario because it will depend on how much knowledge we have and, you know, what is unknown. If the unknown quantities are too many, I really don't know how it will help. I have not thought about this question. Perhaps I don't have a good answer to that. Okay? Yeah. So the idea there is you want to come up with better and better policies. That's the idea. You start with mu0, right? You try to find mu1 whose Q value is better than Q mu0, and so on and so forth. So, I mean, it's not like we are trying to solve one equation. It's like you are iteratively trying to get better and better mu's.
No, I'm saying you said actor-critic methods are approximations of
policy iteration.
Yeah.
So the idea would be there is an actor and a critic. The actor tries to do a policy update. The critic tries to evaluate that policy. Okay, so you can recall that in the policy iteration we had two steps. There is a policy evaluation and a policy update. So the critic will try to use your sample-based data to evaluate how good your current policy's Q value is, and based on that the actor will decide, okay, how should I update my policy. So at a high level, this is what an actor-critic algorithm will do. To elaborate a bit more, you will have a you know, inner loop, outer loop algorithm. The inner loop will try to do policy evaluation, which is the critic's job. Once you have a reasonable estimate of your Q mu using your data, the actor will kick in and see how I can take my current policy and build a new policy from that. Is that okay? All right. So maybe I will move on to the third class.
Sir, what is the difference between Qn and Q mu?
Qn is an estimate of Q mu. Does that answer your question? I'm sorry, who asked me that question? Yeah. So Q mu is a vector which exactly quantifies how good your policy mu is. In particular, it's the fixed point of that T mu operator. Qn is an estimate of that. Is this okay? So when you do optimization algorithms, there is an X star, right, which is perhaps if you have a convex problem, it's the minima over there, right, and your Xn that you get by gradient descent will be an estimate of X star. So Q mu is that X star and Qn is my current estimate of Q mu.
Essentially, we are trying to bring it together, and
yeah, we are hoping that Qn goes to Q mu. Is this okay? So maybe I'll take other questions after the third class. Otherwise, you know, I will not be able to finish in time before the lunch. All right. So now we move on to the third part of this tutorial, right? So far, we were in the setting where the state and actions are finite. Is this okay? So state and actions are finite, and we are able to work with quantities that live in this SA dimensional space. Right? Now we move to the third part of the talk where we will talk about function approximation and deep reinforcement learning. Is this okay? So let's try to understand first the motivation for function approximation and then look at deep reinforcement learning. So I would like to highlight that this is joint work with my colleague Professor Aditya Gopalan, who is also a faculty at the EC department in the Indian Institute of Science. So let's do a quick recap of what we have done so far, right? So what is RL? We have an agent that interacts with the environment. The environment is typically modeled as a Markov decision process. A Markov decision process is characterized by these 5 things. The goal in reinforcement learning is to find a policy mu whose Q value is the largest. Is this okay? So you can see that I am giving different more technical description of what reinforcement learning is. So at a technical level, the goal in reinforcement learning is to find a policy mu which maximizes Q mu. And the challenge in reinforcement learning is that the transition probabilities are unknown and the state actions are large. So in the last half, the second half of the previous lecture, we dealt with this scenario. Is this okay? So we came up with these TD learning algorithms, for example, to deal with the scenario where P is unknown. In this lecture, we want to focus on the scenario where the state and action spaces are very, very large, which is more often the case in practical applications. So what do we do over there? And here are the different Bellman operators that we had defined previously, and we will repeatedly use them in this lecture as well. So here is what we discussed in the previous lecture. Okay, we discussed model-based algorithms. So what does model-based algorithms mean? These are algorithms to find your optimal value function and the optimal policy when the model is known. Is this okay? In this setting, we discussed value iteration, which repeatedly applies T. This operation is known as the Bellman backup, okay, in reinforcement learning parlance. Okay, in policy iteration, you try to do a policy evaluation and a policy update. So you start with a policy, you find its Q value function, then you update the policy, setting it to be the one that is greedy with respect to your Q value function. And you keep doing this, right? And in the conservative policy iteration idea, you modify how you do the policy update. Instead of being full greedy, you try to sit between the current policy and the full greedy policy. Okay? And one saw that in the model-based settings, one can actually prove very strong convergence and convergence rates for these different algorithms, right? And then we looked at the case of model-free settings, which is that of when this transition dynamics is unknown, right? So when the state actions are finite, here we actually took inspiration from these different algorithms and came up with sample-based versions of these algorithms. Okay, in particular, we discussed Q-learning, which is value iteration with samples. Similarly, I mentioned actor-critic methods, which is policy iteration with samples. Then I also mentioned TRPO, which tries to operationalize CPI. Again, in tabular settings, one can show very strong convergence and convergence rate guarantees for all these methods. Okay, so while we can do all these things in the setting where the state actions are finite, which is formally known as the tabular settings, okay, those are not the challenging scenarios. The challenging scenarios is when the state actions are very large, right? When the state actions are very large, you have to do some approximation, and that is what is called as function approximation. Is this okay? So the first thing what we will do is we will go back to the model-based setting. Okay, so now we want to discuss model-based with function approximation, and let's see, at least in that scenario, is life good? Because if in the model-based setting with function approximation, life is good, then there is hope that we may be able to replace suitable expectations with samples and cook up model-free algorithms for as variants of those model-based algorithms. Okay, so that's why I'm talking about dynamic programming with function approximation. And here is the motivation for looking at function approximation. So in real-world settings, the action and state spaces typically will be very large. For example, in control problems and robotics, typically the state and actions will be infinite. Like I have a robo, I have to move this hand. I can move anywhere in between this position and this position. So you can see that it's a continuous action space, right? On the other hand, in certain games and LLMs, while the state and actions could be finite, they could be very large. An example of this is chess, right? So even though chess for chess the states and actions are finite, they are just too many. Is this okay? So while on paper you can indeed run the tabular Q-learning algorithm, okay, to find Q star, the challenge would be that if you run this algorithm, it is going to take forever to figure out what Q star is, and in particular give an reasonable estimate of mu star. Is this okay? That is where the challenge is, right? And you know, in technical language, the issue of large state actions is that, right, we won't be able to get reasonable estimates of TQK, which is what is used in value iteration, right, or Q mu K, which is used in policy iteration and conservative policy iteration. Let me elaborate a bit. Qk is a vector that sits in your SA dimensional space, right? TQk is the output of Qk when T is applied to it, and TQk also sits in a SA dimensional space. And recall that value iteration starts at Qk, applies T to it, and gives you Qk plus 1. Now you may ask, okay, maybe I won't be able to get TQk, but can I get a close estimate of TQk? But if TQk itself sits in a big dimensional space, getting a good approximation to TQk is going to be challenging. Similarly, when you try to do policy iteration and conservative policy iteration, where the policy updates are based on getting good estimates of Q mu k. But these Q mu k's sit in a SA dimensional space, which is very, very large. So again, the question is, in this very, very large space, can I get hold of a reasonable estimate of Q mu k or not? That is the question. And towards that, we come up with function approximation. In particular, we will work with what is called as value function approximation. There is also something called as policy approximation, wherein you try to, you know, approximate the policies as well, right? But in this talk, we will only focus on value function approximation, but policy approximation is also an important thing, but that is something perhaps you can, you know, look it up on your own. So what does value function approximation mean? As I said, you know, these TQ vectors and Q mu vectors play a very central role in value iteration, policy iteration, conservative policy iteration, and we want to approximate them. So the idea is, you start with a class of functions. Okay, these functions could either come from, you know, by using some matrix and looking at the column space of that matrix, or working with a neural network. So neural network means you have an architecture, and that architecture, by choosing different weights and, you know, biases, you will be able to get different functions. So the neural network architecture characterizes a class of functions. Similarly, a linear function matrix in its column space will characterize another class of functions. Is this okay? So what is the idea? You start with a class of functions and try to find a proxy to these vectors of interest within this class. So if you want to find Q mu lies in a very big dimensional space. So instead of searching everywhere, I'm going to say, look, I'm only going to search on the stage, which is like a class of functions, and I'm going to find a proxy for Q mu within this class, right? So I try to find a f within this class which approximates Q mu, or I try to find an f which approximates TQ within this class. And as I said, this class could either be a linear class or one that is associated with a neural network. In a linear class, we start out with a matrix phi, which is presumed to be known, right? And the dimension of this matrix is SA cross D. So the number of rows in phi equals the state actions, right? But the number of columns could be significantly less as compared to the state actions. So what we want to do is, within this column space of phi, can we try to find a good proxy for either Q mu or TQ, right? On the other hand, you can work with a neural network and again try to find a f, where this theta now describes the weights and biases that you are using to define this neural network. Okay, so now the question is, given that I have to search only within this class, how can I get hold of Q mu or TQ? I hope it is clear, and I hope you are able to appreciate why we are wanting to approximate Q mu and TQ. If you are able to approximate Q mu, we will be able to run policy iteration type ideas. If you are able to approximate TQ, you will be able to implement value iteration type ideas. So that's what the idea is. And here is a bunch of ideas that have been used across a spectrum of papers, right, to do this approximation. So let's go over it one by one. Here you have, the goal is to approximate Q mu. So you have some policy, and you want to know what is Q mu. Right? But Q mu sits in a big dimensional space, so we want to find a proxy for that, and here are a bunch of ideas, and here, given Q, we want to know what is TQ. Right? So let's go over this first idea, which is called as projection. So the idea here is, can you find me the f within my function class that is closest to Q mu? Is this okay? Q mu is unknown, I will come to that. Like, see, we first, as I told you, we first come up with an objective function, and then we try to figure out a way to minimize that objective function, right? So first, let's come up with an objective function and worry about, can I solve it or not later? Okay, I will talk about all these things as we move along. So the goal would be, there is a policy mu that I know. Can I find Q mu? But I cannot find Q mu like I cannot search for it everywhere. I'm only going to search within my function class. So that's why I'm saying find an f within calligraphic f which minimizes this distance. But as he pointed out, I don't know Q mu. So which means, if I want to implement this in practice, I will have to, on one hand, use data to get an estimate of Q mu, and on the other hand, try to minimize or try to find a proxy for Q mu within my function class. Is this okay? So this is the challenge. So to confront this challenge, what we do is, instead of trying to solve this problem, we try to solve this problem. So the idea here is, what is Q mu? It's the fixed point of T mu. What we do is, instead of trying to find the fixed point of T mu, you try to find the fixed point of a projected Bellman operator. Okay? So T mu f is a vector. You project that vector onto your function class. That means you try to find a vector which is closest to T mu f. That is what this pi f operator does. Now what you do is, you take this operator and try to find a fixed point for this operator. Okay? And one can show that if you try to find the fixed point of this operator, you will end up with a variant of the TD learning algorithm. Is this okay? The TD learning algorithm with function approximation actually tries to find the fixed points. If you remember, I said that the TD learning algorithm cannot be expressed as a gradient descent of some objective function. This is precisely what I mean. The TD learning algorithm actually tries to solve the projected Bellman operator. To clarify, the TD learning with function approximation will try to solve this. So this is the solution to address the concern that you raised. I don't know Q mu. So first I will need to know Q mu, then project. So in this idea of finding the fixed point of the projected Bellman operator, in some sense, you are trying to simultaneously estimate Q mu and do the projection. But that doesn't mean that the solution to this is equal to the solution of this. But what one can show is that under some conditions, the solution to this is a close proxy for the solution to this, right? So if it is a close proxy, maybe since solving this is, possible using samples, let's try to solve the solution to this problem. That is the fixed point of this projected Bellman operator. But then one realizes that, okay, the algorithm that can be used to solve this problem cannot be expressed as a gradient descent algorithm, and maybe studying it becomes challenging. So then what we do is, we try to come up with a different objective function. So here the idea is, you try to reduce the Bellman error, but only over the function class. Is this okay? So if you didn't have that restriction, the solution to this problem will be Q mu, because Q mu is the one that takes this error to 0. But since we are searching only within this function class, this error need not be 0. So this is an objective function with which you could work. You can see that here you don't have Q mu directly. So you can actually make use of samples to actually solve this problem. But now when you try solving this problem, you see that there is f located at 2 places. Now when you take gradient, I have to differentiate this f, that f. You end up in, some complicated rules, and the algorithms become complicated. Then you sort of say, okay, can I do some approximation further? Let me say this f is actually this, whatever is my current estimate. Okay, so I replace this f with this, and I now try to find an f that minimizes this distance. So when you try to do this, you only have one f whose gradient you have to worry about. So you end up with such an objective function, and there is a similar interpretation for all these ideas over here as well, right? And I would like to highlight that these ideas have appeared across a plethora of papers. Okay, for example, it appears in this LSPI idea from 2003. There is this fitted Q iteration which appears in 2005. Then you have approximate modified policy iteration 2015. Then there is a bunch of algorithms that build on the Q learning idea, something called as double Q learning, deep Q learning, deep Q network, DDPG, TD3. There are a bunch of algorithms that make use of these objective functions that I have mentioned over here. And then there are also algorithms that build on the conservative policy iteration idea, including TRPO, PPO, and so on and so forth. So if you are been exposed to reinforcement learning before, you can see that all the popular algorithms are listed over here. Is this okay? So in other words, all these algorithms at a high level, okay, indeed make use of some ideas like this for policy evaluation. Okay, and some ideas like this for approximating your value iteration idea. Okay, all right. So now the question is, suppose we manage to somehow do that, right? Does it work in the model-based settings? Okay, so the question is, does it work? What works? Does the idea of function approximation work in the model-based setting? Is this okay? So here is a nice paper by Bertsekers from 2011. It is called as Approximate Policy Iteration, and this paper repeats several ideas from his textbook that is there, which is called as the Neurodynamic Programming book, which is there from the 90s itself, right? And what this paper talks about is that the idea in approximate value iteration or policy iteration is to come up with an approximation in the value space. Is this okay? Value space meaning either your TQ or Q mu, these are your value functions, and you want to do approximation in the value space. And the hypothesis with which these algorithms work is that if I can somehow get a very good approximation of your TQs or Q mus, that will yield a better policy through policy improvement. That's the hope, right? Like value iteration works in tabular settings. If I can get a very good proxy for TQ or a very good proxy for Q mu, whatever works in value iteration, policy iteration, maybe the same ideas will work here as well. That's the hypothesis. And what Bertsekers says is, while this is a natural and reasonable hypothesis, okay, this is actually not self-evident and may in fact not even be true in a given problem. Okay, so what he says is the associated convergence behavior is often complex and involves what he refers to as damaging oscillations, which despite their initial description long ago. Okay, so these texts you can find in the 2011 paper, but there itself he says that these oscillations and things like that have been known for long. So if you actually search for value oscillation, policy oscillation, you will actually see that you will end up with papers in the 90s and so on and so forth. We'll actually talk about these issues and so on. So it's not like these issues have been only known recently. And here is an illustration of these oscillations. Okay, so let me give a quick description of what is shown in the figure. So you see there are different regions. Okay, so these regions are in the function approximation space. Is this okay? So the idea here is, this is what is called as the greedy region associated with the policy mu k. This is the greedy region associated with a different policy. This is the greedy region associated with another policy, and this is finally the greedy region associated with some fourth policy. So what you do is, let's say your value estimate is here. So you start here. If you take the greedy policy with respect to this vector, you will end up with this policy. That's the idea. Any vector here, if you take the greedy policy with respect to that vector, the answer would be mu k. That is what is the meaning of the greedy region. So any vector, any vector's greedy policy in this region will be mu k. Is this okay? Now what you do is, you take this mu k and try to find its value function. But the challenge is, you cannot find it exactly, you only have to search within the function class. So when you search within the function class, you may end up in this region. So this R mu k is a proxy, the little r mu k is the proxy for Q mu k within the function class, and this R mu k could lie in the greedy region associated with another policy. So if you now try to do a policy update, the next policy will be mu k plus 1. Now what would you do? You try to find the value of this policy, and its approximation would lie in another greedy region. You end up here, you try to find the greedy policy with respect to this vector. This will be this vector. You try to find its value, you end up here. Right? Now when you try to find the greedy policy, you will end up with this, and if you try to estimate it, you end up in the original region. Is this okay? So what this means is that you put in more data, more training time, you are going to keep circling over here. Now one can ask, can this happen in the tabular setting when you didn't use function approximation? There is something called as a policy improvement lemma which says that this cannot happen. Okay, so that one can theoretically show that these oscillations cannot happen in the no function approximation setting. It's only function approximation that actually brings in all these new issues, in particular these oscillations, right? These oscillations are very interesting and also dangerous, because you may feel that things are moving, but after a long time you may come back to where you were. Is this okay? So it's very difficult to figure out what if such a thing will happen beforehand itself, right? And so on and so forth. Now the question is, will such issues end up in the model-free settings as well? Okay, that is the question that we would like to answer. Do you agree? So in model-based setting itself, long back, people have said that if you use function approximation, lot of issues could arise. Now the question is, in the sample-based setting, would such issues continue to hold or not, right? And is it possible that maybe because of this noise and so on and so forth, maybe you can escape these oscillations and whatever issues that Bertsekas mentions here? Maybe in model-based setting, because of noise, the noise takes you away, and these like these strange attractors don't derail you. Okay, so that is the question that we would like to answer, and in particular, we would like to answer this question in the context of DQN. So DQN stands for Deep Q Network. Okay, this is one of the algorithms that came from David Silver's group, right? And it is one of the most popular algorithms, at least from the previous decade, right? And the algorithm has these many steps, right? Now let's try to make sense of what this algorithm is trying to do. In particular, let's see if it is trying to do something related to what we have studied so far. Is this okay? So in particular, let's read this step over here. It says that we try to do a gradient descent on this error. So let's try to make sense of this error. So let's first try to see what is this yj over here. This yj is the immediate reward plus gamma times plus max of some estimate. So notice that there is a theta minus here and a theta here, which means that when I try to do a gradient descent with respect to theta, this quantity will be fixed. Is this okay? So what this is trying to do is, it is trying to look at a sample-based version of the error, which is t mu k fk minus 1 minus f. If you remember that last error term that I described, which is called as the fitted Q iteration type idea. So this is what they try to do over here. Is this okay? So this is the error that they try to minimize. And now the question is, what can we say about this DQN algorithm? This is one of the very popular algorithms, and it has led to several breakthroughs. Okay, no doubt about it. But if you look at this recent paper, I think this year I have gotten it wrong. It's from 2024. So it appeared in this Journal of Machine Learning Research, and it comes from the University of Alberta, Martha White, Adam White, and their group, right? So they sort of ran DQN, and what they observed is that they observed some catastrophic failure events for DQN across every tested domain. Okay? In particular, they observed that in this environment called as lunar lander, when they used DQN, some agents would simply fly off into oblivion, right? Like you use this DQN algorithm, try to figure out a good policy. After the training, you come up with a policy and you try to run that policy, it leads to such behaviors. And despite training, getting this policy, these policies will try to get incredible amounts of negative reward until the episode was mercifully terminated. Okay? And similarly, in another environment called as Cliffworld, they report that this DQN will get stuck perpetually in a corner. Some agents would learn to jump in the cliff and so on and so forth, right? So it seems strange. You have an algorithm, right? It should learn something, right? So in trying to answer that, what we did was, we did an experiment on random MDPs. Okay, so this is an experiment that we did in our work, and this is the joint work with Aditya Gopalan. So here what we did was, we took 100 MDPs. By 100 MDPs, I mean we keep the state actions fixed, but we sample the rewards and transition probabilities randomly. and we fix some neural network, and we run the DQN algorithm for some fixed number of iterations, and then we ask whatever policy it has discovered, how does it compare with the initial policy? Is this okay? So if you have a learning algorithm, one would at least hope that the final policy that you end up with is better than the initial policy. One can understand that there is noise and so on and so forth. So I will at least hope that, okay, on most of the runs, maybe I end up with a better policy. Right? And what we observed is some pattern like this. Here is the initial performance gap. So this is the optimal performance and this is the initial performance. Since we know the transition probabilities over here, we can actually find out what the optimal policy is. But despite knowing the transition probabilities, we use actually function approximation to check whether these DQNs behave in a reliable fashion or not. So this is the initial gap and this is the final gap. So one would expect that the final gap is smaller than the initial gap, right? And every coordinate here, the x coordinate corresponds to the initial gap of that run and the final gap on that run. Okay, so dots over here would mean that the initial gap is larger than the final gap, and dots over here would mean that the policy has actually degraded. Is this okay? So if you see this thing, we were a bit puzzled that we couldn't find any pattern. Like a reasonable number of dots fall here, a reasonable number of dots fall here, and some of these dots seem to suggest that you actually try to end up getting a very poor policy. Okay, so we did this experiment. You can try to do this experiment. The code for this is available here, right? And then we started asking, right, are these issues connected to the issues that Bertsekas raised, right? And would that help explain some of these things? And in order to answer that question, and because we found it a bit difficult to directly work with neural networks, we looked at a simpler version of DQN, which we will call as linear DQN. So what do I mean by linear DQN? If you actually look at DQN, it actually makes use of 4 things. It makes use of epsilon greedy behavior policy. It makes use of something called as experience replay, which I have not defined, but you can look it up. Then it makes use of this target network. The target network idea is, if you remember in that error, there is a theta minus. So theta minus are the parameters of your target network, and the theta are the parameters of your critic network. So you update the parameters of the critic network to minimize that error, and once in a while, you move those parameters to the target network. So that's what theta minus means. And in DQN, you actually use neural networks to represent this TQK. Is this okay? So what we do is, we actually use linear function approximation so that we can see if similar behaviors arise, and can we provide some theoretical understanding of what exactly is happening. Right? So what we did was, we took a 2-state, 2-action MDP. Right? So this means your Q values sit in a 4-dimensional space, and then we did a 2-dimensional linear function approximation. Okay, so if you see, there is theta 1 here, theta 2 here. So if you put them together, you will get a 2-dimensional vector. If you multiply that with your feature matrix, which is a 4x2 matrix, you will end up with a 4-dimensional vector, which we will use to approximate your TQs that you see in between. Right? And what we did was, we ensured that the optimal policy is represented here. In particular, whatever your Q star is, that actually sits within the column space of V. In particular, if you look at star, this corresponds to 1, 10 raised to 0 is 1, 1, 0. So the first column of phi is actually Q star. Is this okay? So what do I mean by that? While your the function approximation means that you are going to search within a restrictive space. We chose that space so that that space actually contains Q star. Right? So the idea in function approximation is, you search within a restricted space. While the space is small, that space actually contains Q star. Okay, and that is what this star over here denotes. What does this dot denote? This is the initialization. Okay, and we chose this initialization to be close to this star so that the initial behavior policy, that is the greedy policy with respect to this estimate, is actually the optimal policy itself. And then we ran the algorithm multiple times. The Q learning algorithm, the DQN algorithm with linear function approximation. And you see that some initial parts are faded, right? This is just to declutter the figure, right? There is a red trajectory, and the faded part denotes the initial part of the trajectory. Then there is a green trajectory. You can see that it jumps around and later on settles here. Then there is a blue trajectory which also jumps around and then settles over here, right? And I am sort of highlighting the tail behavior of these different trajectories. And one can see that on different trajectories, okay, the algorithm actually settles at different places. Is this okay? So it's like you start from a policy which is actually the optimal policy, and then you run your Q-learning algorithm on different trajectories, you end up at different places. Is this okay? And what we observed is that if your estimates settle over here, how does the greedy policy look like? For these two trajectories, the greedy policies were constant. In this green trajectory, it was some policy which we denote as pi 2. In this case, it was some greedy policy pi 3. But the strange thing with regard to this red trajectory was that if you look at the greedy policy with these iterates, they actually jump between two policies. So this is what is called as policy oscillation, right? Now let's say you ran your DQN algorithm and you saw policy oscillation. Okay, what would you guess? Perhaps it has settled between two policies which roughly are good, and it is trying to decide between the two policies. Maybe their Q values are very close to each other, hence it is unable to figure out which of the two is better, and hence maybe it is jumping between the two. Something like that is what you may interpret, right? And the goal that we had was, can we make sense of all these different behaviors? Okay, so in order to do that, we had to make use of something called as differential inclusions. So if you remember, in our previous lecture, I said that the limiting behavior of your tabular Q-learning and the limiting behavior of your TD learning for policy evaluation, all those things can be analyzed from the perspective of differential equations. Okay, but we realized that because here we are working with an epsilon greedy behavior policy, right? Working with ordinary differential equations is not going to suffice. Instead, we have to work with some concept called as differential inclusion. So let me now give a very high level idea of what a differential inclusion is. So a differential equation is typically written as theta dot of t equals something. Now notice that in a differential inclusion, you have theta dot of t belongs to something. So here H is actually a set valued map, right? Which means that if you give a vector as input, it will spit out a set. Okay, so the idea here is, if theta of t denotes your position, h theta gives you a set of velocities. Okay, and along any trajectory, the velocity will be one of the possibilities from this set valued choice. Okay, that's what a differential inclusion is. And then this bullet sort of describes how do you define a solution to a differential inclusion and so on. There is some technical description, right? And this is what I want to sort of ask you to keep at the back of your mind. The solution trajectory for a differential inclusion can pick any arrow. Arrow is like a velocity inside a little cloud of allowed velocities, right? In a differential equation, when you are at this position, there is an explicit arrow to follow. Okay, in a differential inclusion, you have a cloud of possibilities, right, or a set of choices, and you have to pick one from this set. And in our work, we show that this extra wiggle room makes differential inclusions ideal for capturing different mode switches. Okay, so let me elaborate what mode switch means. Recall that we are doing this epsilon greedy exploration, which means that whatever your current estimate is, you are going to act greedily with respect to that estimate with some probability. Now, when your estimate changes, the greedy action is going to, the greedy operation will give you a different action. So this is what mode switching means. Here you are acting in a certain way. When you go to a different region, you are going to act in a different way. Is this okay? So you can, see that there is some difference in how you act here and how you act there and so on. So this is what is called as mode switching, and the differential inclusion is needed at the boundary of that mode switching. Is this okay? Because when you are here, okay, there is just one way to act. When you are here, there is just one way to act. But what happens on the boundary, right? In the boundary, you have a choice. Either I act greedily as per this region's policy, or I act greedily as per this region's greedy policy. So this choice, to sort of handle that choice, we have to make use of differential inclusions. Okay, let me just have a time check so that I can decide. So I think I'm running out of time. So what I'll do is I'll skip some of these things and may move to the more important parts. So this is an example of a differential need for differential inclusion. In particular, you can see that there is some discontinuity over here. There is a function, right, which for positive values takes the value -1, and for non-positive values takes the value +1. So you can see that there is some discontinuity over here. This is an illustration of a mode switching. On the positive region, you behave in a certain way, and in the non-positive region, you behave in a different way. So this is what a mode switching means. And what this slide tells us is that you cannot study the behavior of this algorithm via an ODE like this, right? That is the illustration of this. But that same algorithm's behavior can actually be studied by a differential inclusion of the following form. Okay, so what is over here? For negative values, you take +1. For non-negative values, you take the set -1, and at 0, you take the interval from -1 to +1. Is this okay? So you make this modification. Here in contrast, for 0, the value was a singleton +1. Whereas here, at 0, you consider the closed interval -1 to +1, and you can see that at 0, you have a set of choices. You can pick any value between -1 and +1. So this is like the set valued story here, and one can show that using this differential inclusion, you can actually study the behavior of this algorithm. That's like the short summary. And in our work, what we do is that we use this concept of differential inclusions to actually understand the behavior of linear DQN. Is this okay? So this is the update rule that we have. And if you recall the update rule for Q learning, it was Qn plus 1 equals Qn plus some step size times some temporal difference times ESNAN. Okay, where ESNAN were your standard basis. Now, since we are working with linear function approximation, the ESNAN is now replaced with the SNANth coordinate of your SNANth row of your phi matrix, and the temporal difference part stays as it is. Okay, so this is, I mean, you can again cook up this algorithm the same way that we cooked up that algorithm. I mean, you can start with an objective function, replace your Q star estimates with these quantities and so on, and you will end up with an update rule like this. Again, you have a temporal difference over here. This quantity is the current estimate of Q star. Okay, this quantity over here is the next estimate of Q star using the new data that you see. Okay, so these two quantities are the estimates of Q star itself, and that's why we refer to this as the temporal difference. Is this okay? And here again the idea of bootstrapping is there. Bootstrapping by itself, that is, you use Qn itself to cook up two different estimates of Q star, right? That's the idea of bootstrapping. That itself is not problematic. But when you try to combine bootstrapping with function approximation, that's when things start getting, very challenging. Okay, so there is something called as a deadly triad that Bertsekas talks about. Okay, in this deadly triad, two of these things is function approximation and bootstrapping. Is this okay? So bootstrapping by itself is not a problem, right? But when you combine bootstrapping with function approximation, it leads to some problem. So that is what I will talk about, right? So we look at a temporal difference thing like this, and observe that here we don't put theta n, but instead we put theta n minus. This is to mimic your target network type behavior, and the target network sort of has some theta n minus, which is kept frozen for a few number of steps, and after some 1/d delta steps on average, it is set to the latest theta n. So that's how your target network works and so on. So we try to mimic those things, and our final result is the following, that the theta n iterates that are generated by your linear DQN, its limiting behavior is governed by a suitable differential inclusion. Okay, and what is this differential inclusion? It basically, the set valued map is defined over here, and perhaps it is more easier to understand it over here, right? So what does this map say? You see that you have a linear operation here. It's like a b minus a theta type expression over here. So this is linear, right? However, the vectors and the matrix that are over here, they depend on a bar, right? And this a bar is depending on some greedy region. So which means that if theta belongs to the greedy region associated with A bar, you pick this operation, and when theta belongs to a different greedy region, you pick a different linear operation. In other words, the dynamics is what is described over here. This is linear dynamics, this is linear dynamics, this is linear dynamics, this is linear dynamics. So what you have is what is called as a piecewise linear dynamics. Is this okay? So Q-learning's behavior is non-linear. What we are saying is with function approximation, you end up with piecewise linear dynamics. Are you with me? Piecewise linear, since it's not globally linear, is not linear, but the non-linearity reduces to a piecewise linearity, right? Now this in some sense helps us understand what exactly is happening, and now we will try to interpret the behavior of linear DQN that we saw before. Okay, so let's try to interpret this figure. You have some linear dynamics here, which means you have some differential equation of the form B minus A theta. So if you run this differential equation, where would the solution trajectory go to? A inverse B. Do you agree? Provided your A is positive, definite, or has those nice properties. If it has those nice properties, it will go to A inverse B. Now you see that for every region, there is a color and a diamond with a similar color. So this is the A inverse B associated with the dynamics in this region. So here life is good. The A inverse B associated to this dynamics sits within the region itself. Here again, the A inverse B corresponding to the dynamics in this region sits here, but here something strange happens. The A inverse B associated to the dynamics here sits here, and the A inverse B associated to the dynamics here sits here. Now let's try to interpret what is happening here. You run your linear DQN, right? Because of noise you will keep moving around, right? And we are reducing the step sizes as well. So once the step sizes become sufficiently small, your iterates will start settling at some place. So if your iterates settle in this region, they will try to track the solution trajectory of this ODE, and the solution trajectory of this ODE is pushing you towards this blue diamond. So you can see that when you settle here, you indeed go to the blue diamond. Okay? But it is also possible that that noise could push you to this region, and then the step sizes become sufficiently small. Here you start tracking the equilibrium associated to this dynamics, in which case you could settle over here. Now what happens here? When you are here, you find the grass greener on this side, and you start here, try to move here. As soon as you move here, the greedy policy has now changed, and you start acting in a different way, which means now the dynamics of your algorithm has changed, and you now try to track the equilibria that is associated with this dynamics. And you sort of go here, then you try to come back here, then you try to go here, then you come back here. And what happens is, when you try to always move towards the other side where you perceive the grass is greener, you will end up settling on the boundary. Okay, so if you see, this is neither this nor this, but you actually settle on the boundary at a point where the dynamics actually cancel off. Okay, so there will be a point on the boundary where the two dynamics actually cancel off, leading to a 0 in the convex combination, and that is the point to which you will settle at. Is this okay? And now you can see that if you have a trajectory that is settling to this point on the boundary, it will sort of jump between the two regions, right? And if you look at the greedy policy associated with these iterates, one time it will be this, one time it will be this, and you will see these oscillations. Is this okay? So now one can ask, okay, maybe you have used linear function approximation, maybe these issues that you are observing may only hold in linear function approximation. What would happen if you actually make use of nonlinear function approximation, right? Okay, before I go that, let me also give this very interesting scenario. We tried cooking up another MDP and use linear DQN in this setting, and the limiting dynamics actually turned out to be this. Now what is strange about this differential inclusion is that from wherever you start, you go to the blue region, and once you go to the blue region, you will be pushed here. Are you with me? So similarly, if you start in the white region, you try to go over here, so you will cross over to the blue region. As soon as you enter the blue region, you will try to go to the blue diamond, and so on and so forth. So in other words, the nice thing about this differential inclusion is that every trajectory will eventually end up the blue diamond, which means for this nonlinear dynamics or piecewise linear dynamics, there is a global attractor. So if there is a global attractor, one would presume that maybe if I run my algorithm over here, it may perhaps converge here, and wherever it converges to, that corresponds to some good policy. So one can show that if you end up here and you take the greedy policy associated with this estimate, it will be the worst policy among all possible policies here. Is this okay? So my point is, if you run DQN in this setting, it will actually take you to the worst possible policy. It's not like, if you give more data, things will get better. If you train for longer, things will get better. It's not like that. Here, the global attractor is associated with the worst possible policy. Whatever you do in this scenario, it will go over there. Okay? So that's the reason one has to do a lot of hyperparameter tuning so that all these weird cases are edged out and some reasonable behavior is observed. Okay? So now the question that I raised before, that maybe whatever we have observed happens only in linear function approximation case. What happens if you work with non-linear function approximation? So this is discussed in one of the papers by Aviral Kumar, who is one of the speakers who will be talking in this workshop on Sunday. Right? And what he discusses is offline DQN in Atari settings. In particular, he looks at different environments. Right? And he talks about the average return that you see for DQN. Is this okay? So one can see that as you increase the number of gradient updates, right, the average return gets better, which means that your policies get better. But as you do more gradient updates, the policy actually starts falling. Okay, it sort of gets poorer. Here again you can see that it gets better, then starts falling, and so on and so forth. So then one may claim maybe such behaviors maybe are apparent only in DQN type algorithms. Maybe there are some other algorithms which don't have such issues. Well, here is the story on PPO, which is called as proximal policy optimization, which is inspired from this TRPO, which is inspired from conservative policy iteration. Here again one can see that you sort of gain in performance, but as you do more number of interactions with the environment, that is, you provide more data, the performance actually drops. Okay, this is what is referred to as performance collapse. Right? We have an understanding of what could lead to performance collapse in a DQN type algorithm. We are conjecturing at this point that maybe those ideas and interpretation may actually carry over to PPO as well, but we have not studied PPO in that depth. All right. So this brings me to the end of this class, this lecture. So what are the takeaways? So dynamic programming methods in the tabular setting have strong guarantees. Is this okay? But when you try to combine these ideas with function approximation, even in the model-based setting, Bertsekas has long time back highlighted that you could end up with several issues, such as oscillations, convergence to suboptimal policies. All those things can happen, right? And now the next thing that we would like to understand is there some way we can go about fixing it? Okay, so in the class after the lunch, in the lecture after the lunch, we will actually discuss some of the ideas from our lab where we have tried looking at this and coming up with some ideas to fix it. Okay, let me stop over here. Thank you. Yeah.
Hello. Yeah, it's just for a personal project actually. So according to what you show, what we saw in on the slides, you mean to say that if let's say I have a forecasting problem and I am using let's say PPO for that. Let's say I put a 6-year data and I let's say train another model with 18 years of data. Does it mean that the 6-year data will be better than
it doesn't say that. I would say that I don't know whether the 6-year data would be better or the 18-year data would be better. That is the problem.
Okay.
Is this okay? Ideally, one would expect that more data should lead to better performance, right? That did not happen.
Okay.
Is this okay? So I'll give you maybe a slight illustration of what do I mean by that. More data would give perhaps closer estimates of these quantities, right? I presume. But closer estimates doesn't mean that things are getting better. So let me illustrate. See, our goal at some level is to be greedy with respect to Q mu. Even though we are far away from Q mu, the ordering could still be correct. Like maybe the Q mu for different actions, let's say the value was 190. So the first action is better than the second action, and maybe your estimate is 2-1. So 2-1 is far away from 190, but you see that the ordering is maintained. But it is possible that you get a very close estimate, but this time the estimate, let's say, is 80 and 90.
Okay.
So 80-90 is a very close estimate to 190, but you can see that the order has flipped.
Okay.
Right? So even though you get a very close estimate, if you look at this greedy policy obtained by this very close estimate, the greedy policy could be very different. Is this okay? Yeah. So here as such, we are, at least as far as I understand, the current algorithms are not accounting for all these things. Okay. They are not saying that a poor policy estimate could still give a reasonable estimate of, the policy improvement, but, a very close estimate could account for a very bad estimate and so on and so forth. So that's the reason I would say that it's unclear whether a 6-year or, I'm not saying that it will be bad. Right? But if we run an algorithm, we have to be sure that it will lead to improved performance if you provide more data. Ideally, one would like that. Yeah. Okay, but that is something that may not happen. Okay, and that, I hope you sort of understood that I'm not saying it will be bad. I'm saying that it is unclear. Okay. Is this okay? That's the point.
Yeah, sure.
Yes.
So in that plot where you were analyzing, we have piecewise linear segmentation. Yeah, so I think I will have to go into the details of the paper, but just I was curious why the attractors for each of the regions are overlapped. It's not, like for example, blue and green, the attractor remains within those boundaries. Yeah. But here, why are they flipped and others?
So at some level, the idea is that if you try to interpret the equilibrium of the dynamics associated here, an alternative interpretation would be that you look at, the dynamics here can be viewed as some projected Bellman operation. Is this okay? Now, projected Bellman means what? You are doing some projection, and the projection is to be done with respect to the greedy policy in this region, and then you have this Bellman optimality operator. So you have this projection T, and you are trying to find the fixed point of that. Is this okay? Now the projection is affected by the greedy policy here. The Bellman operation is, doesn't have any influence of the behavior policy, but the projection operation is influenced by that, right? So because the projection operation is influenced by the greedy policy here, where the fixed point will lie is something that, changes from the choice of the behavior policy. Okay, so here the behavior policy is the optimal policy itself, and if you now try to find the projected Bellman where the projection is with respect to some stationary distribution associated with the optimal policy itself, it turns out that the fixed point is this thing, whereas here the fixed point is over here, but here it is this. So the short answer is one can expect that these fixed points can be in different regions, right? Why in these situations it lies here and why it lies here, that is something I don't know. But in general, they can be all around the place. Let me put it this way. Okay, so all these things, at least at a high level, can happen. And in the function approximation setting, okay, at least in our experiments, we have seen that whatever possibilities we guessed, we were able to cook up some MDPs where we observed those things. Let me just put it this way. Thanks. Okay. And in the tabular setting, because you are not trying to find the fixed point of the projected Bellman operator, but you are rather trying to find the fixed point of the Bellman operator itself. So there you will not see these multiple fixed points. There you will only see a unique fixed point. Right. Okay.
So if I can ask a follow-up. So in the next plot, why was that behavior worse? So what?
Why is it behavior worse? Because if you take, so this gives you the theta values. There is a phi matrix that is separate, we use in these simulations. You take this theta vector, multiply it with phi, you will get some phi theta, which we will interpret as an estimate of Q star. So you take that phi theta star, look at the greedy policy with respect to phi theta star, that will give you a policy. Then you look at the Q value of that policy, like the true Q value of that policy. And the true Q value was the worst among all the policies. Does that help? Yeah. Right? Thanks. So that's what I mean by it being worse. Okay? Yes?
I have a quick question, slide number 18.
Yeah.
So by greedy policy, you're referring to epsilon greedy, isn't it?
Yes.
So
No, here greedy policy is the greedy policy.
okay. So
Right, so let me sort of elaborate a bit. When you run the DQN algorithm, you work with epsilon greedy, but when I ask you to give an estimate of the optimal policy, you give the greedy policy.
okay.
Does that help?
Right.
Okay.
So the question is like if epsilon greedy is applied here, probably
Here.
maybe we end up with pi star optimal policy because because we are stuck in pi naught and pi 1 as the greedy policy is not exploring much.
No, let's be careful here, okay? This algorithm runs with epsilon greedy exploration, okay? This is the greedy policy, not epsilon greedy. This is the greedy policy which is associated with your estimates. Is this okay? So it's not like, because our epsilon is, because we choose some epsilon or something like that, you don't see exploration. So exploration or all those things is happening. The reason it is settling here is because there is an attractor. Like that is the answer, right? So you sort of run like in a differential equation also, okay, you may do a lot of things, but if you are close to an attractor, you will go there. Is this okay? So that is what is happening. There is an attractor here, that's why these iterates are settling over there, okay? And a summary of what we have done is we have tried to understand what these attractors are, okay? And what we have managed to show in our work is every attractor for a linear DQN will actually be a fixed point of a projected Bellman operator. That's the summary. Like every attractor will be a projection of a fixed point of a projected Bellman operator, but the projection operations, will be like you could use multiple projection operators depending on what behavior policy you work with, right? So that gives a multiple choices for the projection operation, and many of the fixed points of this projected Bellman could be attractors. Some of them need not be attractors, they could be unstable, but many of them could be attractors. And here we have illustrated a scenario where the projected Bellman fixed point of the projected Bellman operation, where the projection is defined with respect to the worst policy, that actually is the only fixed point in this scenario. So all those things can happen. I'm not saying it will happen always, and I'm not saying that if you do some hyperparameter tuning, this issue won't go away. But my point is that these things can happen, and unless you take care of your simulation settings, you may end up in such scenarios. That's the point I want to illustrate. Okay? Yeah.
Yeah, so my confusion is like, okay, this was a linear approximation. How does the depth affect? Like,
how does?
The depth of the, let's say you are replacing this by neural network. Usually they go with very deep neural networks, right? So problem could be that this is a linear approximation.
Yeah, so exactly that's the point I wanted to make through these plots. Is this okay? And also this earlier description that I gave. Yeah, so this paper, okay, this is from Patterson et al. 2024. Okay, this paper actually works with neural networks. Is this okay? And there also, if you see, they see that you run DQN and the agents will try to find policies which have look very strange. Is this okay? So our interpretation is that even though you are using neural networks, okay, so maybe I don't know if this is what you are asking. So the difference would be that the greedy regions in the non-linear settings will not be having such nice structure. So the nice structure here is that every greedy region here is actually going to be a cone. Cone means if you take any vector, multiply a positive scalar to it, that vector will sit here. So this is what is called as a cone. And one can show that in linear function approximation, the piecewise dynamics will differ from one cone to the other. In non-linear settings, again you will have greedy regions, but these greedy regions did not have this cone-like simple structure. It will have some very sophisticated structure. I mean, this is the kind of plot you may end up with. Right? So there will be some regions like this and so on. So the idea here is here you will follow some dynamics, here you will follow some dynamics, here you will follow some dynamics and so on. And when you are following the dynamics here, you will try to go to the equilibria that is associated with this dynamic. So in the non-linear settings, while the cones did not the greedy regions did not have good structure, right? the piecewise dynamics will still hold. Is this okay? And then you will try to go here, and as soon as you move here, you will try to find the equilibrium of this dynamics. Then you move here, and once you reach here, you try to find the equilibrium of this dynamics, and all those things can still happen. Okay?
So it's evident from this plot that even if you try to minimize the distance to travel in one iteration by some regularization, you will still run into this issue. Like
I'm not saying you will still run. You can run.
Yeah,
it can run.
Yeah.
Okay? Right? So that's why you will have to, our understanding right now is that this is the reason why you have to do non-trivial amount of hyperparameter tuning. And when I say hyperparameter tuning, one of the things that you do is you play with the neural network's structure itself. So that is, you play with your function class itself with which you are trying to approximate. Okay, and often one has seen that sometimes the richer network will actually give poorer results. A poorer network may actually give better results. All those things, if you have done deep RL, you will see that all those things you will experience. Ideally, one would expect that a richer neural network should give better results. But at least in our experiments, we have often come across the opposite and so on. Right? So my point is that when you play with these function approximations, maybe some of these issues go away. Okay, so to begin with, you may start with some neural network where these issues may happen, and when you start your training, you may end up in some oscillation or convergence to suboptimal policies, and maybe you try to do hyperparameter tuning until you get rid of these issues.
Do you have a recommendation of how to get rid of, like, if you are a...
I don't have. Okay, so okay, let me answer that in a different way. With these algorithms, we don't have, right? We have now developed a different way to handle these problems that to us looks promising to address these issues. So maybe you can answer this question at the end of the 4th lecture, in which I will talk about some ways of addressing these issues. But first, understanding why these issues occur, and then figuring out a way to fix it. Okay, so if your question is, how do I do this hyperparameter tuning to get rid of these issues, I don't know. But in our 4th class, we will actually see how to modify the algorithm suitably so that some of these issues can be fixed. Fixed here is in quote unquote. You will see what do I mean by fixed. Is this okay?
So when you go to the next slide, the worst case performance. So here you need to say that once we start the start doing the epsilon greedy with any theta 1, theta 2 in the left and right region, we converge towards the thetas of the worst possible policy, right? So you mean to say any epsilon greedy, is it? Whatever.
This is with some epsilon greedy.
Some epsilon greedy.
Okay, so it's not like with any epsilon, but these regions are going to continuously change with the choice of epsilon. So it's not like if you just even minorly perturb this epsilon value, then it will go away. It won't happen like that. So it will be, these greedy regions and all will grow or decrease in size continuously with respect to this choice of epsilons and so on. Is this okay? So that's the answer to your question. I'm just thinking about, yeah, okay. So
second question is, the reason you consider set value map is you want to consider all possible policies, behavior policies, and their basically T operations.
No, the reason for considering differential inclusion is to handle what happens at the boundary. Okay. Is this okay? So here there is some linear dynamics, meaning if you are, if you are here, then the velocity direction that you have to choose is explicit. Here it is explicit, in the interior it's explicit, in the interior it's explicit. What happens on the boundary? Okay, so we have to account for that, in particular, to explain this behavior, for example. Okay, because here it is neither settling in this region or in this region. If it's settled within the region, we can look at the local dynamics and provide an explanation. But the fact that it is settling on the boundary means that you cannot ignore either of these local dynamics, so you have to take a combination. How do you take this combination comes from this idea of differential inclusions.
So you are able to show convergence in that sense.
Again, I would like to highlight, we don't show convergence. What we show is, if you converge, what is the, can you give a characterization of the limit? If you converge, can you give a characterization? So so our result is that if your DQN iterates converge, so these are stochastic algorithms, Okay, so on different runs, they will behave differently. So on any run, if they converge, what can you say about these limit points? Can we somehow say that those limit points will be associated with good policies? Will they be associated with bad policies? So the answer that we provide is every limit is actually a fixed point of a projected Bellman operator, and the projection operator is what keeps changing. Like there are multiple projection operators because you can work with different behavior policies. Every behavior policy will result in a projection operation, and all those projection operators could potentially lead to a fixed point. And if those fixed points turn out to be attractors, you can converge there. That's the solution. I mean, that's the interpretation of our result.
Thank you.
Okay. Okay, looks like a good place to stop. Thank you. To the post-lunch session. So this is the 4th lecture that I'll be giving, and there are 2 more lectures in the afternoon session. Those sessions will include some hands-on training by some of my students, as also other students from IISc who are working on reinforcement learning. All right? Okay, so this 4th talk is titled Monotone and Conservative Policy Iteration Beyond the Tabular Case. Okay, so as we saw, there were some issues in the function approximation sense, but things worked in the tabular settings. So we want to ask, can we somehow take some of those guarantees beyond the tabular case? Okay, so at some level, that's the question that we want to discuss. Okay, and this is joint work with a bunch of my students, Ishwar Girik, my colleague, and my postdoc colleague, Aditya and Gal, and we also have a bunch of students, some of whom are present here, Anirudh, Ananyabrata, Kintan, Krishna, who have all helped with different parts of this project. So let's do a quick summary of what we have done so far, right? So we have been discussing RL. So what is RL? We have an agent that interacts with an environment, right? And the environment is modeled as an MDP, and the agent's goal is to find the optimal policy, right? So previously, at least in the first lecture, we were debating what optimal means and so on. In this setting, now I hope you can see that we have a very clean definition of what optimal means. Is this okay? That's the goal. And the challenge is that P is unknown and the state and action spaces could be very large, right? So we saw some of the issues with current reinforcement learning algorithms. In particular, we discussed DQN in depth and also provided some related issues with PPO and so on and so forth, right? When you try to incorporate the tabular ideas to the function approximation setting. Okay, so at a high level, that was what the challenge was, and we sort of looked at some Bellman operators. So this definition, please keep in mind, because these things we will now be using explicitly one more time. Right, so in the second lecture, we sort of discussed various model-based algorithms. In particular, we discussed value iteration, policy iteration, conservative policy iteration, and we showed that, at least for value iteration, that all these algorithms have strong guarantees. But in the third lecture, we saw that these guarantees are lost when you combine these ideas with function approximation. Okay, so this is the summary. In particular, when you try to approximate this TQK and QMUK, so please keep in mind that you may have a very rich function approximation setting in which you may be able to get a very good approximation to these things, but that still doesn't say that your algorithm will be devoid of those issues that I highlighted. Okay, and not surprisingly then, reinforcement learning algorithms. So when I use reinforcement learning, I explicitly mean that we are working with model-free settings, whereas when I talk about value iteration, policy iteration, and so on, I am implying that we are working with model-based ideas. Is that okay? So the model-free algorithms that are inspired by these things, right? It is not surprising that some of these algorithms such as DQN, DDPG, PPO, right, they also end up having oscillations, convergence to suboptimal policies, performance collapse, hyperparameter sensitivity, and so on and so forth, right? So to elaborate on the hyperparameter sensitivity, as I said, if you don't choose the right function class, it is possible that, you may learn, but you may end up converging to a suboptimal policy, right? So unless you do that hyperparameter tuning, okay, things may not work. So the question is, can we somehow address it? Okay. So towards that, we have, developed something called as reliable policy iteration, which I would like to talk about here. So towards that, the first question I would like to ask is, what worked in the tabular setting, right? And what is it that I want to make it work in the function approximation setting? Okay, first let's ask, right, what worked, right? So we can say, okay, in these value iteration, policy iteration, and so on, there was some convergence. Okay, it was trying to do some TQ, Q, something it was doing. But if you want to summarize one thing that was common across all of them, and perhaps is something that we can incorporate in the function approximation setting as well, right? So we sort of asked this question, and we realized that in some sense, these all algorithms are learning, right? Quote unquote learning, because what does learning mean is what I want to describe. I want to say that learning in some sense is connected to some notion of monotonicity. Is this okay? When something monotonically gets better, one can say that perhaps there is some learning that is happening, right? And in all these model-based algorithms, we saw that something was getting better in a monotonic sense. Is this okay? For example, in the value iteration setting, when such an initial condition held, right, your Q0s, Q1, Q2, and so on, they monotonically got better. In the same way, in the policy iteration setting, when you evaluated the intermediate policies, the Q value functions of the intermediate policies, they monotonically got better, right? And in the conservative policy iteration setting, these averages kept getting better. By average, I mean, instead of looking at the monotonicity at a vector level, you looked at it after taking an inner product with some weight vector. Like for example, here your nu is your weight vector. You take its transpose and multiply it with this vector, you end up with a scalar. So at least this scalar is guaranteed to monotonically improve in the conservative policy iteration, right? So at some level, I feel, so I'm emphasizing I because I'm not sure if this is the right way to, describe learning, but I believe that some notion of monotonicity is required to say that your algorithm is learning. Okay, so then we ask, okay, it is this monotonicity, if that is what is special, can we incorporate that monotonicity in the function approximation setting? Okay, so that is the question that we want to pursue. I hope the goal is clear. In the model-based settings, all these algorithms have some sense of monotonicity. Can we extrapolate or extend that monotonicity to the function approximation setting? And maybe in that case, we can say that maybe there is some learning that is happening even in function approximation, right? It would be great if something like this happens. Why this would be great? Because then your policies are getting better and better. But that would require that you know the Q values somehow, and the Q value functions themselves get better, but we are in the function approximation setting, so perhaps expecting this would be too much. So the question that we began with was, can we somehow ensure some notion of monotonicity that approximately reflects the monotonicity that we see over here? That is the question that we want to address. Okay, so towards that, we sort of, went back in history and asked, what were the algorithms from the past that had this monotonicity, and at which point did this monotonicity start failing? Is this okay? So we saw that value iteration had monotonicity. This was the algorithm in 1950s. Then there was this policy iteration, which was the algorithm in your 1960s, right? And then we had this conservative policy iteration, right, which came in 2000s, which also had some monotonicity. But this function approximation ideas actually precede conservative policy iteration. So we sort of went back in history and asked, at what point in time, did people stop caring about monotonicity, right? So towards that, we sort of came across this algorithm called as modified policy iteration. Is this okay? So in this modified policy iteration, which appears in this textbook by Putterman, in this paper by Putterman and Shin, which is also discussed in the textbook, right? So this algorithm also has a policy evaluation step and a policy update step. Is this okay? But the difference here is that here you do the policy evaluation partially. What do I mean by that? Let's say you start with some initial value estimate Q0, right? And some initial policy mu0. You take this Q0 and you apply this T mu0 operator m times. So what it means is that you start with Q0, apply T mu0. Then whatever is the output, you apply T mu0 again on that. And then you again do T mu0 until m many times. And whatever is the output, you call that as Q1. And then you define the next policy to be greedy with respect to Q1 and you repeat it. Is this okay? Now let's try to compare this with value iteration and policy iteration. Okay? Now if m was 1, and your mu k is greedy with respect to qk, then one can show that because mu k is greedy with respect to qk, T mu k qk is actually tqk. Okay, so if you recall the definitions of this T mu and Tx, notice that there is a max operation here, right? And here the A prime is chosen from mu. So if mu is greedy with respect to x, then if you pull action A prime according to mu, you will actually be doing this operation. Is this okay? So if you come back over here, if m is 1 and mu k is greedy with respect to qk, then this is actually value iteration. Are you with me? So if m is 1, this is value iteration. Now let's ask, can we get policy iteration from this? And the answer to that is yes, again, if you set m to be infinity. Why is setting m to be infinity going to lead us to policy iteration? Because T mu is a contraction operator. If you take a contraction operator, start with an arbitrary vector, apply that contraction operator infinitely many times, you will go to the fixed point of that operator. And if you take T mu k and apply it infinitely many times, you would end up at Q mu k. Is this okay? So the policy evaluation step will then lead to Q mu k. And then you take a greedy policy with respect to Q mu k. And then if you repeat this process, you will see that you have policy iteration. Okay, so in that sense, you can see that this modified policy iteration is a bridge between value iteration and policy iteration. In fact, there is an even more relaxed version of this algorithm, which is called as optimistic policy iteration, wherein instead of updating the full vector, you only look at a small subset of state actions and make such updates only for those chosen state actions. And for the other state actions, you set qk plus 1 to be equal to qk. Similarly, here in this policy update, you again choose a small set of state actions and update the policy only on those small state actions and keep the policy at the other state actions to be equal to the previous policy. Okay, so this is like a relaxed version of this. And what we observed is that even with such relaxations, the iterates that are generated in this setting actually end up having some monotonicity here. Is this okay? So let me summarize. This algorithm is nice because it somehow captures both value iteration and policy iteration. And in this case, if you have some initial condition like this, then the iterates generated by this algorithm also have monotonicity. Okay? And if you sort of go to this paper, or alternatively this discussion is also there in Bertseka's textbook, right? And you try to understand why do you end up with this monotonicity, you realize that the monotonicity proof is actually a half a page proof. And the key inequality in that proof is something like this. So notice that there is an initial condition, right? T mu0, q0 is greater than q0. So you have to choose q0 and mu0 so that this is satisfied. Once this is satisfied, from the properties of your T operators, remember I said that these Bellman optimality and Bellman operators are monotone, right? By using those properties, one can show that the same inequality actually holds at time instance k as well for every k. And once you show this inequality, Okay, it is very trivial to extrapolate this to this. Is this okay? So then we said, okay, if this is the key inequality, how to ensure such an inequality in the function approximation setting? Okay, because we realize that the monotonicities, the monotonicity is a consequence of this inequality. So how to get this inequality in function approximation setting is the question that we started asking. Is this okay? And here is a short proof of why this inequality actually holds. Okay, so here is the initial condition. So this inequality holds because of our initial condition. Is this okay? And if you take m equals 1, this will be your q1. And the question now is, if you obtain q1 in this fashion and mu1 is said to be greedy with respect to q1, would t mu1 q1 be greater than q1? Okay, and here is a one-line proof of why this condition implies this condition for k equals 1. And once I use such an argument, one can show using induction that this inequality holds for every k. Okay, so here is how short that argument is. Okay, you can go over that argument, and I'm happy to explain that argument as well later on. So keeping this in mind, we said, can we incorporate this inequality in the function approximation setting? Towards that, we propose this idea of reliable policy iteration. Okay, so this also has a policy evaluation and policy update step. Okay, and notice that we are in the function approximation setting. Okay, and again to emphasize, we are in the model-based setting right now. Okay, we will eventually figure out how to take these ideas to the model-free settings. At this point, recall that Bertsecker said that, even with model-based settings, when you use function approximation, there are a lot of issues. So the question we wanted to ask was, can we somehow address some of those issues in the model-based setting itself? And perhaps if we are able to address it there, maybe we may have some chance of addressing similar issues in the model-free setting. That is the goal. Is this okay? So here again we have a policy evaluation and policy update. Let's go over the policy update first. Your new policy is greedy with respect to fk plus 1. Okay, this is exactly what we did before. So nothing different. In previous policy iteration, you basically had q mu k here, right? And you took a policy that is greedy with respect to q mu k. But here you cannot get q mu k, but you have an estimate of that, and you take a policy that is greedy with respect to the estimate. Now the question is, how do we get this estimate? So we do it differently. But before I tell you what we are doing, let's first recall what previously people did. So the idea there at a high level was, can we get a good approximation to q mu k? Is this okay? There were multiple, objective functions that were discussed to somehow come up with a good proxy for q mu k. Okay, so one of the ideas, if you recall, was projection. Can I somehow get an f which is close to q mu k? Right? We are doing something different here. What we try to do is, whatever is my current estimate, you try to find a f which is as far away from fk as possible, but at the same time satisfies some inequality like this. Is this okay? So this objective as such, we can play around with, but these constraints are what are more important. Why are they important? Because these are the inequalities that enabled the monotonicity in the tabular setting. These inequalities, came from the monotonicity properties of the Bellman operator in the tabular setting. Right? But when you go to the function approximation setting, the monotonicity of the Bellman operator is not enough to guarantee this inequality at all k. So what we do is, we force this inequality over here. That is, we try to find an f which is as far away from fk as possible, but it has to satisfy this constraint. Is this okay? So these constraints were free in the tabular setting. Here we are enforcing it. Are you with me? And then we repeat the story, right? So this is our new policy evaluation idea. Now let's go a bit deeper into this policy evaluation idea. Okay, so as I said, the goal here is to solve some constrained optimization problem. You try to go as far away from your current estimate as possible. Notice there is a maximization subject to some constraint like this. So let's try to understand what each of these things is trying to do. So this optimization incentivizes moving far away from Fk, okay, as much as possible, which is try to go as far away from the previous estimate as possible, right? And these constraints, what do they try to do? So there are two inequalities over here. Okay, the first, or the second inequality here enforces monotonicity. It says that my Fk plus 1 should be above Fk. It is forcing it, right? You want monotonicity, I am saying you don't get monotonicity for free, force it. So this inequality here forces that monotonicity, and you see that there is another inequality here, and one can see from the monotonicity property of your T mu operator, if you sort of apply T mu to both sides, because T mu is a monotone operator, this inequality will be preserved. That means T mu k to the power 2f is greater than T mu k f. And if you use that inequality along with this, one can see that f is less than T mu k f is less than T mu k to the power 2f, and so on. And if you apply T mu k infinitely many times, you will end up with Q mu k. So this inequality over here means that your f is below Q mu k. So with this interpretation in place, what this optimization problem is trying to do is, it is trying to find the best lower bound to Q mu k. Are you with me? It is trying to find the best lower bound to Q mu k. Best lower bound, because if you try to satisfy this inequality, your f will be below Q mu k. And best because Fk is already a lower bound and you want to go as above Fk as possible. Is this okay? So now one can ask, okay, you may have written this optimization in some fancy way. Is it really doing things different to what was done previously? Okay, so towards that, we tried interpreting this optimization problem from a projection perspective. And what we observed is that this optimization problem can be equivalently expressed as this optimization problem. So notice that there is a max here, there is a min here. However, the max is taking f far away from Fk. Here the min is taking f closer to Q mu k, right? So why are these two things the same? They are same because of these constraints. What do I mean? These constraints enforce f to be a lower bound to Q mu k. So Fk is here, Q mu k is here, f is in between. So going further away from Fk means that you are going closer to Q mu k. That's why, I mean, if you interpret it at that level, this maximization and this minimization are actually equivalent. Now, what is this minimization telling us? This minimization is a projection operation, because here you are saying that you want to find an f which is closest to Q mu k, but we are not trying to find the best projection within the function class. Instead, we are trying to find the best projection within this restrictive class. That is, you want to find an f within your function class that additionally satisfies these constraints. So this is like a constraint projection. So that is how this optimization is different from this optimization, right? In that, we try to do a constraint projection. But this interpretation is true only in the L1 sense. This norm as such can be any norm, right? I mean, our results apply whatever norm you pick with. All right. So now the question is, if you do this variant of policy evaluation, what can we guarantee about reliable policy iteration? Okay. So after looking at this new policy evaluation idea, one may feel that, okay, we are doing something strange. Okay, does it have any connection to what we have done before? If you remember, I said modified policy iteration, okay, has some relation to policy iteration and value iteration. So does this reliable policy iteration also, does it have any relation to policy iteration or not? And the answer turns out to be yes, there is a relation. In particular, when you repeat our idea in the tabular setting, meaning if you take your function class to be the set of all functions, or alternatively your set of functions to be all SA dimensional space, in that situation, one can show that RPI's performance mirrors policy iteration's performance. This is not surprising, because what RPI tries to do in policy evaluation is to find the best lower bound to Q mu k. And when you are in tabular setting, you are allowed to work with any function. So the best lower bound to Q mu k is Q mu k itself. In tabular settings, you are allowed to work with those functions as well. Are you with me? Right? So that's why in the tabular setting, RPI mirrors classical PI. And the other thing we can guarantee is that because we have a constrained optimization problem, one may wonder whether these constraints are feasible, not feasible. We actually guarantee that the iterations optimization problem, I mean, in every iteration, the optimization problem remains feasible. And the most important thing is over here, that the lower bounds or the estimates monotonically improve, right? So the f0 is less than f1 is less than f2 and so on. So the fk's monotonically improve, right? But what do they tell about the true policy? Because we are caring about the true policy. So what we show here is that these fk's are lower bounds to q mu k. So let me elaborate a bit more on that. Ideally, we would have liked if the q mu k's themselves grew. We are not guaranteeing that. What we are guaranteeing is that a lower bound to q mu k, that is actually monotonically improving. Is this okay? So what it means is that while your q mu 0 could be here, your f0 is here, your q mu 1 could be worse than q mu 0, but the lower bound to q mu 1 will be better than the lower bound to q mu 0. So what it means is that the lower bounds get better. It is possible that the policies can degrade, but even when they degrade, they cannot go below what your estimates are predicting. Is this okay? So keep these things in mind. Okay, now one can ask, can we extend similar ideas to the conservative setting as well? And one can ask, okay, why are we interested in conservative settings? Remember that some of the most popular algorithms in reinforcement learning include PPO, TRPO and things like that, which are inspired from conservative policy iteration. But again, the idea of conservative policy iteration has been developed in the context of tabular settings. So we would like to ask whether we can extend those ideas from tabular settings to the function approximation setting as well, right? And one of the questions that I had didn't answer in the previous class was, why should we use conservative policy iteration? Okay, this is a question that we have been asking, and to be honest, we don't have a very good answer. But in one of the papers that we read, I think I've cited it over here, Metalli and all, we made some observation that if you look at the behavior of conservative policy iteration and compare it with policy iteration in tabular settings, perhaps we may not see any advantage. In particular, you can see that the dark blue curve corresponds to policy iteration, right? And then there are some dotted lines which corresponds to USPI, and then there is CPI. So CPI stands for conservative policy iteration, and this is a recent modification of conservative policy iteration. And one can see that both this blue and green dotted curve, okay, do not perform as well as your policy iteration, right? So at this point, our conjecture is that maybe in tabular settings, working with these conservative ideas are not that great. However, the story reverses when you move on to the function approximation setting. So here, one can see that while your policy iteration in the function approximation setting learns or improves quickly, unfortunately, it seems to be settling at a local attractor. Is this okay? You can see that policy iteration rises very quickly, but it settles at a local attractor. On the other hand, these conservative ideas seem to be progressing slowly, but you can see that eventually it is able to escape the attractor that your policy iteration has managed to reach. So our conjecture right now is that perhaps these conservative ideas, while they learn slowly, are able to escape some local attractors. At this point, this is a belief based on such figures and similar stories that we have observed in our lab experiments as well. We would like to know a bit more about this, right? So keeping the motivation of conservative policy iteration in mind, one can ask, can we develop a conservative variant of reliable policy iteration as well? So here again, what we do is we keep the same policy evaluation idea that we had in the RPI setting as before, but now we change the policy update. In RPI, we said, let's go full greedy, right? In the conservative thing, what we say is, can you be a convex combination? I think there is a typo here. This should be FK plus 1. Sorry about that. So can you be a convex combination between the full greedy policy with respect to your current value estimate and your previous policy? Okay, so in that sense, you try to be conservative. And in the original conservative policy iteration, you chose this alpha by maximizing a lower bound on a quantity like this. The difference between this quantity and what you optimized in conservative policy iteration is this thing over here. in the tabular setting, this Fk will actually be Q mu k, which means that you are trying to find an alpha which truly optimizes this performance gap. In function approximation setting, we won't have access to Q mu k. So what we do is, we try to optimize the performance gap with respect to the lower bound on Q mu k. Does that make sense? So here notice that instead of having nu transpose Q mu k, we try to optimize over nu transpose Fk, which is the lower bound on Q mu k. Okay, and we were able to show that this quantity can be approximated again by a quadratic function involving alpha, right? And by solving that optimization problem, one can optimize a lower bound on this approximate performance gap. Okay, so here is such a lower bound that is described over here, and one can see that this performance gap is actually lower bounded by a quantity like this, which is quadratic in alpha. So if you solve for alpha, you will be able to figure out which alpha to choose and so on. And what we observed is that we can actually get some different lower bounds as well. That is, we can get a tighter lower bound as compared to this lower bound, and we were able to see how this differs from the lower bound that is there in the conservative policy iteration paper. Okay, so what we observed is that if we ignore this third term over here, whatever is over here, that has mirror quantities in the lower bound for conservative policy iteration. That is, if you go to this Kakade Langford or this Metelli et al. Paper, you will see terms that look very similar to this, except that wherever you see this little f, those are replaced by Q mu's, which are the true value functions. What we are saying is that these lower bounds now involve the estimates of your value function, right? And in addition, it involves some terms that depend only on the gap between T mu f minus f. So if your f, if it was Q mu, what will this quantity be? If f was Q mu, what would be T mu f minus f? 0. Is this okay? So this additional term would not be there in the tabular setting, but it will be appearing only because of the function approximation error. So what we are able to see is that by actually working on this new policy evaluation idea, we are actually able to extrapolate ideas that were built in the tabular settings in a natural way to function approximation settings, and that actually brings forward several new terms that would have been absent in the tabular setting. Okay, and one can actually derive some convergence rates and so on and so forth, and one can show that here one converges to a ball of a radius whose a ball whose radius is of this order, where epsilon is how well you can approximate your Q value functions. So if epsilon is some bound on how well you can approximate your Q value functions, then one can show that the error decays at the rate of, so I think there is a typo here, this should be K. So you decay at the rate of order 1 over K to a ball whose radius is max of epsilon square, where epsilon is the approximation power of your function class. Okay, all right. So with this in place, we would like to ask, okay, you have some good ideas on paper. Do these ideas translate to something interesting and useful in practice? Okay, so the first thing that we tried to do was, we tried to run some model-based experiments, right? So here we consider two environments, that of inventory control and chain walk. And in these settings, one can see that the model is actually known. When I say the model is known, you know the transition probabilities. Is this okay? So with this knowledge of transition probabilities, what we do is we try to solve that problem in the function approximation setting. Are you with me? So there is a MDP problem. We know the transition probabilities. The state and actions are finite, but we don't try to solve that problem in the tabular setting. We actually try to solve that problem in the function approximation setting. In particular, in this case, if I'm not wrong, the number of states is 50. So it is 50 states and 50 actions. So the SA product is 2500, and we use a function approximation whose dimension is 75. Am I correct? Yeah. And then we try to run a reliable policy iteration idea over here. This is one run of that experiment, and this is average performance over multiple runs. And in this single run, one can see that our RPI's behavior. Okay, this is RPI. The RPI's behavior goes up very quickly and stays there. Is this okay? So now let's try to understand this plot. In this plot, you can see that there are a bunch of algorithms compared, and this is the optimal value that you can reach. And you can see that there is a dotted line and there is a solid line. Okay, let's try to understand what this dotted line is. This dotted line is your critic estimate, that is your FK values, the outputs of your policy evaluation. And this solid line over here is an estimate of Q mu K. Now when you are doing your learning, that is reinforcement learning, you won't have access to Q mu K. What you would have access to is FKs and mu Ks that are estimated based on these FKs. So you will know mu K, you will know FK. How good is mu K? You can only know after some external evaluation. Okay, so since this is finite state action setting, one can actually evaluate it externally, and one can see that the solid line is sitting above the dotted line, which means that the dotted line is indeed a lower bound to the solid line. Are you with me? And one can see that the dotted line is actually very far away from the solid line. So in that sense, our algorithm is not trying to go very close to the solid line. It is trying to remain a lower bound. But despite it trying to be a lower bound, you can see that the algorithm, at least in this simple setting, is learning really fast. Right? In contrast, you can see that for this variant of conservative policy iteration, the dotted line and the solid line are very close, but it is learning very slowly. Is this okay? And here there is a conservative RPI plot also. So while it is able to reach here, you can see that the conservative idea actually proceeds very slowly. Right? Now we tried to use this idea in a slightly challenging problem, which is that of chain walk. And in some runs of these algorithms, we observed something very interesting. Here again, one can see that the green curve goes up very sharply, but settles somewhere in between. Is this okay? This behavior mimics what we saw in the Metelli et al. Paper for conservative policy iteration and this safe policy iteration and all. Right? So there we saw that the vanilla policy iteration learns very quickly, but settles at some local attractor. Right? So here again one can see that RPI goes up quickly, but settles at an attractor, whereas this black curve, which corresponds to conservative RPI, while it learns very slowly, is often able to escape these local attractors and go to a really nice policy. So our conjecture at this point, so I'm emphasizing this is a conjecture because we don't have a solid evidence, the motivation for why you may want to work with conservative ideas would be to escape these local attractors. Is this okay? That is what we conjecture. Hopefully, as we move along, we get more insights. So this is the story in the model-based setting. And then we asked, can we extrapolate these ideas to the model-free setting? So at this point, we said, okay, let's just try some heuristic ideas and at least see, are we seeing some promise over here, right? So the first question that one would like to ask is, we have a constraint optimization problem, right? How do we solve this constraint optimization problem when you only have access to the model? When you have access only to the samples. Is this okay? You interact with the environment, collect samples, you don't have access to the transition probabilities. Using only these samples, how can you solve this constraint optimization problem? So before we try to understand that, let's find out the issues. In order to solve this in the model-free setting, the challenge is that we don't know T mu K, okay? Because T mu K involves the knowledge of P. The second thing is the more important part, which is that this is a vector, this is a vector. Okay, so both these are vectors which are living in a SA dimensional space. So there is an inequality over here, which means that if you look at the inequality at a coordinate-wise level, you have SA many constraints. Is this okay? So this is actually a very problematic thing. It is problematic because while your function approximation class may have a smaller dimension, the number of constraints is very large. Is this okay? So the question is, can we handle these constraints in certain way? So our heuristic idea was that, as is done in standard constraint optimization problems, what we do is we took this constraints, put it as part of some penalty function and moved that weighted penalty function to the objective. That is, you do like a Lagrange multiplier operation, move the constraints to the objective by adding some weights. Is this okay? So we come up with a weighted penalty function. So now you convert this constraint problem into an unconstrained problem where the constraints sit as part of some penalty function, right? And then we use some standard deep RL tricks wherever there is this team UK, you replace the expectation that is present over here with samples and use some standard deep RL tricks, and you somehow come up with an algorithm. And we then tried running this algorithm in some simple experiments. The first of that was this Cartpole setting, okay, and the goal here is to balance this pole, right? The key thing to keep in mind here is that the action space here is discrete. So in this setting, we wanted to ask how well does RPI behave, okay? So here is the performance of 4 algorithms, and for each of these algorithms, one can see that there are 2 colors that are present, the solid curve and the dotted curve. The dotted curve is what you will observe during training. You will use those dotted curves to figure out a policy. Once you figure out that policy, you can externally figure out how good is that policy. So you have to get this solid curve by doing some external policy evaluation. Is this okay? During training, you only have access to the dotted lines, but after you get hold of all the policies, you can do an external evaluation and get hold of this solid trajectories. And keep in mind that the solid trajectories are what matter at the end of the day. The solid trajectories are obtained by the policies learned, and the policies that are learned using these dotted lines. Are you with me? Right? So in these 6 scenarios, one can see that there are some numbers over here. This number represents the number of neurons that we use in our neural network. So which means that we start with a poor neural network here and we go to a rich neural network over here, right? Now let's try to see what happens over here. And before that, let me just explain what do I mean by RPI DQN, right? So in DQN, there is a policy evaluation line of code. Okay, there is a bunch of code in that algorithm which concerns policy evaluation. And DQN's goal is, can you come up with a close approximation? What we do is we remove that code, replace it with our code, where the goal is, can you find a lower bound to the true value function and enforce this lower bound to grow. Okay, so we somehow incorporate both these ideas here and try to do this. And so this RPI DQN means that you take this DQN's code, take the policy evaluation part of that code, replace it with the policy evaluation that is part of your RPI. Is this okay? So that is how you get RPI DQN. And rest all parameters of RPI DQN and DQN are the same. Okay, so now let's compare the performance. So what happens with DQN is the solid curves goes up, which means that initially it learns, but later on you can see that it actually starts coming down. And what is surprising is that the dotted line actually keeps going up. Is this okay? So during the training part, you will only get to see the dotted curve. So if you see the dotted curve going up, you may perhaps be very excited, as anyone would be. Oh, the dotted curve is going up, I am learning. But you can see that what is actually happening, the solid curve is actually coming down, which means that the true value function is actually deteriorating. Right? And in contrast, once you replace that DQN's policy evaluation with our idea, on one hand you can see that the green dotted curve tries to move up, and the solid curve is sufficiently far away from this or non-trivially far away from this. So it goes up like DQN but stays there. It is not coming down. Is this okay? So that is the key thing to observe. While DQN also initially learnt a reasonable policy, it let go of that policy. Our algorithm in contrast is trying to hold on to that policy. Is this okay? Now let's see if a similar story unfolds here as well. Again, you can see that the dotted lead curve goes up and the solid curve goes up and then comes down, and you can see that more or less the story is similar, but the story, the performance stabilizes when you sort of move to richer neural networks. In contrast, by just changing the policy evaluation in DQN, one can see that we have a more robust story across a multitude of function approximation settings. And in all these examples, we saw that PPO actually does a very good job. So this is the purple curve over here. It actually does a very good job. And we can see that DQN, which was not doing very well, once you replace it with the RPI DQN, it is able to match in performance with PPO. So we then said, okay, can we use this idea and try out some slightly more challenging setting? So we went from Cartpole to inverted pendulum. So here is the inverted pendulum environment. the difference between Cartpole and inverted pendulum here is that in Cartpole, the action space was discrete, whereas in inverted pendulum, the action space is continuous, because here you have to decide what is the force that you need to apply to this cart here. There you just had to decide whether you want to move left or right. Here, in contrast, you have to decide the force that you have to apply, which makes this problem more challenging than the the Cartpole setting. And here again, we observed a very similar story. So you can see that because of the continuous action setting, we are now forced to work with a cousin of DQN called as DDPG, right? And we take the policy evaluation part of DDPG, replace it with the RPI idea, and call the new algorithm as RPI DDPG. And then we compare its performance with DDPG's performance, and also the performance of other algorithms in this scenario. Here again, the dotted line and the solid line have similar interpretation. And here again, one can see that the solid line monotonically improves, and the solid line is able to go up very quickly and stay there, right? And in contrast to RPI DDPG story, you can see that PPO's performance, which is run using the hyperparameters that are standard, right, from the stable baselines 3 setting, one can see that PPO's performance in contrast is very oscillatory, right? And it is not really able to find a good policy, at least in the experiments that we did. So then we said, okay, can we try out some more ideas? And a couple of weeks back, my students actually managed to show some improved performance over DDPG in the more challenging Mujoko environment as well, right? So here are different environments that are part of this Mujoko suite, right? And here we said you take DDPG, which is represented in green here, replace the policy evaluation with the RPI idea, and we call this as the the RPI DDPG algorithm. And we tried comparing the performance of the red curve with the green curve over here. And in certain situations, observe that the green dotted curve, okay, actually races off, but still the true performance is very poor. Is this okay? So the green curve here represents DDPG. So the estimate is very high, but the true performance is actually very poor. Is this okay? In contrast, in our case, the red dotted line stays below the solid curve. So the dotted line seems to be growing up and holding on to its value. And while the solid curve, goes up and down, you can see that it comes down, but it tries to stay above the dotted line. Okay, so this is very important. While the true performance could degrade, if you implement our algorithm correctly, the hope is that the degradation will be up to the lower bound, not below it. That is the hope. And these are initial evidences of that. So again, I would like to highlight that our algorithm will not prevent collapse, but it is going to control that collapse. It is not going to lead to a complete collapse like what happens over here. Okay, it can collapse, but the hope is that we stay above the lower bound over here. And the difference between this implementation and the previous implementation is that, if you remember, there is a Lagrange multiplier, and in the previous setting we were able to work with one Lagrange multiplier. Here in contrast, we had to adaptively change that Lagrange multiplier depending on how many constraints were being satisfied. Okay, so we had to make this modification in this more challenging situation to show that in all these 5 environments that are part of Mujoko, we are actually able to significantly outperform the DDPG story, right? And then we asked, okay, if we incorporated the conservative policy iteration idea, conservative reliable policy iteration idea, and come up with a PPO analog, would we be able to see some better story in terms of performance collapse, right, with regards to PPO? So these are very initial experiments. I mean, this is like initial promise, but we are not there yet to confidently say that we are able to address the performance collapse that is there in PPO. So let us try to understand the difference between these two algorithms. PPO over here, I mean, the blue curve over here corresponds to PPO, and the green curve over here corresponds to CRPI PPO, which means that you take the PPO code, wherever the policy evaluation is being done, you replace it with the RPI idea, and wherever the policy update is being done, you replace it with the conservative policy update idea. Okay, so you get the variant of PPO in this fashion, and we try to compare it. Now the surprising thing that we observed over here is that on an average, the dotted line and the solid line actually go hand in hand. Okay, so the solid line and the dotted line are going hand in hand, meaning the critic is actually able to get a very good estimate of your true value function. Is this okay? On an average, the critic is able to get a very good estimate of your value function. Despite that, one sees that there is a performance collapse. Is this okay? So far, the philosophy in reinforcement learning is, can I, come up with a better function approximation class, or by, maybe playing with my neural network, so that I'm able to get these value function estimates accurate. But what this story says is that even if you're able to get accurate estimates, you won't be able to prevent this performance collapse always. I would again like to highlight that we are not saying the performance collapse will always happen. All we are saying is that we don't know when the performance collapse could happen. That is what the challenge is. Because if we are unsure, we will be uncomfortable deploying such algorithms in more challenging problems. Do you agree? Right? So you can see that even though the critic estimate and the true evaluation are hand in hand, we can still see a performance collapse. But in contrast, in the CRPO PPO story, one can see that the lower bound, even though it is not very close to the true estimate, is able to hang on to there, and the policy evaluation, the true value function is above this. So one can see that it learned this policy over here and is able to hold on to that policy. It's not like PPO didn't learn a good policy. It went to a good policy, but it is not able to hold on to it. Right? So ideally one would say that, or one would hope that by running the training for more times, by putting in more data, the hope is that we can get better and better policies. Right? But what these algorithms, plots try to show us is that even if you put in more training time and more data, it is possible that there could still be a collapse. Right? And our algorithm is some attempt from our end to hold on to the good policies that you may have discovered. So this brings me to the end of this talk. Okay, so let's try to understand the takeaways and open questions that are there. So at a high level, we discussed the idea of reliable policy iteration and conservative reliable policy iteration. And the key thing we wanted to ensure was a sense of monotonicity. Ideally, we would have liked the value functions to monotonically improve, but in function approximation space, we believe that is too much. So what we instead ask is, can we ensure some monotonicity on the lower bounds to the true value function? Okay, so that was what was the motivation behind these algorithms. And the nice things about these algorithms is that you can take the policy evaluation that is suggested by these algorithms along with the policy update suggested over here, and we found that we could take this and readily incorporate it in existing pipelines. At least we were able to manage to do that in some of these algorithms, and we see that at least in beginning experiments, we are already able to see that the performance is better than the vanilla algorithms. Okay. So now what are what is left here? As I told you, the guarantees for RPI, CRPI at this point in time are in the model-based settings. We would like to extend the theoretical guarantees from model-based settings to model-free settings. That is one of the key goals that I am interested in. And then, PPO has led to several interesting developments for LLM fine-tuning, right? And it has played a very, very key role. In particular, it has led to the development of this algorithm called as GRPO, right? So the question that we would like to ask is, if we can somehow ensure that some of the challenges that are associated with PPO, we are able to address by incorporating some of these reliable policy iteration ideas, would we be able to build better algorithms based on that for LLM fine-tuning as well? Okay, so with this, let me stop. Thank you. So I think I have time for a few questions, and after that, I would request my students to come and set it up. You can perhaps already do that, okay? I'm happy to take more questions if you have. Yeah.
Function, but here we are going towards the lower bound, which means the tail distribution of the value function is also kind of, there is some sort of constraint that is
I mean,
enforcing
so maybe I'll give an answer in two ways here. Okay. The first thing is that this is not in the risk sensitive setting at this point, because the lower bound that we are seeking is the lower bound to the Q value, which is the expectation itself. Is this okay? So there is no notion of, I believe you are talking of quantiles and things like that. So we are not in the quantile setting at this point.
Yeah, I understand that, but are we going towards that kind of thing?
At least that's not our motivation right now.
Okay.
So the goal is not to go to a risk sensitive type philosophy. Rather, the goal is whatever is the current philosophy, which is that of doing reinforcement learning with function approximation, where the goal is to find a better policy, or to learn. Right? And learn means you want to get a better policy. And can you do that? And that better policy still is defined from an average or expectation perspective itself. The definition of what constitutes a good policy we are not changing. We just want to ensure that can we reach there reliably in a function approximation setting. Okay, but having said that, let me try to give you a second answer to this question. Can we extrapolate these ideas to risk sensitive settings? And the answer is, if you see at the heart of all of this, the key role was played by the monotonicity of your Bellman operators. So if you have a Bellman operator in the risk sensitive setting, which also has this monotonicity property, the definition of these operators don't matter. What matter is the monotonicity. If the monotonicity property is there, then our ideas will extrapolate to that setting as well. Okay?
Thanks. And also in the training, the variance of, I think that shaded portion is the variance, confidence interval.
Yes.
I think that is also looking better
in certain scenarios. I think, telling confidently about that variance, I think we are not there yet. Okay, in certain scenarios, definitely the variance seems to be very good. But we also saw certain situations where the variance was not that good. So I think we are still not there where we can confidently say that this idea actually reduces variances.
Because I
and
was
things
trying to link towards that, towards the CLT theorem, where when we are trying to focus that empirical mean, taking care of the lower bound of the empirical mean, it is something like we are kind of shrinking that normal distribution.
Yeah, so I'm not sure if I can confidently say that it helps with the variance yet. I don't think we have.
Kind of trying to relate it where the variance was low.
I see. I don't know. Okay, let me put it that way. Okay. Yeah.
My question was regarding that how you related that first point of n times Bellman operator to the conservative policy. Like, how does that?
No, I related that to value iteration and policy iteration, not to conservative policy iteration at that point. Is this okay?
Okay. So in the model free setting, which is the sample based setting, you said that you're using the constraints based on some Lagrangians, right?
So I mean, the typical idea of how you fold a constraint into the optimization problem is to take the constraints, right, put it in the objective and multiply it with some weights which you refer to as Lagrange multipliers. So typically one would need to figure out these Lagrange multipliers as well. At this point in time, we are heuristically deciding what these Lagrange multipliers should be. So in the initial experiments, the Lagrange multipliers were heuristically decided, but they were kept fixed. In the some of the remaining experiments, we saw that these Lagrange multipliers need to adaptively be modified as well. Sometimes they need to be less, sometimes they need to be high, and that is important. Because the Lagrange multiplier being very high at some level means that you are respecting the constraints more, and if they are very low, you are sort of saying, okay, more or less all the constraints are okay, you try to, get a better value function estimate. Is this okay? So it's like, holding the learning part and allowing the learning to happen. When you are confident that all constraints are met, you want the algorithm to learn quickly, but when you are unsure whether the constraints are being met, then you want the algorithm to slow down its learning so that you can focus more on ensuring you go to a region where the constraints are satisfied. Is this okay? So, yeah.
The Lagrangian, is it over a sample of state action pairs, or is it something you incorporate in the model itself?
I mean, the Lagrange multiplier and the model are not connected. We implement it in the algorithm itself, right? So at this point, we have a scalar Lagrange multiplier. So ideally, we should have a Lagrange multiplier for every constraint. But right now, we are working with a scalar Lagrange multiplier.
Is it a sample or just?
I mean, it's a scalar whose value we adaptively change. I think some of these details would you discuss in this thing? Okay. Okay, so I think he will give some more details of this hands-on, during the hands-on session. Maybe you can ask some of these questions after that hands-on session. Okay. Okay, I think this brings to the end of my talk. Thank you. Maybe we'll allow them to continue. You can ask me during the break. Okay.
No. Okay. So am I audible? Yeah, so we'll be starting with the tutorials. So in the first 1 hour, in the first half an hour of the first tutorial, we'll introduce you to Q-learning. We'll demonstrate Q-learning in 2 environments. And then Ishwar will come and present like the limitations of Q-learning, and he'll show how DQN works, and then we'll demonstrate our algorithm, which solves certain limitations of DQN as Professor discussed right now. So you can go to our RL workshop website, and at the top there will be the simulation links. So you can go there and you can download you can open the Jupyter notebooks, and you'll see them in the Google Colab, and then you can follow along like with me here. So just a quick recap. So in the reinforcement learning problem, so this is our main loop. We have an agent. The agent interacts with the environment and it gets some rewards. And its goal is to maximize its rewards over the entire trajectory. So we model this loop in the form of a Markov decision process, which is essentially a 5-tuple. So you have a set of states, you have a set of actions, you have the transition probability distribution, you have the reward function, and you have the discount factor. So the first thing we have to do is to implement this programmatically. Now we'll not be doing model-based setting here. We'll directly go to model-free setting, and we'll implement the Q-learning algorithm. So this is the main RL loop. Now in any RL algorithm, so in any reinforcement learning algorithm, this is the core crux of what you actually have to implement. So if you notice here, the agent at times t equal to 0, it will have an observation from the environment S0. And then the agent will take an action A1 that will lead the environment to change its state S1, and it will return you and reward RT plus 1. So that is what we'll implement here. So you'll start with the environment here. Then you will ask the environment to give you the first state. Now, based on the current state, you'll get an action from the environment. Then the environment will simultaneously act that action in the simulator, and the simulator will give you the next state, and it will also give you the next reward. Now, in case the episode gets terminated, it will return a terminated flag as well. And in case it's not, so it will be 0, basically. And then once you get the state, then you may either learn or you may continue collecting data. So it depends on the algorithm. And so this is the entire loop. You collect states, take an action, you either perform some learning task, and if it gets terminated, you end the loop. So we'll start with this simple grid world environment first. So in grid world, it is a finite state, finite action environment. You have 5 rows and 5 columns. So you have in total 36 cells here, and these cells are of 3 types. So this one is the goal state. Now when you enter the goal state, you will get a reward of +5. And these are dead states. When you enter a dead state, you'll get a reward of -3. So the goal in this environment is that the agent will start in any state, and it has to attain the maximum reward it can get. So you have 4 actions. In each state, you can either go up, you can go left, you can go right, or you can go down. Now observe that at the corner states, certain actions are not possible. Say for instance, in state 0,5, if you take a right or a top action, that will move you out of the grid. So in that case, what we do is we penalize the agent if it tries to move outside and give it a negative reward, so that it learns not to exceed the boundaries of our grid. And so this is our agent. So this is the code which actually generates this grid. I'll be just skipping over it, so you can. We have to sign in. Just a second, we'll sign in. We didn't know. Do you have the Google account?
Should I give leave?
Yeah, you can just sign in Google once. Okay. Sorry for the interruption. Yeah, so we'll run the create grid function first. I'll not be explaining this function. You can just look at it yourself later. This is just the geometric aspect of creating the grid. So this is how we represent the grid as a class in, say, Python. So we define our actions in the form of a list. We have 4 actions. Then we assign each action a numerical value so that our algorithm can actually use it. Then we define our grid here, number of rows and the number of columns. We define the states that we want. So, and then we create the grid. And here is the function that will reset the environment. Like once the episode is terminated, you will go back to the original state. And this is the step function. So here the agent will simply take the action and it will execute the action. So if the action is, say, up or down and it is valid, you'll change your state. And if it is invalid, you'll get different rewards based on the actions. So here is the sample grid we'll be working with. You have 3 goal states here, which will give you a positive reward, and you have 5 like death states here, which will give you a negative reward. And the agent's task is to maximize the overall reward, and can start from any position. So we'll start with the Q-learning algorithm. Now, if you recall, the Q-learning algorithm, this is the simple update which we have to implement for the Q-learning algorithm. Now, what you have is a Q table. So a Q table is basically a lookup table of size, states, comma, actions. So I'll show you one lookup table here. Now observe, our rows are each state is 1 row. So if you look, we have around 36 states. So we'll represent each state, say 0 by their cell numbers 0, 1, 0, 2, 0, 3. And that will be represented in the Q table. And simultaneously, we'll have each action for each state. Now we initialize the Q table initially as zeros, all zeros. So each action will have an equal probability of being picked. You can initialize it randomly or some other way as well. It doesn't make a difference. Now this is the queue table, and now what will happen during the update rule, if you notice, is that the agent will select a max action from the queue table. So based on the current state which you have, what the agent will do is, it will look at the queue values and it will simply pick the action which corresponds to the maximum queue value. So this is basically the core thing of what we have to implement. And again, we'll incorporate our this queue algorithm inside our original RL loop, which I showed previously. And that you can see here. So this is our queue learning algorithm. We'll initialize the queue table. We'll get an environment. And we'll define a few hyperparameters. So gamma is the discount factor that will basically control whether you want to look at short-term returns or you want to look at long-term returns. So if the gamma is small, the agent will focus on immediate returns. It will try to maximize its immediate returns. However, if the gamma is larger, it will try to maximize returns over the entire trajectory. Then you have the epsilon parameter. The epsilon parameter typically tells you like how much, it's basically the parameter controlling the epsilon greedy policy. And it will tell you like how frequently should you take a random action for exploration and how frequently should you exploit. And so this is the main algorithm. We'll initialize the queue table with zeros. We'll get a state. We'll take an action using the epsilon greedy policy. Once we get an action, we'll simply implement our queue learning update rule, which is shown here. We'll exactly implement this same thing. If you notice, this is existing queue value plus learning rate times the TD error. So here what we have is, we get the action. Based on the action, we get the next state that we'll achieve. We'll define our learning rate here as 1 by n. Then we'll simply update queue table here. And that is our algorithm. Now we'll implement this algorithm on the queue table in two settings, in the finite horizon setting as well as on the infinite horizon setting. And we'll see how the policy actually differs in both cases. So in the finite horizon setting, if you notice, I've just run the code. Now by finite horizon, we mean that once the agent reaches a goal state, it will stop acting. So like it will just terminate. Yes, so this is the optimal policy in this grid, if you notice. The left grid will show the optimal queue function values for each state, which is basically the expected reward you can get. And this grid is showing you the optimal policy. So basically, if you are in this state, you should take the right action to reach to the goal as quickly as possible and get the maximum rewards. So if you notice in the top right corner, the agent is trying to reach these two goal states, whereas in the bottom left triangle, the agent is trying to reach the bottom left state. Because this is an episodic environment, so it has to reach a goal state as quickly as possible. Now we'll do the same thing in an infinite horizon setting. Yeah, so here in the infinite setting, you will see the policy of the agent has changed. Now, because here on the left is the optimal queue function, and on the right you can see the optimal policy. Now here the dynamics are different. Once the agent reaches a goal, it can still continue acting in the environment. So the optimal policy here suggests that the agent should reach to the top right corner because you have two goal states. And once you reach one of the goal states, you can just alternate between those two goal states continuously until the episode ends. And so in that way, you can net the maximum award. So if you compare this setting with respect to the previous setting, earlier we were going to the, in the bottom left triangle, we were going to the bottom left state because that was the closest state possible to get the maximum reward. But here in this case, the agent instead tries to avoid this state and goes to the top right corner, even though initially it may net some like a few less rewards as compared to the previous setting, but in the long run it will have a higher chance of getting more rewards. So this is the optimal policy in the second case. Before I move on, do you have any questions? Okay, so now we'll see another different environment. This was a continuous state and this was a finite state and finite action environment. Now we'll look at the Cartpole problem, which has continuous states but finite number of actions. Now this environment is a bit difficult for Q-learning to run on because if you remember, in Q-learning you need finite states and finite actions. However, we have infinite states here. So I'll describe the environment first. So in Cartpole environment, basically you have a cart and on that top of the cart there's a pole. So the environment basically gives you the state gives you 4 different information about the environment. You have the cart's position on the x-axis, its velocity. Then you also have the angle that the pole makes with the vertical, along with the angular velocity. And your goal is to simply move the cart in such a way so that the pole stays upright as long as possible. Now, because this is a continuous environment, so there have been the environment's bounds have been defined in a certain way. So the x-axis has to be between minus 4.8 to 4.8, and if the agent tries to exceed those boundaries, we'll simply terminate, because that is not where, because in certain cases you'll observe that the agent simply tries to run as fast as possible towards one of the ends to keep the pole upright and attain rewards that way. And so we have certain bounds here. And you have 2 actions. Either you can push the cart to left or you can push the cart to right. You cannot exert force, you'll exert a uniform force in this case. And you'll get a reward of +1 each time step the pole is upright. So here in this case, you can get a maximum reward of 500 because we allow the agent to run the environment for 500 time steps. And you need to basically keep it alive, keep the pole upright as far as possible within the bounds defined. Now the issue is that our state space is infinite. So we cannot represent it in the form of a Q table because the number of states are infinite. So what we do is we discretize our state space. So we suppose for the pole angle, we have defined a range of values. Now we divide that range into n buckets. So suppose we'll define buckets as in say 2 degrees each. So you'll have around 15 buckets, you'll have around 13 buckets here. So minus 12 degree to 10 degree angle will be a single bucket. So any angle, any state that falls within that angle range will be assigned as the single bin value. And the value, and this is how we'll represent our state space in this case. So since our state is a vector of dimension 4 and we are discretizing it, so suppose we define 4 buckets each, so you'll have 4 to the power 4 states here in this case. So, yeah. Now here we'll have another different trade-off. If you have less number of bins, the agent will not be able to control the cart as precisely as possible. However, if you have more bins, the agent will be able to control the cart, but the size of the Q table will increase exponentially, and that is what we'll see in the experiments. So this is the discretized function that, just a second. Yeah, so this is the discretized function. It will simply take a state and it will give us the bins, the output. It will output the bins in which the current state lies in. This is done by the numpy's digitized function. Then here we are using the same Q-learning algorithm as was defined in the previous setting. In addition to that, we are defining bounds on our agent. so that if the agent exceeds those bounds, we'll simply terminate the environment. And the rest is the epsilon greedy policy and the queue function, which is same as defined previously. Our training loop is also same. You take an action, you get the next state and the reward, and you'll update the queue function. In addition to that, we define an evaluation function. So to evaluate an agent, like during the training time, the agent is both exploring and exploiting. So it might take some actions randomly. So to accurately assess the performance of the agent, what we do is we use a deterministic policy. So during the certain time steps in training, we'll stop our agent from training, and we'll evaluate the agent on, say, 100 new games, and we'll ask it to place policy on those games and see what the average reward it attains. So the next two are just the plotting codes. So we'll run the Q-learning algorithm with discretized state space on the Cartpole environment with 1,000 steps, 1,000 episodes. So the agent will play the game 1,000 times, and each game's length will be around 200. So either it will stay up to 200 length, or if it terminates below, we'll just stop the game there. And so we'll start with 2 bins. Basically, if the pole is towards the left, that is 1 bin. If the pole is towards the right, that's 2nd bin. And we'll just run the code once. So you'll notice that we are simultaneously printing what rewards the agent is achieving over the previous over the previous 10 time steps. Now these rewards change because during training, the agent is exploring as well as exploiting. So it might be possible that the performance improves. However, in certain states, the agent took a random action that accidentally made it made its behavior worse, and then it collapsed. So here is, for example, a training curve. You can see how the agent evolves over the training time. So initially, it doesn't know anything about the game. However, as training progresses, it slowly learns. However, since the exploration is still active, you might observe these ups and downs in the curve. And here is the policy which the agent has learned. So if you notice, the agent is not able to properly control the cart here because we only have 2 bins. You cannot exert proper control here. Now let's go to 4 bins. Now in the case of 4 bins, I'll just show the results we have here. We have a similar issue here where the agent is unable to run the cart. However, it is getting better rewards as compared to the previous policy. And we'll do this for 6 bins and 8 bins as well. So this you can observe. Now here the policy is slightly different. The agent has learned to just move towards one side of the screen while trying to keep the pole upright as long as possible. And for the 8 states and the 10 states case as well, we'll do the same thing. Now what we'll do is we'll plot the performance of the agent versus the number of bins. Now here you'll observe a somewhat surprising thing. Now what we are usually, what we'll assume is that as we increase the number of bins, the agent's performance should improve because it should be able to exert a more fine control over the environment. However, that is not the case here because if you observe, the size of the queue table increases exponentially as well. Now, we are keeping our training budget fixed here. The agent will play for 5,000 games. So if the number of bins are small, that means that the number of states is small. So the agent gets more chance to explore those same state spaces over the training time. And thus it can form more accurate queue estimates of those states. However, when the number of states are large and the training budget is small, same as what it was previously, you may not be able to explore all the states as well as you were able to do it previously. And thus it may happen that because in ideal case, usually it should be able to explore infinitely often to get proper rewards. However, that is not possible in this case here. And so you see this performance dip here. Now it might be possible that the code which you are running, you might not observe this exact same thing And that is basically owing to the randomness of the agent and the epsilon policies and other stuff. So this basically motivates us to move to function approximation, and there are several reasons. The first reason is the size of the exploding Q table. Now suppose if we are in a more complex environment, such as a Mujoko, say, a cheetah environment or a humanoid, in those settings you have, say, 18 or 20 states. And then if you want to, suppose, discretize each of those states in, say, 100 bins, you will have somewhere around 20 to the power 100 states, which is simply impossible to fit in. And the second thing is, if you notice, when we are binning our agent, suppose if you are at the boundary of some bin, the states which are, say, like, suppose the bin boundary is 10, right? And suppose the angle for the bin boundary is 10 degrees. Now, what we would expect is that the state at angles, say, 9.9 degrees or 10.1 degrees, and their Q values should be quite similar. However, when we bin it, we are losing that information as well. So that is the second thing which is an issue. And so this motivates us to go for function approximators such as neural networks, and that is what Ishwar will show in the consecutive part. Thank you, and this is all from my side. Do you have any questions?
Hi everyone. So let's go to the DQN notebook. So let's go back to the simulation links. Let's open this third link. So while I talk, maybe I'll just put everything to run so that we will have some output by the time we come to that cell. So let me just run all. Okay. So thank you, Girek, for introducing this Q-learning. And as he mentioned, so the Q table will actually exponentially grow even with binning. So it is not a very feasible idea. So that is when people from DeepMind actually proposed this idea called a deep Q network. So basically what they do is they replace this Q-learning table with a neural network. So basically the Q table will have an entry for each state action, and the output will be like you just observe the Q value. Instead what they did is they actually replaced this table with this neural network, which takes an input as state, and it gives out the like the Q values for every action. So if you observe here, the states are maybe infinite, but the actions needs to be finite, because I mean the output of the neural network needs to be like, say, some finite number. So this kind of setting can be applied to environments where we have like infinite or like large number of states, but the actions should be like, say, finite or say in limited number. So this was like a revolutionary idea. Actually, we can see this algorithm lead to some superhuman performance in Atari games. So let me just show you a small video from DeepMind. So this is a game called Breakout. It is a game in like, say, Atari suit. I think most of us would have played this game in our childhood, right? So basically in the starting of the training, if you see the agent is actually struggling to learn. So in the first 100 training episodes, if you see the agent is somewhat managing, but like it's not able to play that well. And as the training progresses, so you see there is some kind of learning happening. Now it has actually sort of learned to play at some good level. So at this point is when the agent actually figures out there is some clever way of playing this game. So basically what it understands is let's create a small tunnel, and then let's pass the ball through the tunnel so that it can actually capture more number of bricks. So I think this is what they have observed. So let's see. So it just created a tunnel to the left. Yeah, so it tries to pass the ball through that so that it can gain maximum number of, let's say, points. Yeah, so while training these kind of agents need a lot of compute, which will not be feasible for us to do it in such a tutorial. So what we will do is we'll come back to the same Cartpole example, which our friend was just discussing, where he discretized the state space and so on. So let's now not discretize the state space, but use this DQN idea and see how it performs. So in that front, what we do is we use these packages called Gymnasium and Stable Baselines 3. So Gymnasium is an OpenAI, it was built by OpenAI, and then it is now given to a Pharma Foundation, if I'm not wrong. So they actually have some benchmark environment. So if you have a new algorithm and if you want to test how your algorithm performs compared to other algorithms, then you can actually use environments from this suite and you can benchmark your algorithm. And also there are this, so if you want to, like say, if you have a new algorithm and if you want to compare against others, you actually need not code all of the famous algorithms. Many of them are coded and like say well tested and maintained in these packages called Stable Baselines 3, and there are a few more like CleanRL and so on. So we would like to expose you to such like say APIs in like say Python, and these packages actually have some evaluation techniques, but it did not have like the kind of evaluation what we wanted. So in our previous talk where Professor Gugan showed that we have a lower bound, we want to track the critic estimates and so on, right? So they are though they are all been in the algorithm, like explicitly we wanted to create our own evaluation script and so on. So we have coded an evaluation script, and which we have just downloaded from our repo here. And then here we include all the required packages, and then we start off with the training here. So we would like to show you the performance of DQN on like say on a rich neural network and see how it performs, and then we go on to the smaller neural networks and so on. So each of this algorithm actually has been fine-tuned. Basically, every algorithm will have like a lot of hyperparameters, and they actually need tuning. So most of the like say famous algorithms and these benchmarks have already tuned parameters, and which are available on this Stable Baselines 3 zoo. So this repository contains all the fine-tuned hyperparameters for most of these famous algorithms and environments. So let us pick all the best hyperparameters available for DQN from this repository, which are these basically. And then we will train for say 50K time steps, and we will evaluate every 5,000 time steps. So the core idea here is to first create an environment, and then you just seed them so that you can have reproducible results, which is actually very important in like say research. So whenever we actually want to like say publish some like say tables and like say plots and everything, it is a good practice to have this reproducible results. So always seed your experiments so that they are reproducible how much ever possible. So we seed these environments so that for reproducibility purposes, and then this is the main training loop. So if you see here, we haven't coded any of this DQN algorithm. We are using the package Stable Baselines 3, which has this DQN like say coded up. So we are just using that for now, and we will run our like say training. So basically this is the we are just integrating our evaluate loop here, basically the evaluation script which we have written, and then the model.train will actually start training the model. So I think by now it should have done with the training. Yes. So we are plotting the thing. Okay, so basically now this is not like any discretized one. This is actually coming from this neural network. So we have the x-axis is the time steps. Like say we have given it a budget of 50K. Oh, okay, there is I think a small typo here. It is 50K. And then we have plotted the discounted return along the y-axis. So if you see the dotted line and the solid line have like no correlation, and then it can actually overshoot, and the policy value can actually be very small, but the critic can actually be saying it's actually good. So sort of this critic and the true policy value actually are not much correlated in this sense. And also if you see, it's actually overshooting even the maximum possible value. If you actually run it for longer, you can see that it is growing way too high. I think in the next plots we will be able to see that. So since the episode length is 500, the maximum discounted return an agent can actually achieve is roughly around 100, like 99 point something. But if you see, the critic is actually crossing that already. So this is like the beauty of DQN. Like you need not have to maintain a large table and so on. Like now you can actually work with continuous states, with finite actions and so on. Now let's see, there are some issues with DQN. Basically why DQN works is like the theory is there for tabular setting, and then work. So the hope is that when we have a very good, like say, neural network or function approximation class, which can be close to tabular or very good in a sense, then we have seen this, like say, DQN kind of algorithms will play good, will work well. And there is also a very common issue of this overestimation in DQN. So that's when double DQN and other algorithms were proposed. I think I encourage you people to look upon these things. I mean, what is overestimation and how people are, like say, coming up with solutions to this overestimation and so on. And it can also oscillate or even suffer performance degradation, like our Professor Gugan Tope has shown in his talk. So now let's, what we do is let us reduce the function approximator's capacity from 2 layers of 256 neurons each. Let us come to like 8 neurons of, 2 layers of 8 neurons each. And now let's run the same, like say, algorithm. So it's just like a copy paste of the previous training code, but now it's trained on a much smaller neural network, which is of 2 layers and each with 8 neurons. So if you can see here, so initially there is some learning, but after some time it actually like say collapses, and I mean like it's at 0. I mean like it is not learning anything. And if you see, the critic is also like overshooting and overshooting. So the key factor to keep note here is this solid line is only coming after you evaluate. So after frequent like say time steps, you take the whatever is the learned policy and you evaluate separately, and only then you get this solid curve. But this dotted curve is what is your critic. So this is what you can actually observe always. And this has like no correlation with what is the true performance. And it is actually saying you are doing so good, where the actual reality is like you are very, very bad. I mean, so this is when we actually propose this reliable policy iteration. So let's just recall policy iteration. So here we have 2 loops. I mean, in every loop we have 2 steps. One is like the policy evaluation and then policy improvement. In the policy evaluation step, we actually compute the true Q values. And in the policy improvement, we actually try to find the greedy policy with respect to this Q function. And this actually has this very good theoretical guarantees of monotonic improvement, and it will actually converge to like the Q star and so on. Now what we have done is the proposed method of RPI, which is designed for function approximation. So even here in every loop, we again have 2 steps. One is the policy evaluation step and the policy improvement step. So the policy improvement step is exactly same as what was there in like the classical policy iteration, but the evaluation step is now modified to the new constraint optimization problem, which we have actually proposed. So with this, we have this following guarantees that for every iteration there is the constraint optimization is feasible, and also we have a monotonic improvement in terms of the lower bound. So we have this critics which are actually improving, and we have a guarantee that our true value function would be above the estimate. So in some cases, when you actually have like a environment where you are satisfied when you get a reward of say 500, and if the critic coming from our algorithm is actually reaching 500, then you can reliably stop your training and say, okay, my true Q value would be above 500. So this kind of signals are missing in current algorithms, but we try to fix that in some sense. So to have a model-free extension, so what we do is, so this is the objective which is under consideration. So we want to replace this with samples, because we will not have like the access to TMU, and there are SA many constraints here. Like Professor Gugan actually mentioned in his talk, though we are working in a D-dimensional like say function approximation class, we still have TMU F greater than equal to F constraints. Basically, this F is an SA dimensional vector, so we actually have like 2 times two SA constraints here. So what we do here is like the standard trick what people do in optimization. We move these constraints into the objective function. So the goal here, I mean, I'll just flash this, like say the loss function, and I will try to explain each component of this loss function. So the first component of the loss, which is minus C times F, actually motivates or makes the critic go up. So here if you see, we want to move as far away from Fk as possible, but in the positive sense, like you want to move above from Fk, but as far as possible. So this first term actually helps or mimics that component. And then we have this constraint T mu F greater than equal to F. So if your F is greater than T mu F, then there is some violation. if t mu f is actually greater than f, there is no violation. So what we do is we put that constraint here as f minus yi. So yi you can think of as a sample for t mu f. So if yi is a sample for t mu f, if f minus yi would be positive only for constraints which are violated, and for which it is actually satisfying, it will not be playing any role because of this plus sign. So what we do is we project into the positive orthent. So basically, whenever there is loss or violation, then there is some component of the violation is added to the loss. If there is if the constraint is satisfied, then it actually plays no role in the loss function. So the last part is in similar sense for f greater than fk, but since these fk's are random and it's still in the learning process, so what we do is we cannot completely rely on the critic in the exact previous step. So what we do is we say just have like a uniform lower bound, say try to be above q min as much as possible. So this second component, the third component of the loss is to say that try to be above a uniform lower bound q min instead of having a fk at each time step. So this loss, so wherever we see this dqn critic loss function, you can actually drop in with this loss function, and we actually have seen benefits. So now let us do that. So now let us take the dqn code from stable baselines 3. So this is the same code which we have taken from the stable baselines 3 implementation of dqn, and then this is exactly same, and we just go to the train function here. So let me go here to the train function. Exactly. So this is the default dqn loss. So here we have just replaced it with our loss function. Basically we have this term 1, and then we have term 2 and term 3, and we just take a mean of this, and then we just do the back propagation. So in place of default dqn loss, we have replaced it with the loss function which I just described, and let's see how it performs. So now let's run for the 256 layer case. So in this 256 layers, we use this hyperparameters of 1, and then we had this c lambda 1, lambda 2 as hyperparameters introduced in our new loss function. And for this set of hyperparameters, we actually see that RPA is doing good. So basically, there are two key things to like say note. So one is like we see there is a lower bound which is being maintained for the true Q value, and like though there can be like drop in performance of the policy, it is not going beyond the critic. So if you see here, this kind of guarantee is what is given in the theoretical sense, but it may actually not carry over in the like say in the model free setting. But in our simulations and in our observations, we have seen that it indeed actually carries over to even simulations in the model free setting as well. So if you see here, the policy improvement policy may degrade a bit, but then it is still guard. It has a guard of this critic, which will like, I mean, we can say that it may not go too far beyond the critic. So this is what happened in the 256 neuron case. So let's see what will happen in the 8 neurons case. So if we see here, so though it did not learn like to balance like for all the time steps, it is actually doing reasonably very well, and it has like the still the lower bound properties holding and so on. So let's see the comparison between DQN and ours. So yeah, so this plot actually represents DQN versus ours in the 256 case. So DQN can oscillate, and it can actually go below, and the critic value can be like too high even when the policy value is too low and so on. Whereas ours actually maintained a good lower bound, and then the performance is very satisfactory. Now let's come to the 8 neuron like say architecture. So basically, if you see here, the DQN learned and like say failed miserably, and then the critic is actually blowing up, giving no clue about the true value, and our RPA actually maintained and did a pretty good job. So next, what we did was we ran this algorithm on like say on this CRPA on this more complex environment like Hopper and so on. In interest of time, I will not be able to run all of those here. So what I did was we captured some videos. So this is what the performance of the robot is in the beginning. So basically, the goal of this is it's a one-legged robot you can think of. It is trying to actually learn to walk. So if you see here, in the beginning of the training, it is not even able to make even few steps. It's just falling maybe just after 1 or 2 steps. But after training using our algorithm, you can see here, it actually starts to walk very well. Oh, come on. Oh. Yeah, so I think our friends in the afternoon session will actually talk more about how RL was applied in the in robotics and so on. They actually wanted to bring a real robot and show the demonstrations, but I think the robot is in a different place, and I think they couldn't manage to bring it here. But I think they will talk more about how RL was used in robotics and so on. And another friend of mine will actually cover some actor-critic methods and policy gradients and so on. So with that, I would like to stop here. If you have any questions, I'm okay. Thank you. In the same CSA department. She'll be talking about actor critic and also some of her works. So over to you.
Yeah. Thank you. Hello all. Welcome back. Yeah, so today, first I will be talking about policy gradients and actor critic algorithms. Then we will run some simulations, and then I will be talking about few of my research works. Yeah, so let's get started. In the RL workshop webpage, you can, under the simulation links, you can go to the actor critic section. Yeah, so first let us talk about policy gradient and actor critic. So before in the value based methods, what was happening, we were estimating or calculating the value function, and from that we were deriving the optimal policy. But in policy gradient, these methods they learn the policy parameters. So here we parameterize the policy and we try to learn the policy parameter. We learn it based on the gradient of some scalar performance measure, L theta. L theta, we will define it later. And yeah, so here we don't need to depend on the value function. We can directly update the policy parameter. Yeah, so as I mentioned, we need a performance measure, and using the gradient of that function, we are updating the policy parameter. So we can define the objective function in our setting L theta in this manner. Here, mu theta, pi theta, these are, mu theta is the stationary distribution, and pi theta, it is the policy. It is parameterized by parameter theta. RSA, this is the single state reward for a specific state S and action A. We are getting RSA as the reward. And the policy gradient theorem, it gives us this expression for the gradient of the performance function, which is defined in this manner. Here Q theta SA, it is the state action value function, and yeah, this is the expression for the grad L theta. So yeah, let us look at the algorithm, Monte Carlo policy gradient algorithm. We also call it as reinforced algorithm. So yeah, here as I mentioned above, this is the expression for grad L theta. So in this algorithm, for Q theta SA, we use the returns. As you can see in this algorithm, GT, it is the return. So in this algorithm, what we do, for each episode, we calculate the returns for each state, and we use that return in that gradient formula, and we use that for updating the parameter, theta parameter, which is the policy parameter. But there are certain disadvantages in this policy gradient method. One is, as I said, we are using the returns for that Q value, right? So it may have high variance unless and until we have a very large number of episodes. And the second disadvantage is we are waiting for the full episode to get all the returns. Yeah, so now to overcome this, let us look at another method, that is actor-critic methods. These are the methods which have two component, I can say, actor and critic. So actor is for the policy and critic is for the value function. So these methods, they learn approximations to both the policy and value function. So yeah, now we can represent the value function either in the lookup table or in the function approximation setting. But as mentioned earlier in earlier talks, in lookup table, what is a problem is that if we have a limited state space or action space, then it is okay. But if the state space is very large or we have a continuous action space, then it is not feasible. So then we switch to function approximation setting. So in function approximation, instead of storing a value for each state or each state action pair explicitly, what we do, we have a parameter for the value function. We parameterize it, and we can either do it by linear function approximation or we can use neural networks. And yeah, so in this way we can tackle the problem. So yeah, as I said, it is crucial for dealing with large or continuous state spaces. And there it is not feasible to maintain a lookup table. So talking about linear function approximation, we can approximate it as mentioned here. So if v theta as mu, I can say here mu is the parameter, critic parameter, and we can using linear approximation, we can approximate is at phi s transpose mu, where phi, this is a feature mapping for each state. For each state we will already have a predefined feature vector, and our task is to estimate the critic parameter. Okay, now let us take a glimpse on the critic actor algorithm. So as I said before, here we will be having two parameters, actor and the critic, and our task will be to estimate both. So yeah, so in this algorithm, we first select an action and we observe the reward, and then we have a next state. So we first compute the temporal difference error, and then we use it to update the critic parameter and the actor parameter. And so this is the actor-critic algorithm using policy gradient. So yeah, so now we can see some simulation how actor-critic algorithm using policy gradient can be implemented. So yeah, this is the gymnasium package that we need to first install. And these are some of the packages that we need to import. I already ran the code all the cell before, so just we can take a look at that. So yeah, the first environment that we can take a look is the frozen lake environment. So this is basically a grid world setting, 4x4, and some of the cells are considered obstacle or hole, I can say. So if the agent reaches that cell, the episode is terminated. So the task of the agent is it should reach the goal from the starting. This is the starting state, and it should reach the goal subjected to the problem that the reward should be maximized. The long-term average reward should be maximized. Yeah, so here the action space for each cell, I can say, there are 4 possible actions that can be taken by the agent. Move left, move down, move right, and move up. But in some cells, like towards this corner cells, if the agent suppose let's take the case of the starting state. Here, if the action is taken left or up, so it will come back to the same state. Yeah, so the state, how it is represented here, the state is represented by an integer. So we can start from the start state 0, 1, 2. Horizontally, we can number it, and total, we can say the state is numbered from 0 to 15. And each episode starts with the state 0, 0, 0 coordinate. Yeah, and the reward function is defined in this manner for this environment. Either the agent goes to some other cell, or it reaches the hole or the obstacle, it gets 0 reward. Only when it reaches the goal state, it gets a +1 reward. Yeah, so this is the actor-critic network that we can build. We are using neural networks for building the actor network and the critic network. And yeah, this is the training function that we have defined. So yeah, and another thing I forgot to mention is this is the argument is slippery here. We can make it as true or false. True means for each action taken, like suppose currently we are in this state and the action is to go right. So if is slippery is false, then it will go towards that direction. But is slippery, if it's true, there is some probability that it can move in the perpendicular direction because of the slippery nature of the frozen lake. So as of now, I have tried to run the code by making is slippery false. So yeah, we are running for 5,000 episodes, and the discount factor we have taken as 0.9. And let us see, after after training, I have tried to plot the average reward with the number of steps, and this is the plot that we are getting. So initially it is in the exploration state, so there is some variance, but after a few number of steps, it is trying to reach some stability. And as our motive is to maximize the long-term average reward, so we can see that yeah, it is trying to get that. Now the second, okay, so this environment we had discrete state space and discrete actions. So the next environment is the pendulum one. Here we have an environment where at one we have a rod, and one end it is fixed and the other end is free. So the state space here, it has 3 components, cos theta, sin theta, and angular velocity. So theta, it is measured in this manner. From the, as you can see here, this is the theta. So cos theta, sin theta, and the angular velocity, these 3 are the components of the state space for this pendulum. And the action space is the torque that we apply. So the objective is we have to put it upwards, like the center of gravity of this pendulum should be above the fixed point. That is our target. So we need to apply some torque. So the action space is continuous. The action is, it is continuous, and the value can range from -2 to 2, the torque that we apply. So now, and yeah, the reward function is defined in this manner. It consists of the angular position, angular velocity, and the torque that we apply. And the starting state for this environment, it can be any random angle, which can range from -pi to pi. So yeah, and how will the episode terminate? There is only one criteria. The episode terminates when we reach 200 time steps for each episode. Okay, now let us run the actor-critic network for actor-critic algorithm for this environment. So yeah, we have defined in similar manner for pendulum also. And after running for around 300 episodes, I again plotted the average reward with number of time steps for this environment. And we can see here also actor-critic with policy gradient, initially there is some disturbance, like there is some variance we can see, but after a particular amount of time steps, it is trying to achieve some stability. It is we can see there is some less variance after some time steps. Okay, this was about the pendulum environment. Now the third environment that I took is the mountain car continuous environment. So here, this is an environment where we have a track in this manner, and we have a car. So if this car reaches this flag, then it is assigned some high positive reward. The exact reward I forgot, but yeah, plus 100 it is assigned. And in any other position, it will get a reward of -0.1 into action square, where action is the force that we apply to this car. So the state space here, how it is represented. So at any instant, we have two components. One is along the x-axis, its coordinate, and the second is the velocity of the car at that time. So these two constitutes the state space for this, and the action space is the action space is, yeah, as I mentioned above, the force that we apply, directional force to the car. So again, this is a case of continuous state and continuous action space. So yeah, let us now try to apply, yeah, and again the episode will end when there are two criteria. One is it will terminate if the position of the car is greater than or equal to 0.5. This is basically the goal position on the top of the right hill. So if it reaches here, the episode will end. Or if we reach 999 steps in each episode, then it will terminate. Yeah, so now again, let us try to run the actor-critic algorithm in this environment. So we tried 100 episodes for this as it was taking a lot of time. So we tried to run it for 100 episodes. And again, I tried to see the performance of the environment in terms of the average reward over time. And yeah, in this environment also, we can see that after a particular time steps, it is trying to attain some stability. And it is, yeah, and our motive is we want to maximize the long-term average reward. Yeah, so I think we are achieving that here. Okay, so this was a little demo on how we can apply, implement actor-critic algorithms on 2 to 3 different environments. Now I will talk about what work I have done. Basically, I have worked on actor-critic algorithms in my PhD journey. So yeah, let's see that. Yeah, so I have worked on actor-critic algorithms for, yeah. You have a question? Okay.
Could you go back to the pendulum example? Previous one. You are defining the observation space for the pendulum question. Can you hear me?
Yeah, you're audible.
Could you go back to the pendulum question?
Okay.
Yeah, where you're defining the observation space. Here, why is X and Y defined separately instead of having just theta as observation space and
yeah, but
defining
like
X and Y?
there can be discontinuity, right, in the theta. Like it can go from theta can be from 0 to 90, and again there can be discontinuity in the angle. But cos theta, sin theta, it is a continuous function.
No.
So because of that only.
But here you're measuring X and Y as cos theta and sin theta. All are continuous. There's no.
Yeah, cos theta, sin theta, they are continuous functions, right?
Yeah.
But theta, we are measuring its deviation from that x-axis, right? Here, as it been mentioned.
Yeah, so here again you're measuring theta. So why aren't you defining theta as the observation space?
Because theta, it can be discontinuous, right, after a particular time. But cos theta, sin theta, they are continuous function. To maintain that continuity, they have defined that. Are you clear?
No. If theta is discontinuous, then even cos theta and sin theta will be discontinuous.
Theta is the angle, right, between from the x-axis and the pendulum. So it can see the sin theta and cos theta function, they are continuous functions. So we wanted continuity in the state space, that's why. See, here theta can be from 0 to 90, right? Again, it can go to 120. Again, it reaches a maximum. It will again go to 0, right?
Mm-hmm.
So there is discontinuity, right?
Okay.
But cos theta, sin theta, they are continuous functions.
Okay.
Okay.
Hi, hello.
Yeah.
Yeah, that only in the reward function. Can you explain why it is like theta square plus 0.1 theta? Like how you define that reward?
This has actually I took this environment from OpenGym.
Okay, so
So
it
you
has
can
taken it from there only the reward.
Yeah, these environments are predefined. I am just showing how to carry out the implementation of actor critic algorithms on these environments. You can visit the page where there is a complete description about all these environments.
Okay, so like in general, how we like define rewards if we have to define? Like in different cases, you have taken different reward values.
Yeah, it depends on your goal, right? See, if you want the agent to follow a specific path, if it is getting deviated, so based on that you can assign negative rewards. If it is going in the way you desire, then you can assign positive rewards. Also based on that you can decide the magnitude of the negative rewards.
Okay, thank you.
Yeah. Okay, so I will be talking about two of my works. First one is the finite time analysis of constraint actor critic algorithms, and the second is about the critic actor algorithm. So this 3 time scale constraint actor critic algorithm, it was studied previously for their asymptotic convergence. So my task was to do the finite time analysis on these algorithms. And to see the convergence rate of these algorithms, to find out the sample complexity of this algorithm. And also previously few works were done on finite time analysis of 2 time scale actor critic, which was the unconstrained one. So we wanted to see whether including a constraint makes any impact on the sample complexity. Yeah, so this was our contribution. We carried out the finite time analysis of these two algorithms, 3 time scale constrained actor critic and constrained natural actor critic. And also we took some environments from the safety gym and we tried to run these algorithms against constraint DQN. So yeah, this is a constraint setting. In constraint MDP, in normal MDP, what happens, we make a transition from one state to other state and we get a reward. But here, along with the reward, we also get a cost. So, and the number of cost can be one or multiple. So here we have Qn, H1 and to HNN, where Qn is the cost that we want to minimize, but H1 and to HNN, these are also cost, but these are the constraint cost. We will specify specific thresholds on this cost. So yeah, this is the main aim of the algorithm. So we want to minimize the long-term average single stage cost, that is the QM, subject to the constraints that all the other single term average penalty costs, I can say, that should be below particular threshold. So we have, for here we have taken 1 to n separate penalty cost, and we have the constraint that the long term average of each cost should be below a particular threshold. And because this is a constraint optimization problem, we have Lagrange relaxation here, we have Lagrange multipliers, and when we do this to convert this constraint problem to the unconstrained one, and after doing this, we can say that initially this is the DSA plus this term. This is the single stage cost that we have in the unconstrained setting. Yeah, so this is the algorithm. In previous work, this was already studied for its asymptotic convergence properties. So our task was to find the convergence rate, the sample complexity, and to see whether the constraints are affecting the sample complexity if, compared to that of the unconstrained one. Yeah, so another algorithm, as I mentioned above, one was constraint actor critic and second was constraint natural actor critic. So in natural actor critic, what we have natural gradient, we have Fisher information matrix. We use the estimates of the Fisher information matrix in the policy gradient to update the policy parameter. As you can see here in the constraint natural actor critic, we have Gn inverse, which was not there in the actor critic algorithm constraint 1. So this is the difference. And so our aim was basically first to see whether the introduction of constraint is affecting the sample complexity or not, and after that we also tried to see whether the introduction of natural gradient is affecting the sample complexity or not. Yeah, so these were the learning rates that we used, and this is the result that we got. So our aim was to find the convergence rate of the actor, but as you can see in this theorem, we have terms like AK and BK, so this requires doing the analysis of the average cost estimate and the critic parameter. So we did the analysis of those parameters also, and finally putting it back into this theorem, this is the final result that we got. So yeah, this is our result. We go epsilon minus 2.5. This is exactly similar to that of the unconstrained one. So I can say that we found out that inclusion of constraint did not affect the sample complexity of the algorithm. So we went from 2 time scale to 3 time scale. Still the sample complexity was not affected. Yeah, and we also tried to see how it is these two algorithms are performing as compared to the constraint DQN. Basically our aim was to see whether the constraint is satisfied or not. So we can, as I said, the constraint can be one or many, but for simplicity in our experiments we took one constraint, and yeah, it was satisfied. Every algorithm in all the environment, 3 different environments, they satisfied this threshold. Yeah, so this was the first work. The second work, I worked on critic actor. So critic actor, it is a variation of actor critic algorithm. In actor critic, what happens? We have it is a 2 time scale where the actor is on the slower time scale than the critic. But in critic actor, it gets reversed. The learning rates get reversed, so the time scale gets reversed. The critic is on the slower time scale than the actor. So few years back, Borker, in his paper, he introduced this algorithm and he studied the asymptotic convergence properties of this algorithm for the tabular case. So what we did, we took this algorithm for the function approximation case, and here basically the learning rates of the actor and the critic has been reversed, and we tried to perform the finite time analysis of this algorithm. And these are some of the assumptions on the learning rates that we need to take to make the finite time analysis easier. C alpha, C gamma, these are the constants on the learning rate. So it depends on us what should we take. So based on this, we can adjust this. And yeah, and also one thing is here there is a projection operator on the critic. So this was also necessary for performing the finite time analysis for bounding the critic parameter. Yeah, so yeah, these are the results of our work. As in the previous work, it was an actor critic algorithm, so we focused on the convergence of the actor, but as it is a critic actor algorithm, our main task was to find the sample complexity for the convergence of the critic. But here also the convergence of critic, it involved convergence of other parameters like the actor and the average reward estimate. So yeah, we did the analysis of those estimates, and finally we got the sample complexity as you can see, epsilon minus 2 plus delta, where delta is not 0, but it is very, very close to 0. So yeah, this is better sample complexity than the 2 time scale actor critic algorithm that was achieved by Wu et al. Yeah, so like if this is an example, if we give delta is 0.01, so this is the sample complexity that we get. So delta cannot be 0, because if delta will be 0, then mu and sigma, as you can see here, mu and sigma, this will be same, and it will get converted to a 1 time scale algorithm. So we need to preserve the 2 time scale nature. So delta can be very small to 0, close to 0, but it cannot be 0. Yeah, also we tried to do some experiments. We tried to compare our critic actor algorithm with some single timescale actor critic, DQN, and PPO actor critic and critic actors. So basically this PPO actor critic and critic actor, these are in the average reward setting. We tried all these algorithms in the average reward setting. And yeah, this is the plots that we got. We saw that our critic actor algorithm in the long run average reward setting is competing well with other previous algorithms. Yeah, so that's all. Any questions? Sorry? In asymptotic, we see whether the estimates are converging, right? But in finite time analysis, we see the behavior of the estimates at any particular time.
But when you say in your evaluation, the average is performing good as you go over the time, right?
This one, you're talking about the plots.
Yes.
This plot is not for finite time analysis. We were just trying to see whether how it is comparing with other algorithms.
Okay, so this is not really
For the finite time analysis. Okay. Finite time analysis, the theoretical part here, we are checking the behavior of the algorithm at any finite time. But in asymptotic,
finite time analysis, you are showing some evaluation, right?
yeah, we are doing the analysis.
Some plots you are showing.
No, that is not for finite time analysis. After that, we tried to see how it is behaving as compared to other previous algorithms, just for the sake of doing experiments. Yeah.
So you said that the sample complexity you are able to reduce from 1 over epsilon to the power 2.5 to something close to 2.
Yeah.
So do you know the lower bounds on these different algorithms, and do you think maybe the analysis of the actor critic methods were poor, but perhaps they also have better sample complexity?
Yes,
do you have
yes.
some comments?
Yeah, that can be possible because this is one of the methods. There may be many methods and some can get better sample complexity on the actor critic also. That can be possible, but I don't think as of now anyone has tried to do that.
And in your simulations, do you see critic actor actually, showing faster convergence, maybe in tabular settings instead of this? So I don't know. Is this tabular setting? Or
No. This is function approximation using neural networks. We did.
I see.
This is, I think we can't conclude anything from this because very 2-3 environments only we tried and very few iterations and very few number of seeds. So we can't get a solid conclusion from this.
Okay, but do you have a conjecture like critic actor could be better in certain
Yeah,
scenarios?
it can be like if we carry out more experiments, more complex environments and all, then it can perform. But our main motive in this work was the theoretical one, so we focused on that.
Okay, thank you.
Yeah, thank you.
Okay, let's thank the speaker one more time.
We now have Prakrut and Ganga from the CPS department, so who will be talking about RL used in robotics and also have a small demo on the robot. Over to you. Thanks.
Hello. Yeah. Hi, I'm Prakrut Kotecha. I'm a PhD student at Stochastic Robotics Lab in IISc, and my guide is Professor Shishir Kolatia. In Stochastic Robotics Lab, we mainly work on 3 research focuses, where we develop the robot hardware, we have like optimal or safety-based control techniques, and we have robot learning. In this presentation, we'll be mainly focused on robot learning area. So first question comes to our mind is, what is robot learning exactly? So what we mean by robot learning is basically it's like an amalgamation between machine learning as well as robotics, where we try to use machine learning techniques to solve robotic tasks. And we like try to adapt to different kind of environments or learn new kind of skills that we can use in either static or dynamic environments, which we might have not seen during the training of the algorithms. So the main aspects that we need to focus on is the algorithm itself and the data that we get from the robots. So the classical methods that have been used before we went into purely learning-based methods are classical MPC methods or like optimization-based method in general, where you take the model of the robot and you use that to solve an optimization problem with some constraints, and you find a policy so that you can perform a given kind of task. So in the video, as you can see, you are able to actually walk on a relatively flat terrain with some uneven like steps put in between. And you're also able to adapt to, let's say, kind of disturbances that you have on the robot. You push the robot in a certain sense, but it's able to still stabilize and keep walking. So these are the kind of things that we were able to get from the previous methods. But the main issue was it was not able to move to multiple terrains. That is what we want, one of the main things. And it was very strict in terms of like assumptions that we take, because we can't, for a complex robot system, we can't write the full order dynamics of the system. So what we try to do is we approximate it to something which is relatively simpler, and we can solve it in real time. And that's what we put it on a robot when we are doing it. So one of the main issue is that we can't extrapolate those when we are moving to a more complex environment. But the benefits are you are able to understand what robot is going to do. So it's sort of what we call interpretability of controls and actions. So it's basically when we compute an action, we know what the robot should perform on hardware. And so we can say if that action is safe or an unsafe action. And also we are able to enforce constraints that we have on robots generally, like we don't want the leg of the robot to actually hit the other leg as well. So those kinds of constraints can be enforced in these kinds of techniques. But the state of the art is technically currently the learning-based methods, which have outperformed the classical works like by a huge margin. They're able to actually crawl through spaces, they're able to climb boxes, and they're able to do all kind of like random behavior, Markov behaviors that we want from a robot. The main issue here is that we don't have any kind of interpretability on what they'll be doing. All we know is that if we give this kind of observation, it will do something. We don't know what it might happen, like what it might do on the hardware itself. So one of the main issues here is we can't guarantee if the output that we get from the robot is safe or no. So that's why we call, like in terms of when we put learning-based methods, we call it as an unpredictable method, where we can't say if this will work or not work. And it also does not have any way till now to handle constraints in a hard constraint form. Basically, I need to enforce the constraint explicitly. In some sense, it's soft constrained methods where you can say that it will try to follow some constraints, but you can't ensure that it will follow all those constraints. So these are some of the main motivations that we use for our work. So the first work that we did, this is from back in 2019 when we started the quadruped locomotion part. Here what we are trying to do is we are trying to bring in interpretability in a sense that the motion that we see in the red in the 3 videos that we see on the right hand side, that's where we are trying to actually find the parameters to build these splines. So the output of the network is basically the parameters of these splines through which we can generate those splines and then ask the robot to follow those spline curves. So in a sense, we know how the spline looks, and so we know how the robot will move in a certain setting. This is one of the first attempts to bring interpretability into a system. So here the idea is basically you have the current state of the robot, you put it into that neural network, and the output of the neural network should be the parameters of the spline. And the reward is basically you want to move in the x direction, in this case the forward direction, and you want to minimize the energy of the robot, energy expenditure of the robot. So this is a very a very introductory way into the robotics learning phase. So some results from this is shown here. So we have tested it in relatively flat grounds, but in outdoor settings, indoor settings, if like in muddy settings where you actually have some sort of deformation in the ground itself. So, and all the three robots are actually in-house built robots. So we have tested it on our own hardwares, and we were able to get decent enough results. But the main challenge still was to get it on multiple terrains. That's what the main promise from learning-based method was. So then we move on to some more results on the same kind of work, where we developed bigger hardwares and we tested the same kind of algorithm on different hardwares. And we have one result where it actually works on slopes as well, but you need some sort of support so that it does not fall completely off, because it's still in a relatively younger phase, and you can have all these kinds of different behaviors like turning around in the same place, walking forward, walking backward, sidestepping, and all these different kind of behaviors because we are trying to predict the parameters of the spline and not exactly the motion itself. So one of the first work where we went into having this interpretability in terms of a multi-terrain setup itself was what we call as PIPLOCO. The key idea here is to actually integrate planning into the framework of RL itself. So here I'll explain the main idea in the next slide. So the idea is basically when we are training, we have something that we have added as a dreamer module, in which we are trying to learn the dynamics of the system as well as the reward and the value function of the system. And the value, all of these is learned in a supervised fashion itself because we have all those kinds of information when we are training the RL policy itself. But why we train the dreamer module is basically that we want the dreamer module to be used during deployment, where we are trying to get the constraints that we want incorporated while solving this optimization problem itself. So during deployment, what we are trying to do is optimization problem because we know we want that planning framework as well as the constraints to be incorporated when we are deploying something on the robot. So here we have this infinite horizon MPC. Why we call it infinite horizon is because we have this approximated value function that we add to the cost when we are deploying it. So we have a finite step prediction till h step where we use a single step reward. And from that onwards, we use the value function to make it an infinite horizon approximation. And with this, actually what we got as, if we use just a vanilla actor critic, so what happens after a few iterations is basically our approach learns way faster than what we have like a vanilla actor critic, which does erratic behavior till 1,000 iteration kind of setup also. Whereas our approach has already started learning how to walk in different directions. And we have some hardware results of this on a unitary Go1 setup, which will be shown here. So we are able to actually climb stairs. We are able to get this drop where it actually, after dropping also, because it does not know if there is a change in environment beforehand. So after dropping, it has to kind of stabilize itself. And these are the kind of behaviors that we train during simulation, during the training of the RL algorithm. But we can't technically guarantee all these environments are seen in the training algorithm. But it's actually able to adapt to different kind of scenarios on a hardware as well, because we have randomized that much environments, terrain environments. So it's kind of a robust policy that we're trying to build, not the most optimal policy. And that's why we say that we need like an MPC or an optimization problem to be solved during deployment so that it becomes a locally optimal solution rather than become just a robust solution. But one of the main issues still remained was that interpretability of the system, because the dynamics that we are learning is still a neural network. So we are trying to get the current observation, and we are just trying to predict the next observation, what it could be based on the action. So what we want is to understand how the robot will move given this action. And that's why we moved into something which we call as a physics embedded dynamics. So in physics embedded dynamics, what we do is basically when we have just a plain black box setup, in that sense, robot does not know where it might go. It just knows, okay, this was the previous observation. This is what I'm expecting as my next observation. But I don't know what that next observation means. So what we try to do is we encode the dynamics of the system, the full order dynamics of the system, and we try to learn the full order dynamics of the system itself. And that actually brings in the interpretability that we were looking for. And it's actually able to do a much longer horizon prediction with lesser error. So the training part actually remains the same, where we just replace the dynamics with a physics-informed dynamics, which is what we call, in this case, we are using Lagrangian dynamics. But we can use any other form. If you want to use like a Hamiltonian dynamics, we can still learn the same setup. But we have focused on Lagrangian dynamics because it gives the full state of the robot. And the deployment part is basically you warm start the policy you warm start the MPC using the policy from the RL, because you want to actually converge in a relatively smaller time, in real time basically. That's why we try to warm start the policy using RL. And then we start optimizing around that local policy itself. So until convergence, we sample the distribution from Q, the joint angle distributions, perform the linear system rollout using the dynamics of the system, compute the reward, which is basically sum of single step rewards plus the critic for approximation for infinite horizon. And then we select the maximal output. So select the trajectory which gives the maximal reward basically. And we keep repeating this until convergence, and then we return the first action itself. We don't give the whole action trajectory, we give the first action, and then once that step is taken, we again compute this whole optimization problem. So the key insight here is that originally what was happening was, we were solving this whole forward dynamics, which is actually slow because it has something which we call as inversion of a big matrix. Because in case of robots, we need a mass matrix, which is, as soon as you go into a complex system, it becomes larger and larger. So in case of quadrupeds, it becomes an 18 cross 18 matrix, which is very hard to invert in real time, actually. So what we shift this optimization problem into is something we call as an inverse dynamics in robotics, where we don't have to actually invert the mass matrix. We just have this direct calculation of U, but the issue is U is not our actual actions on the robot. U is the torques calculated, but we use U to keep it consistent with the dynamics. So we actually solve it in the Q space, that's our actions, but we actually use U's to compute the rewards as well as to keep it consistent with the dynamics. So it becomes much faster. And yeah, so now moving on to our next method, which started moving on multiple terrains. Now we actually want it to move with the weights, with changing weights on it. So what we have put is basically we have put a tray on it, and we have took like 2 kg steel balls, which we put as a weight in the tray. And so what we do here is we train 2 different policies. We have one nominal policy which can work on any kind of terrains, and one what we call as an adaptive policy, where it can actually adapt to different kind of load that is being put on the robot itself. So if you put any kind of, like, let's say 2 kg balls, 4 kg balls, 10 kg balls on the robot, it should be able to still move with similar efficiency and across multiple terrains. So the extra actions that are supposed to be added to the multi-terrain policy itself, that is what comes from the adaptive policy. So we train these 2 in parallel, and we are actually able to get decent enough results with this setup. So these are some rewards that we use to train the 2 policies. And the simulation results are like compared to the baseline has this jerky behaviors where the ball might just fly out of the box itself, or it might stop walking because of the extra weight. The height goes down because we are not expecting that much weight, and so hence we don't apply that much action on the robot. Whereas in our case, when we add that adaptive policy, it's actually able to walk through. It has some hiccups in between, but it's actually able to cross the whole terrain, whole stair terrain. This is the most difficult stair terrain that we have in the simulation setup. So if you see on hardware, what happens is as soon as you add weight, in baseline, in traditionally if you don't have an adaptive policy, the height of the robot keeps going down. and there is a risk of it hitting the ground itself with its leg continuously. As you can see, it hits the legs to the ground, or the knees of the robot a lot on the ground. Whereas with our policy, it actually maintains the same height that we have, whatever weight we put, till we have trained it for 10 kgs. It's a 12 kg robot itself. So we put almost equal to that on the robot. And it can actually carry it without changing the height. And we have tested it on multiple terrains. We have tested it on slopes, in random terrains of tree leaves, stairs up and stairs down. Stairs down is something that actually is really difficult, but we don't realize because technically you're going down and the weight is actually pushing you forward. So that momentum is what you have to counter, and you have to stabilize the robot. And it's actually able to do it pretty well without falling off the whole stairs. And so this is actually all we have. This is the team that has built the quadruped robot. We'll have a small demo of the quadruped itself. And I think we'll have it off the stage itself, because it will make a lot of sound on the stage. Yeah. If you have any questions in the meantime, you can ask. She's setting up the robot. Yeah.
First
Yeah.
of all, great job.
Yeah.
It looks really good. So, can you explain what is it exactly that makes it so adaptive policy when you deploy it and in the changes?
So you're asking here, right? Yeah. So here what happens is, in the adapt observation history that we're talking about, we're actually trying to give the torques, computed torques, added to the observation, which we're not giving previously. And we are giving that to the adaptive policy so that it knows what kind of action it was applying before, and hence try to give extra some joint angle so that it tries to keep the base height constant. So initially what we're doing is, with the nominal policy itself, even if we give the torques, it's becoming like a next step prediction where it's trying to, okay, I need to maintain the height. But next step, let's say the weight again changes. Now you're not able to keep up with the change of weight, and hence the height decreases. But in this case, because we are giving a separate policy, which kind of makes it an adaptive in the same time step. Yes.
First of all, there is a fantastic work when you. My question is this:
Yes.
when you combine the NPC with RL,
Yes.
is the robot adaptive?
Yes.
For adapting to the weight, have you done any theoretical analysis about the guarantees of the convergence of the optimal policies for the RL?
So let me clear it out first that we are not doing MPC for the adaptive part. The MPCs were done for the previous two methods where we are trying to bring interpretability. For the adaptive part, directly we are using the policy, the RL policy itself. We're not using the MPC in this case. Yes.
While you are using the RL, have
Yes.
you done any theoretical work on the convergence of the policy?
No, we are not working on the theoretical part of convergence of the policy. Yes. Yeah. Yeah, so she'll do the demo of the robot now. You guys can see. This is one of our safer policies which might not travel through the terrains, but because it's a crowded setup, we don't want it to do any kind of weird behaviors here. So what she is doing is she is giving the velocity command from the joystick, and it walks in that direction. It can turn around, it can move forward, move backward, and with the given velocity. So if you have a higher velocity, it will move faster. So if you see in this case, you will have quadrupeds performing, the quadruped is the robot. It's performing a very symmetric kind of a gait. That's what we showed as our first method, where you try to parameterize the spline, and you do that itself on the robot. And so this is what I say, this is the most safe method that we can go for, but it does not do very well on different kind of terrains. This is mainly all we have for the robot demo as well. It just moves around, you can do sidestepping and stuff. Sorry?
Yeah, so I would like to thank all the speakers of this hands-on tutorial session. I request all the speakers to come on stage so that I can hand over a small token of appreciation to them. Prashansa? Is Prashansa here? Yeah, maybe you can just come over here. Just come over, yeah. You guys can come over. All right, first let's give a big round of applause for them. I think very exciting work is happening. Okay, and to each group, maybe I'll try to give a token of appreciation. Okay, thank you. Thank you. Okay, maybe you guys can go to the middle. Okay. All right, so that's all for today. Just a quick announcement about tomorrow's session. So from tomorrow, the main workshop will begin. We will begin at 9 AM tomorrow, right? And also keep in mind that tomorrow we have planned a cultural evening as well as a gala dinner after that, right? So the cultural event will start at 6:30 PM and it will be in the same auditorium, right? And the gala dinner will be similarly outside where we have lunch itself. Is that okay? All right. That's all for today. Thanks a lot. I hope you enjoyed.